Pyrometry, or on the measurement of fire and heat. First part, on fire and heat in general. First chapter. Preliminary basic concepts. Section 1. The inner nature of bodies remains, despite all physical and chemical investigations, still very much concealed. True, magnifying glasses could give hope of getting to know the smallest parts more closely. The discovery made in this way, that there are tiny little globules that give blood its red color, seemed to justify this hope. Yet one did not find anything further than that nature, in the small, is just as composed as in the large. Where one had hoped to find constituent particles, one caught sight of little animals, and was compelled to conclude that one was still infinitely far from what one was seeking. The shape of the constituent parts, the manner of their combination, the forces by which they are held together, the resulting differences in their outward form, their hardness, toughness, fluidity, and so on. All these are things that must be inferred rather than seen. The art of inferring them correctly has not yet advanced so far that it does not often get mixed up with what is called groping in the dark. Section 2. These reflections quite properly begin where fire and heat are the subject. Is fire a special kind of matter? Is it different from light? These are questions long since raised, which have been answered now one way, now another. In this respect, fire is as unknown to us as the constituent parts of any other body. But there is the further circumstance that fire exerts its effects for the most part in bodies. And these effects are so varied as the composition of bodies may always be, and are so altered by it when the state of the fire is changed. It is undeniable that in order to see clearly here the inner nature of bodies, their constituent parts and their manner of combination would have to be more closely known. But since we are still far from that, we must likewise take refuge in inference. And that is a somewhat uncertain, for I do not really understand by this the adoption of arbitrary opinions by which one effect or another can indeed be explained. While, on the other hand, many others remain unexplained, or, what is worse, are directly contradicted by the opinion that has been adopted. But in order to make a beginning, I shall follow common usage of language, that is, the customary names. The word warmth has various meanings that must be indicated more precisely. First, warmth insofar as it is felt. In this sense, it comes very close to us. And since what is really being discussed here is the measure of warmth, we can at once introduce the names by which the sensation of the various degrees of warmth has been expressed in ordinary speech. The warmth at which we feel most comfortable we call pleasant or temperate. Our sensation is then, as it were, zero. If the warmth is so much greater that we actually feel warmth as warmth, we say, it is warm. If the warmth increases further, it is very warm. A still more perceptible degree is called hot or also sultry. These names refer to the weather or the air. With water, we use the terms lukewarm, warm, hot, boiling. And when it is above a certain degree of heat, it is no longer called hot, but burning, because our sensation of warmth is then joined by the sensation of pain. And this is precisely what makes it so that no one willingly lets his hand be burned. We use similar names with regard to other bodies as well. As long as we can touch them without pain, we call them warm, very warm, hot. Opposed to warmth, according to our sensation, is cold, and in such a way that we regard the latter as something just as real and active as the former. In fact, even when one sweats from great heat, one shudders in severe cold, and in still more severe cold one freezes, just as one is scorched and burned by still greater heat. All this is very natural. It refers only to what we feel. But from this, no conclusion can be drawn about cold considered in itself. For if we were to judge by our sensation, we would also have to say that cold burns. The Latins did, in fact, say, "Urum Montana knives," and this is not a far-fetched expression. One need only hold one's hand in snow until it begins to become quite numb, and then go into a heated room if one wishes to feel the burning more strongly. I myself have seen that the skin did not peel off. Certain people of the religious orders who go barefoot in the snow. From these remarks it follows that what we call warm refers first of all to our sensation, and indicates the intermediate degrees between lukewarm and hot. We ascribe warmth to bodies insofar as we call them warm. And since we find that bodies are not warm of themselves, but become now warmer, now colder, we are compelled to look for the origin of warmth outside them. We then find very powerful causes, namely actual fire and sun. Yet, on closer investigation, there are still some other causes that have something peculiar about them. It was found that when metals are hammered or filed, they become hot. Likewise, heat can arise through strong rubbing. Wood can be set on fire by friction. Again, it was found that in the fermentation of wine and beer, warmth arises. Finally, there are also substances that become hot merely by being mixed. In this way, warmth and fire are produced where previously there was none, or at least none was felt. This is, to be sure, an occasion to investigate more precisely, but also an occasion to make our knowledge still more confusing. It sounds extraordinary when someone boasts of the trick of being able to turn cold into warmth on a warm stove. That means finding cold where there is nothing but warmth. And yet the matter goes on. If one pours aqua fortis on iron, it fizzes up with heat. If one pours the same acid on snow, it becomes even noticeably colder. With reflections of this kind, one is easily led to the view that warmth and cold are still far more unknown things. Meanwhile, these things are only unknown in a relative sense. Warmth and cold, considered as sensations, are concepts that are in no way as clear as the concepts of light and colors may be. Fire shows itself to us visibly in the form of flame or glowing coal. That it acts more strongly or more weakly according to its size and distance is also immediately evident from sensation. Without burning ourselves, we dare not come too near a fire. We rightly conclude from this that it must be even hotter at a closer distance, that the warmth or the heat of the fire is communicated to bodies in this way is likewise evident from the fact that we find them warmer when we touch them than they were before. We likewise find that they acquire the same degree of warmth more quickly when they are nearer the fire, or also when at the same distance the fire is larger. From this, we find that bodies heated by a fire lose the warmth they have acquired as soon as they are removed from the fire. Similar experiences also occur with sunlight. Finally, common experience teaches that not every kind of wood burns equally well, that not all flames give the same heat, and that one can intensify weak heat by blowing on it. But the effect of fire on bodies does not consist merely in making them warmer. With slight warmth, one notices no other difference in things than, for example, that wet bodies become dry. But with stronger heating, the hardness or solidity of bodies changes greatly. In boiling water, an egg becomes hard, whereas butter, tallow, fat, and the like melt. Bricks must first acquire their hardness in the fire, whereas limestone is turned into powder, wood into ash, and metals into glass. Changes of this kind have something astonishing about them, and it is precisely for that reason that we are inclined to imagine in fire forces suited to such transformations. Yet, however strong these forces may be, they still have their limits. Gold and silver do indeed become fluid in fire, and the foreign parts burn away. But the part that is properly gold and silver cannot be burned by fire, whereas other metals are transformed into lime and glass. Some bodies withstand the heat of the fiercest fire unaltered. Most, however, are changed so that one no longer recognizes them. All these changes are now as well known to the learned as to those who work with fire. That gunpowder has something quite peculiar about it when it is ignited is too well known for me to need to describe it in more detail. To the fact that heat passes from warmer bodies to colder ones, another circumstance is added, namely that it moves upward more easily than downward. The flickering of a flame catches the eye. In boiling water, along with the heat, a quantity of bubbles rises. If one holds a hand at the same distance above, below, or beside a strongly heated body, the difference in warmth is easily felt. An iron that glows at only one end will soon glow at the other as well, if it is held straight upward over that end. Second chapter, the measurable in fire and heat. 9. What has been said so far is for the most part drawn from common experience. And without adducing many circumstances, one can already see from it that not everything can be determined more precisely. It is enough to throw out and to consider what occurs. Various things have already been indicated. Now, however, without adding much more, I will return again to usage of language, this time to the Greek, so as to help myself with it. Languages are actually arranged so that they express concepts that are correctly composed from their parts or roots, as often as this accords with the rules of the language, yet much is lacking in this. Still, at the very least, It should not be lacking that, according to the manner in which concepts are combined, words are also combined. And this is what is given here in Greek with a rather concise brevity. I have already chosen the word pyrometry as the title of this work. Now the words pyrostatics, pyrolics, and pyrodynamics may also appear. And because of certain differences, thermometry may be set alongside pyrometry or opposed to it. These names could, in themselves, serve well as headings for just as many main divisions of pyrometry. And then one might also take up pyrobolics and pyrotechnics in their most general meaning, and perhaps also add pyrophorics, pyrousics, pyronomics, and the like. But I think the intention of the word, as it would be understood, would not be followed. It is aimed more at words than at things. Still, it will not be useless to consider a little more closely the meaning and scope of these designations. Often words can also lead to things, and for that reason, it is always worthwhile. 11. We have already seen that forces can be thought of in fire and heat. With forces, one can connect an equilibrium, and this quite naturally leads to something like statics. In this respect, one may think of a peristatics. What maintains the equilibrium by the force of fire or heat is, for that very reason, also a force, because only things of the same kind can take in the immeasurable nature of fire and warmth, can be set equal. In truth, the matter is the reverse. Precisely from this force that resists fire, we conclude that fire too has a force, and indeed not merely the force to warm, by which resistance must be overcome, but also the force to separate and to transform. In general, what opposes fire as a force is the hardness and firmness of bodies already mentioned, and especially those bodies which, under burning, become soft and fluid, or else fall apart into lime and ash. A body without any applied force cannot fall apart into pieces. But since fire divides bodies, often even shatters them, it is therefore quite right to ascribe to it the force required for this. 12. Fire, or warmth considered as a force, can also be in equilibrium with itself. And it is so whenever a body in which it is present is equally warm in all its parts. Now, take the circumstance already mentioned, 6, that warmth moves away from a body when it is in a colder place. From this, it follows that fire in a body has no lasting equilibrium unless the body is just as warm as the place in which it is. By place, I mean here any location whatsoever, whether in the air, in water, in other bodies, or even in empty space. For experiments with the air pump have long since shown that warmth has no aversion to a vacuum. 13. This equilibrium of warmth in different bodies and outside them depends above all on their capacity for equilibrium, just as the equilibrium of liquid matter depends on heavier and lighter kinds. In connected tubes, a column of mercury balances a column of water 14 times higher, and it makes no difference whether the tube is of uniform width throughout or not. In the same way, a larger body contains a greater quantity of warmth, yet the warmth is not therefore stronger, and thus, in bodies of different density with equally strong warmth, there can be a greater or a smaller quantity of warmth. Common experience does not decide much about this. One does indeed find bodies which, of the same size, take up warmth more quickly than others. But whether in equally long time the same quantity of warmth enters them, this remains undecided and must be determined by special experiments. I mention it here as something not in itself improbable, in order to bring out more clearly the similarity between pyrostatics and hydrostatics. One sees without difficulty that this latter word, the difference is only this: hydrostatics, as the word itself suggests, originally concerned water, and little by little was extended to other fluid substances, whereas pyrostatics quite properly confines itself to fire and heat, and can therefore remain within the true sense of the word. Section 14. Moreover, the very word pyrostatics naturally gives rise to the question of the lightness or heaviness of fire. I find in Schroeder's Gerquichtsstunden that the French writer whom he follows proposed a method for weighing fire, though Schroeder himself thinks little of it. One is to weigh the wood before it is set alight and then weigh the ash after it has burned. In this way, one would indeed find that a good deal of mass, smoke, and vapor has been lost. But this would also have to be weighed. Only then would the question arise whether the weight of fire amounts to anything that can be estimated by a balance. Fire is lighter than air, even when the air is very rarefied by burning. One can see, therefore, that if one wanted to weigh a burning piece of iron after it had cooled again, the balance would have to be extremely sensitive, and even then it would scarcely show more than the difference requires. The same applies to the dynamical experiments by which it has been found that metallic calxes are heavier than the metals from which they were made. If one wishes to prove from this that the increase in weight comes from fire remaining behind in the calx, the outflow and influence of fire within bodies is a circumstance that already justifies the term pyrolysis. Pyrolysis is, in a sense, the science of the movement and flow of fire. It arises from the assumed equality of the forces of fire within and outside a body, or also in different parts of the same body. In the narrower sense, pyrolysis may also mean the conduction of fire through tubes, and thus include, for example, chimneys, wind ovens, stovepipes, and similar fluids, as well as the reverberatory or blast furnaces used in assaying. Even in fire hearths, the flame is often drawn under several ovens, and in ore heaps, the beds are often warmed by such flues. In bathhouses, too, there are cases where warm spring water is led through long pipes to the bathhouse, and then, together with the water, its heat must likewise be carried along. That is to say, one must arrange things so that the water does not cool underway. Pyrodynamics concerns, in general, the forces of fire insofar as they are produced by changes in bodies. The sunlight concentrated by art, the power of fire in gunpowder, the strengthening of its force by enclosing and releasing it, the outbursts, melting, burning, the calcining of bodies in fire, steam engines, the rapid force of vapors, and so on. All of this comes into consideration in several ways. Force, space, mass, and time are compared with one another in various ways, and the result shows very considerable differences. Glass, wood, and stones burst when they are exposed too quickly to fire. In other cases, as for example with gunpowder, and often also in extinguishing and in igniting, a rapid effect is required, whereas there are also many cases where a moderate but sustained force of fire has the desired effect. The art of cooking provides in boiling, roasting, baking, and so on, a number of examples, and such examples are found in all cases where the effect produced by fire is meant to proceed only to a certain degree, insofar as the word warmth has its meaning only with respect to those degrees that can be felt by us without pain. Thermometry comes into play. In a narrower sense, however, the measure of warmth can then be applied according to the judgment of our sensation. The common thermometers were, from their first invention, arranged for this purpose. Their inventor went from the greatest winter cold to the strongest summer warmth, and even now the degrees are described as freezing cold, very cold cold, moderate warm, very warm, great heat, or other similar terms. They plainly refer to our judgment of the state of the air, for what is called great heat is a heat in which glowing iron can cool very strongly. Pyroballistics and pyrotechnics are particular applications of pyrometry insofar as they belong to the art of gunnery and of fireworks. Fire itself is not thrown, but rather burning and glowing bodies. For one never finds what is properly fire by itself, but always bound up with bodies and other materials. The pure flame is nevertheless only a burning vapor. In the most general sense, pyrotechnics is understood to mean the art of dealing with fire, and to that extent it extends very far, and just as far will pyrology also extend. If one finally looks to the laws according to which fire is directed in its effects, then thus one may also count as part of it the pyronomy, or pyronomics, which in truth also includes the so-called fire ordinances in cities. Finally, I have also mentioned Section 10, the pyrophoric admonition. This is meant especially to indicate the means of keeping and preserving fire, along with its fuel, for a long time. Section 19. Since the sun is an inexhaustible source of warmth, which it communicates to us through the plants and summer fruits, and since, through our changes of season and their weathering, it brings about the alternations of the seasons, this deserves in pyrometry a special investigation, which may be called pyrometeorology. Section 20. If, then, it were only a matter of names, we would have gathered here a good stock of terms, indeed such as have a considerable scope and meaning, and thus we could already have named so many individual parts of pyrometry. In truth, however, they serve rather for a mere pyrology, or pyroscopy. For the arrangement of such a vocabulary would be devised more for memory than for understanding, and would be more an explanation of words than of things. With this store of names, the matter itself still remains unknown. If we are to learn to know it more closely, we must penetrate deeply into the interior of bodies. For there we find the workshop where fire produces its finest and greatest effects. Yet this penetration into the interior of bodies is not so easy. It presupposes much prior knowledge, and for the most part, we must first infer from the outward effects that fall under the senses how it must be constituted inwardly, so that such outward effects can occur. These outward effects must therefore first be known to us. One sees without difficulty that in this way the order of the presentation is determined, pyrometry, or on the measure of fire and heat. Second part, on the expansion of bodies by heat. First chapter. On the expansion of air by heat, 21, I have already remarked. P14, that fire is never found by itself anywhere, but is always combined with other matter. The chemists, who are especially concerned with calling fire and its effects by their proper names, find that in combustible bodies there is a certain combustible substance, phlogiston, which, when it departs from bodies through burning, leaves nothing behind but a fire-resistant ash, and in most cases produces a fire-resistant glassy acid. This phlogiston is probably not what one calls fire itself, but it is akin to it, and in my opinion deserves to be regarded as having the closest relationship to it. It is found chiefly in fatty or oily substances, and by means of such substances, it can in particular be restored to calcined metals, so that they regain their ductility and metallic form. The difficulty of preserving fire, or even phlogiston, in a pure state, and of measuring its quantity and strength directly, caused that one must therefore have resorted to other means in order to achieve this purpose. Now, since in the effects of fire one finds, in so many different ways, something that can be increased or diminished with the strength or the quantity of the fire, it is understood that one proceeds best when one ensures that this happens in the same proportion. For in other cases, the inequality must first be corrected by calculation and by the proper arrangement of the scale of degrees. The first to attempt something of this kind was Cornelis Drebbel of Alkmaar, North Holland. He was, as far as one finds in the Alkmaar Chronicle, born there in the year 1572. In his early youth, his parents, who were well off, provided him with a good common education. His chief inclination was toward mechanical and chemical curiosities, and especially toward inventing new devices and secrets. Through this, he came into contact with several learned men. The invention of perpetual motion is among the intentions he pursued. He sought it partly in chemical mixtures, partly also in forces of nature that were still unknown up to that time. It may remain undecided whether the long-known steam spheres, eolipolas, or other experiments, gave him the occasion to discover that air is greatly expanded by warmth and contracts again in cold, and in particular, that even the force of the sun's warmth is sufficient to expand the air in such a way that all kinds of movements can thereby be produced. In Jardin's continuation of Schwenter's De Liceae Physico-Mathematicae, page 399, I find that Drebbel in the year 1607 published at Alkmaar a book on perpetual motion. In that same year, according to Jardin, Drebbel's patron, Emperor Rudolf II, had Drebbel brought to Prague in an unrecognized manner as a prisoner, and gave him the freedom of the city so that he might obtain his improvement without having to pay the 100 thalers demanded by the castle captain. The proposal to present his device to the emperor, which also succeeded. Among other things, he presented a cabinet with 2 little curtains and several pictures. These little curtains, or as he called them, hangings and tapestries, as soon as the sun shines upon them, open of themselves and a pleasant music is heard. But when the sun sets, or a cloud passes before it, the music stops, and the hangings and tapestries close. After the opening, Neptune and Phoebus also appear with their retinue. A fountain makes the water spring continually from pipes, and when the sun shines upon it, the water leaps up to a height of 100 pipes, and so on. Also, there was still a glass in which water rises and falls by itself in the space of 24 hours and about 40 minutes, twice, so that it indicates the hours and quarters of the day correctly. These movements also occur when one holds the glass in the hand. Of all this, Drebel says that the King of England, James I, and many thousands of people have actually seen such a device. I mentioned these circumstances. Drebel is usually described as a magician from the Netherlands, and at most it is said of him that he served King James and invented the so-called Drebel thermometer and the air weather glass. In any case, people still imagine him as a wondrous and mysterious man who makes far too much of his affairs, reveals nothing, and judges very confusedly, as one can see from his book on the nature and properties of the elements, which has been republished from time to time. I find nothing particularly remarkable in these accusations. Curiosity, especially about hidden things, has always been a powerful driving force, leading to many attempts and with them to true discoveries. If one takes Drebel's treatise as it was at the beginning of the previous century and connects it with the chemical, or more properly speaking, alchemical ideas of that time, one will easily understand that things could not appear very clear in Drebel's mind. Meanwhile, he had the advantage over many teachers of natural science of his day, and those who followed him. He tested his ideas by real experiments. That such tests sometimes turned out successfully is already shown by the fact that the air weather glass and his thermometer belong to me like friends. The Dutch envoy at the English and French courts, whom I shall not name, called him his friend. With King James in England he was held in high esteem. Emperor Ferdinand II gave him his portrait as a gift, and when, in 1620, he was taken prisoner in the Palatinate by imperial war forces along with other persons of the emperor's court, he was set free at the intercession of the King of England and the States General and sent to London, where he died in 1634. This is what I have been able to find about Drebel, the invention of his thermometer, or, more properly speaking, of the air weather glass produced by warmth, dates from the beginning of the previous century. James III came to the English throne in 1603. Drebel's book appeared in 1607. Within this period, Drebel was in London and in Prague. His clavichord is also not the an invention that can be made in a few hours and brought into working order. It took time, and thus the date is very likely the year 1603. With regard to the 73rd year of Drebel's life, one ascribes the invention of Drebel's thermometer to certain Italians as well, to Galileo, and even to Fra Paolo Sarpi, who is famous in the history of the state, and Santorio is also still put forward as the inventor. In the case of Fra Paolo, it is probable that he received news of the invention through his correspondence, and that through him it became known in Italy. Galileo is said to have received it only from Diodati, his pupil and greatest admirer. Perhaps Galileo may have made improvements to the invention, and the same may also have happened with Santorio, for it is well enough known that Drebel's thermometer was by no means what it ought to have been, although Drebel must have understood its principle very well. Robert Flood, who among all made the most reflections on it, and, unlike Drebel, not a mechanical artificer but a secretive thinker, claims he found the invention in a manuscript at least 500 years old. That may be so, only it must also be doubted whether Drebel had read the manuscript or not. In itself, the invention seems to be as old as the steam bowls, which Vitruvius already describes as long known and used for blowing up a fire. The swelling of pigs and other animals' bladders, and likewise fish bladders in warmth, their bursting with a crack when one lays them uncut in the fire. These two are things long known to all the world. Yet from there to Drebel's thermometer is still a step that was not actually taken until it could be taken. 26. How Drebel may have made his thermometer is unknown to me. Presumably it was a glass bulb with a long tube. Through the warmth of the hand, the air in the bulb expands and is partly driven out. If the tube is then set in water and the hand removed from the bulb, the liquid rises in the tube to a certain height and remains so until the warmth of the surrounding air changes. This invention is the simplest of all and probably the first. It was soon found that colored water, red wine, cherry water, when copper plates had been placed in it, and it had thereby taken on a green color, was more dangerous, that brandy or spirits was safer, and that plain water should be used only as a last resort. It was also found that much depends on the proportion between the width of the bulb and that of the tube, if the instrument is to be sensitive. At first, to set the tube in a vessel of water, bending it around and blowing onto it, a globe open at the top, into which the water or other liquid substance could be poured. In this way, the instrument could be carried about more convenient. In the recreational mathematics, which Scott used as the basis for his dithermometer arc, and which was published by Kircher and Scott with great care and diligence, I find that as early as 1636, people already knew how to fit the globe and tube together in such a way that the liquid substance ran through the entire length of the tube from summer to winter. Further, that this space was then divided by the Italians into 18 parts, but by the Dutch into 4 parts. And finally, that each of these 8 parts has now again been subdivided into 8 smaller ones. This difference in subdivision probably arises from the fact that the Italians followed their then customary so-called 4 degrees of warmth, by which they were accustomed to judge the force of cold and the weather, and which, as far as is known to me, were distinguished by the names cold and dry, cold and moist, warm and moist, warm and dry. The philosophers, on the other hand, preferred to place 4 degrees of warmth above the temperate state of the air and 4 degrees of cold below it, because they chiefly considered the meteorological use and gave for these 8 divisions names that are easy to understand. Temperate, lukewarm, warm, very warm, hot, likewise frosty, cold, very cold, bitterly cold, 27. Now, there remained an even greater step to take, in order finally to conclude that since air is so easily expanded by warmth, it can also be compressed by external force. That this happens in the breathing of animals and fish was certainly known from the earliest times. Yet how often one sees things from which correct conclusions could be drawn, and yet they are not truly drawn until a long time later. Otto von Guericke fell upon this, and in a quite special way, he wanted to pump the water out of a cask filled with water, so that its surface, and with it the air, might sink farther. His intention was to obtain an empty space for the air. His hope failed, but he found circumstances from which he could conclude that the air was immediately pumped out with the water, and that despite its uninterrupted continuation, it did not fill the space again, but rather spread itself out and became thinner by its own force. At the same time, he found that it ran together again, and that the outer free air likewise always shows this same force of spreading out. In that 2 hemispheres that fit well together, when the air has been pumped out of their cavity, pressed together very strongly. He presented the experiment solemnly before the assembled to the imperial diet, and this helped to make the matter widely noticed. About that same time, namely in 1643, Torricelli invented the barometer, and thus all the steps were taken to learn more precisely the weight, the pressure, and the buoyant force of the air. Second chapter. On the expansion of other materials by heat, section 28. It was soon found that the glass sphere by which one had weighed the air, and which therefore ought to be a barometer in fact, indicated only the specific weight of the air, and that Torricelli's tube deserved the name barometer far more. Likewise, it was found that the so-called thermometer does not indicate purely the changes of heat, but that changes in the weight of the air also contribute greatly, and that consequently its variations are a mixture of barometric and properly thermometric changes. Now, by means of the barometer, one could of course distinguish these effects by a sufficient calculation, but this was troublesome, and so people also sought by other experiments to construct instruments that change only with heat, section 29. In this, the Florentine Accademia del Cimento succeeded. It observed that among liquid materials, especially spirit of wine expands very noticeably. One therefore took this, filled glass bulbs with long tubes with it, and sealed the end of the tube. This arrangement has been preserved to this day. The year of this invention is not known to me. It is, however, described in the Academy's Saggio, which appeared in 1667, together with several other thermometric experiments. The Academy itself was founded in 1657 by Grand Duke Leopold of Florence, and since in 1667, these so-called Florentine thermometers were already known in many countries. And the academicians also report that some of their thermometers took on color in the glass, something that does not happen in just a few days. the time of the invention must be closer to 1657 than to 1667. Section 30. The academicians made such instruments for their own use in various sizes, and state how they determined the scale in each case. They adopted two extreme points. They fixed the lowest point by placing the thermometer in snow and ice. Now it is well known that the winter cold is not very great in Florence, and that snow and ice are not much colder there than they are elsewhere. So this point is not very uncertain. They found the other, or highest, point by setting the thermometer in the sun on the warmest days. This degree is somewhat uncertain. Yet Dorelli and Malpighi say that this degree is precisely the one that corresponds to the greatest heat in the shade, between 1 and 2 o'clock in the afternoon. From this, it follows that the Florentine academicians, in the method mentioned above, section 26, remained essentially with the Dutch way of dividing the thermometer. Only instead of 8 philosophical degrees, they used 80, and instead of 4 medical degrees, they used 40. In the first scale, the 80th degree was that of summer sunshine, and they set the cold of snow at the 80th, so that they still counted 20 degrees downward to reach 0. Likewise, they counted 20 degrees above the 80th, and thus the whole scale contained 100 degrees in all. Section 31. The other thermometer had only 50 degrees in all. In this one, too, the 40th degree was that of summer sunshine. They set the common point of cold, or found it, at the 11th or 12th, and thus these degrees agree with the 17th of the first division. Section 32. Finally, they made still more sensitive thermometers, which they divided into 300 degrees, or perhaps even into 400. With this latter, they carried out experiments to see how water, when it is turned into ice, first expands as it freezes, then contracts again as it warms, and finally expands once more. This thermometer stood in the summer sun at about the 400th degree, in ice or freezing water at about the 140th, and in ice that had been mixed with sal ammoniac, it fell to the 35th, perhaps even to the 15th degree. The first thermometer fell to the 7th degree when the ice was mixed with saltpeter, and to the 5th degree when they mixed it with sal ammoniac. From this, the following corresponding degrees result. On the expansion of other materials by heat. Indicators. First thermometer, second thermometer, summer, warmth of the sun cows, warmth of the blood, freezing water, severe winter cold at Florence ice that has formed 33. The Florentine thermometers soon became known in all countries. They did not have the very troublesome error of the Drebel thermometers, nor the additional inconvenience that they were easy to break. Yet they were less sensitive, because they did not take on degrees of heat as quickly as Drebels. At first, and for a long time afterward, it was Italians who concerned themselves with improving barometers and thermometers, and who carried them from city to sell. These people departed greatly from the care that the Florentine Academy had observed in dividing the scales of their thermometers. And for that very reason it was found everywhere, to one's annoyance, that thermometers had no intelligible common language, and that their divisions did not agree with one another. Indeed, some even blamed the thermometers themselves and produced experiments in which thermometers hung side by side were tested, from which one was supposed to prove that their changes were not only unequal, but not even proportional. Such investigations may be found, for example, in Wolff's physical experiments. All 34, the academicians of Florence further, say that they also found in water, oil, quicksilver, and many other liquid materials that they expand through heat. They found the same in salts and metals, but they carried out no experiments to determine how much the expansion amounted to at different degrees of heat. Halley seems to have been the first to do so, who in 1693, therefore, with air, with spirit of wine, and with myrrh 20, on the expansion of other substances by heat. When mercury was used for certain experiments, it was found that in boiling water the mercury expanded by 1/7,000th part, and this led to taking the heat of boiling water as a definite degree, and using it to divide thermometers, as Fahrenheit proposed. But this 1/7,000th part does not determine how many degrees of cold are to be indicated, nor from what point the counting must begin. For that reason, it also made his determination of the expansion of air and of alcohol unusable. The proposition that bodies expand in warmth and contract in cold suffers, in some cases, a considerable limitation, especially when liquid substances begin to freeze. Ice, depending on whether it freezes more quickly or more slowly, is 1/9, 1/11, or 1/16 lighter than water. Many circumstances, however, contribute to increasing this difference. The freezing particles of water arrange themselves in a particular order and in a loose packed position, as one sees at the edges of vessels in which water begins to freeze. And one sees the same in snow as in frozen water droplets. Hollow tubes also form in frozen ice and make it lighter than if it were melted, since in this way many earthy and glassy parts are given off in the form of slags. Wood, too, always contains moisture, which, when the wood lies in the cold, expands like ice. One sees without effort that the cause of the expansive force of heat must lie in the way the force itself acts. Yet the force remains no less real for that. Third chapter. The air thermometer, first section, on compressing air by external force. 36. That air can be compressed and thereby made to exert a stronger force could have been known to everyone long ago from the simple play of children. Children push the pith out of a piece of elder wood to obtain a completely hollow tube. They cut a wooden cylinder that fits tightly inside it. Then they make little pellets of paper that can be driven into the tube with some force. They push the first pellet in at one end of the tube only far enough that it is just inside. But the other pellet they drive in with effort from the other end until the first one shoots out, producing a louder crack the more force was needed. In Upper Germany, such a tube is called a Schleiderbuchse, probably because instead of the paper pellets, sloes may also be used. Everything depends on the pellets fitting the tube exactly. Since I do not know the history of this children's game, I cannot say how old it is. But one can easily see that it amounts to the same thing as the so-called wind guns because the pellet is driven out by the compression of the air. The so-called blowpipe also belongs here. It is still used by enthusiasts for shooting birds. They call the pellets Ivor pellets because much depends on their being light. They put these into the tube, blow hard into it, and drive it out with such speed that they can shoot a bird down from a tree. Here the air is compressed by blowing. 37. Despite this plaything, Otto von Guericke has the credit for having made the rapid force of air, its expansibility and compressibility, into a scientific understanding. Yet he did not immediately reflect on the mathematical part of this knowledge. That was reserved for Mariotte, who was inclined to compare the compressing force with the degree of compression, that is, with the reduced space, and to determine the ratio between the two. He found that a 2, 3, or 4-fold increase of the force makes the space occupied by the compressed air 2, 3, or 4 times narrower or smaller, so that the space stands in the inverse ratio to the force. The experiment he therefore performed, and repeated often, is very well conceived. Meanwhile, it seems he carried it only as far as a 4-fold compression. It is uncertain what would follow if one extended it to complete compression. Others, however, doubt whether the gas would then remain exactly correct. See de Bernoulli Hydrodynamics, P20238. This prompted Professor Sulzer to undertake Mariotte's experiment anew and to continue it up to an 8-fold compression of the air. Memoirs of the Berlin Academy, 1753, pp. 116-122. The compression was carried out in Mariotte's manner, in a bent glass tube where the air in the shorter arm was pressed by the external air and by a column of mercury. The space occupied by the air is represented by the height in the tube, in which it was increasingly compressed. Likewise, the total compressing force is indicated by the height of a mercury column. Both are given in Rhineland inches and their decimal parts. The result was as follows. That is 348 by the numbers in the first column. 39. This was done according to Mariotte's rule, because by that rule, the numbers in the second column ought to stand in inverse proportion to the numbers in the first column. Now the numbers in the second column are smaller than the numbers in the third column calculated by this rule. From this it follows that the air is compressed somewhat more than would correspond to the measure of the compressing force. In Müller's Collegium Experimentale, I find a similar experiment, though not set out so fully, which, in decimal parts of the presumably Nuremberg foot, gives the following determination. Height of the pressure. Height of the air column, observe, calculated. This likewise shows that the air is compressed somewhat more than according to Mariotte's rule. 41. In order to compare these experiments with the preceding ones, they must first be brought to the same scale. This can be done with sufficient accuracy if, with reference to the last table, one multiplies all the numbers in the first column by 2 divided by 2.35, and all the numbers in the other two columns by 2 divided by 0.64. In this way, from the two tables, the following results. On the compression of air by external force, height of the pressure, height of the air column, observed, calculated, difference. The main question now is, how do the differences in the fourth column arise? One finds that, for the most part, they are fairly uniform, and this is shown precisely by the fact that, in the experiment, the pressure on the air bladder was increased only by a very small addition of mercury. The first of these differences is indeed equal to 0, because for calculating the third column, I took the height of the air column of 12 inches as the value at the start. But if, in fact, the air had been allowed to compress more than the Marriott rule requires, then I too should have had to take more than 12 inches as the initial height of the air column, since the air is already in a compressed state. Because the barometer at 29 inches indicates equilibrium, thus one could say that the very first number in the third column ought to have been assumed greater than that of the second column. I therefore want to add an indeterminate amount, 12 of XX. Then, according to the Marriott rule, the corresponding number on the compression of air by external force of the third column equals 22,000, divided by 21,000 times 12 plus X, that is 11.42 plus 22,000, divided by 21,000 times X. And this will give in the fourth column the difference 7 plus 22,000 divided by 21,7 plus 22,000 divided. And in just the same way, for every number n in the first column, the difference is found to be AT plus 22,000 divided by 21,000 times X, where $, represents the differences contained in the fourth column. But since at first X increases only very slowly, the expression 22,000 divided by 21,000 times X also remains fairly uniform for the first differences, and therefore the jump from each 0 to H7 always remains. But if one wanted to assume X large enough to eliminate this, then it would be all the more impossible to eliminate it with the subsequent differences. E43. It is therefore far less forced to play a role. The mercury is poured into the longer tube. This produces oscillations in the shorter tube, and with these it is only too easy for some air to be drawn in between the tube and the mercury. This reduces the height of the air column. This already seems to be found from the first glance at the table, since, as we see from it, the differences from the second onward are already very noticeable. The fact that the air becomes ever denser, and therefore the last differences, even if they were quite equal to the first, would still have to displace more air, and consequently the air drawn in between the mercury and the tube would have to be very noticeable and visible. This consideration has no weight here, because this air is likewise compressed into a narrow space, and therefore can be just as little perceptible at the beginning. Here it is not a matter of mass, but of space. And the differences in the fourth column show that this space increases very little, indeed in the end decreases rather than increases. The oscillations will also finally become smaller and smaller, and this causes less and less air to be drawn in between the mercury and the tube. B44. That the reason given here has something to it, and is in fact the true one, experiments with the barometer have shown, by which one has convinced oneself that, in order to obtain it properly and in agreement, the mercury barometers filled over a fire usually stand about 2 lines higher than others that are filled in the ordinary way. So from the mercury, especially from the spaces between it and the tube, so much air has been drawn upward into the empty space that is to be filled, that it can hold the mercury in equilibrium by 2 lines. When it is compressed, it can therefore draw in just as much again. About 45. I therefore find no reason to depart from Marriott's rule. Marriott presents it in 3 places. In his essay on air, in the discourse on the movement of water, and in the essay on logic, and each time he speaks of it as something that one will find confirmed by experiments on air. Air that has been enclosed and compressed retains its force unchanged for many years. One cannot therefore say that it becomes weaker through compression, and for that reason contracts more than Marriott's rule would require. In general, those who, following Bernoulli's hydrodynamics, are inclined to believe that air contracts less than this rule states do so, because in a narrower space, what is material in the air comes more into consideration. so that it seems the air could not be compressed further than until its particles come to lie against one another. In which case, however, it would probably have to become just as dense as water. Second section. On the force of heat in the air, Mariott's rule presupposes that in his experiments, the warmth of the compressed air must remain the same. This already follows from Drebel's experience, namely that greater warmth expands the air more than it would expand under the same pressure. Mariotte really wanted only to determine how the density of the air relates to the compressing force. Accordingly, the experiment necessarily had to be carried out with the warmth remaining unchanged. The degree of warmth does not matter here. The main condition is that it does not change in the meantime. Another. And in experiments of this kind, one has always taken this into account, since the influence of heat on the expansion of air has been known since Drebel's time. In such experiments, one finds a double equilibrium. First, that between the weight of the air and the compressing force, and then that between the expanding force of heat and the counterpressure of the air. This shows that the force by which heat expands the air is equal to the force by which the air's compressing force maintains equilibrium. This latter force is commonly called the lifting weight, and in the same way one commonly considers the pressure of the external air, as well as the surface that has to withstand the pressure and counterpressure. From this one has long since derived the following two propositions. The first is that, at the same degree of heat, the density as well as the speed of the air are in inverse proportion to the lifting weight. This is precisely the mathematical proposition considered in the preceding section, Joule 49. The second is that at the same density, the force of heat is in proportion to the speed of the air or to the lifting weight. This follows from the preceding. For if, at a certain degree of heat, the lifting weight is P and the heat is increased, then the density can be kept the same only by an increased weight P. And this must be greater in proportion to the density, C48. The increase of heat, therefore, causes the air at the same density to maintain equilibrium under a greater pressure. Its force has therefore increased in the ratio of P to P50. This proposition has not always been understood correctly enough, because from it, one immediately derived another proposition in which the condition of equal density was omitted. One concluded, namely, and this was quite wrong, that at the same pressure, the force of heat is in proportion to the expansion or the increase of volume grows. For IEPA relates to EGPP as the original volume, relates to the volume R enlarged by heat 48. But the original heat in the rarefied air is really only altered in the ratio if the air is kept at the same density. And one would be greatly mistaken if one wished to omit this condition. The proof of the proposition rests on it. Therefore, it must also be understood in the proposition itself. To determine the ratio of the pressing forces DGPE and ADP, which are necessary, when the heat is changed to maintain the density by means of the ratio of the volumes, by which the weight EGP expands the air because of the increased heat. In this way, one does not need to compress the air again and again and again and to find the weight EPPA. The volume can be measured more easily. And then OHEP pool 52. This was noted in order to remove the ambiguity of the first stated proposition, and would in fact be true if one wished to understand the proposition DGPA in such a way that heat, even in the air thinned by it, possessed a force increased in proportion to the measure of expansion. But this is not so, because heat would then continue to act to infinity without ever ceasing. Yet its expanding force does cease precisely because it expands. For every force that spreads itself over a greater space becomes weaker in each part by that very fact. The expansion of the air, therefore, goes only so far, until the heat is weak enough for the external pressure and the weight of the air to hold it in equilibrium. If, then, we take the expansion of the air under the same pressure as the measure of the heat, or of the force of heat in the air, we assume that the force of heat is to be reckoned in air of equal density. Now, a certain degree of density must be taken as a basis, and this is in a sense arbitrary so long as the question is only on the force of heat in the air to compare the degrees of heat with one another. Properly speaking, it ought to be the greatest possible density that air can attain, and which it then reaches when it collapses together through cold or is compressed by an external force until its particles upon one another. One may imagine the air now made into a very dense mass. The elasticity of the air makes it clear that at such absolute density, it would occupy little space. If the degree of heat decreases as 1, 1/2, 1/4, 1/8 down to 0, in order to maintain the same density, the rising weight must likewise decrease as 1, 1/8. But if the weight decreases, then the volume increases as 1, 1/2, 1/4, 1/8 down to 0. This, however, must be understood only insofar as the uniformity of the rule and the brevity of the expression require it. For although the volume does not become entirely 0, it can nevertheless be regarded as 0, because in comparison with the previous volume, it is already so small that it may, for practical purposes, be considered nothing. See 4555. Now the degree of heat is 0, properly speaking, what one may call absolute cold. Consequently, at absolute cold, the volume of the air is 0, or as good as 0. That is to say, in absolute cold, the air is compressed so tightly that its particles are pierced through, or so to speak, become as dense as water. The expansion of air, therefore, arises chiefly from heat. Amundsen is, as far as I know, the first who recognized this, and who demonstrated it to the Royal Academy of Sciences in Paris at the beginning of the present century. An invention which, in my opinion, could have been held to be very good, and which perhaps for that very reason, because it is so simple and so true, found unbelievers. Amundsen's made a very useful application of it in the improved, and at the same time, scientifically reported Trebellic thermometer. Yet during his lifetime, which lasted only a few more years, he could not bring it about that this long-neglected thermometer was compared with the Amundsen's thermometer. True, an Amundsen's thermometer was set up at the Paris Observatory, but it was immediately hung in another room, as if every comparison were to be carefully avoided. This comparison did not begin until some years after Amundsen's death, and it was carried out as negligently as it could possibly be, for Amundsen's thermometer introduced an intelligible language. And that was precisely what La Hire did not want to grant his own, or else he already considered it superfluous, because he believed he had fixed points in it, namely, the temperature in the hall of the observatory, and the one in the attic of the air in the open hall of the observatory at the time when it freezes in the field, an observation which he read aloud every year at the Academy, when he reported on his weather observation. But this was not exactly the means to advance the sciences with united forces. Third section, the Drebel thermometer, together with its modifications. Al 57, I shall present only the most common kinds of the Drebel thermometer. The simplest, and probably the oldest, is the one shown in the figure. One pours into a small vessel water, spirits of wine, or some other liquid substance. Then one takes a glass tube BC, on the upper end of which a bulb is blown. One warms the bulb, either over a flame or in any other way, until some air has been driven out through the tube. Then, while it is still warm, one sets the open end of the tube in B into the liquid. The result is that, as the bulb cools again, the air inside it contracts. Since through this cooling the expansive force becomes smaller, the pressure of the external air is able to drive the liquid up into the tube until it has reached a height C, where it then remains standing as long as the air in the bulb has the same warmth and the external air the same pressure. The height BC becomes greater the more the bulb has been warmed. If it is warmed too much, the water or other liquid rises up into the bulb, and this must be avoided. Conversely, it does not rise high enough if the bulb has been warmed too little. It is also easy to see that much depends on a suitable proportion between the length and inner width of the tube and the size of the bulb. This was left to the skill of the craftsman throughout the whole previous century. Some may, as already mentioned above, 26, have hit upon it fairly well, but there was nothing methodical about it. They proceeded, however, carelessly and hastily, and in doing so failed all the more because they pressed the scale into the glass and used it with all thermometers, however different the internal conditions might be. And since they proceeded in the same way with the Florentine thermometers, the complaints about the inequality of the thermometers and their degrees naturally increased. It was soon found that, when water was used for this purpose, it froze in the cold, and that water, wine vinegar, and other liquid materials in vessel B gradually dried up, and therefore had to be poured in again. To prevent evaporation as much as possible, They poured a little oil on the surface. Leupold used a mixture of 1/4 aqua fortis, 1 part wine vinegar, and 2 parts water, whereby the aqua fortis is colored green with copper or blue with silver. They also considered taking mercury instead of such watery materials. Yet, because of the very great weight of the mercury, the outcome was noticeably different. Finally, one sees without difficulty that such thermometers could not well be carried about, and that it was best to leave them in the place where they were once set, as 59. Even setting this defect aside, it will not be useless if we determine number and measure more precisely. The first point that matters in this regard concerns the dimensions of the bulb and the tube and their selection. The tube is best when it is everywhere of equal width and yet truly cylindrical, for an uneven tube would first have to be reduced by calculation to a uniform one, and the scale to be applied to it would have to be divided into unequal parts. In order to test the tube, one therefore lets a portion of mercury into it, which can easily be done by warming and then cooling the bulb. By varying the inclination of the tube, one then easily brings it about that the mercury runs back and forth into the bulb, and one can see where it remains standing. In this way, one can examine whether the tube at all distances from the bulb maintains the same width. This necessarily occurs when the tube is uniformly wide throughout. One therefore has an easy means of assuring oneself of this. If one has tubes drawn from glassworks, the middle is usually the most uniform. It is also advisable that the mercury in the tube have a length of at least 1 inch, for if one errs somewhat in measuring the length, the error matters all the less the longer the mercury column admitted into the tube is. Once one has assured oneself of the goodness of the tube, it is weighed very exactly. Then the bulb is filled with mercury up to a point on the tube D, which one marks. After that, everything is weighed again. If one subtracts from this weight that of the glass, one obtains the weight of the mercury. Finally, the tube, too, is filled with mercury, right up to a point marked at the NB. And everything is weighed once more. If, from this weight, one subtracts each of the 2 preceding ones, one finds how much mercury has been poured in altogether, and how much in particular lies in the tube between the points B and D. When filling, one must take care that no air remains mixed in with the mercury. But if one wants to proceed more exactly, one lets the mercury boil, both when the bulb is filled and when afterward the tube is filled. This boiling is done with glass funnels made especially for that purpose. If these are too short, the work can be made easier by pushing a fine iron wire into the tube, because the mercury runs down between the wire and the tube, while at the same time the air is allowed to rise. Now, the determined weight of the mercury is exactly proportional to the space it occupies, and if one wishes to know it, one can find the size of the space, both in the bulb and in the tube, in cubic inches and lines. If one knows the weight of a cubic inch of mercury, it is understood that one would have to take account of the differences in weights and inch measures. But since here it depends only on the ratio, one may leave that aside in the weights. If water or wine spirit is used, and the tube BD is at most about a foot long, one need not pay much attention to the difference in pressure of the column BC as it rises or falls, in order to determine the ratio of the tube to the bulb, because the pressure of the outer air is 33 to 34 times greater. If the thermometer is to serve only for measuring changes of temperature, it is enough if the bulb contains 4 times as much space as the tube, for I have found that when, in the cold of freezing water, the space of the air is 1,000, then this space, in the cold of snow, which is mixed with almost as much saltpeter, has been reduced to 918, and on the other hand, at the degree of warmth of the human body, it expands to 1,130. Such a degree of heat is probably never reached by the air in the shade in Europe, and just as rarely, at least in our region, does it happen that it should reach the cold of frozen snow. Now, from 918 to 130 is roughly as 4 to 5. If, therefore, the space in the tube is 1/4 of an inch in diameter and the bulb is 1 inch, then the water, or the liquid substance, in the most severe winter cold will rise almost up to the bulb. And, on the other hand, in the greatest summer heat will sink down almost to the little vessel B. The tube can be made somewhat narrower still, partly because of the pressure of the column CB and partly because of the variable pressure of the outside air, 63. If the bulb still has to be blown, one can fill the tube with mercury so that it stands between 2 points marked at both ends. From the weight of the mercury, the volume of the tube can then be calculated. Taking this volume 4 times gives the volume of the bulb, and from this one can then find the inner diameter of the bulb, which one then has blown to this size, or else selects one from among several bulbs already blown and fuses it onto the tube, or does it oneself if one knows how to handle it. Now imagine, beside the tube, 2 lines EG and FH, which rise straight upward from the level of the surface BCO. The length of the first, FH, is to be as long as a tube of equal width would be that contained as much space as the tube BD and the bulb taken together. The length of the other line, EG, is to be equal to the height of a column of the liquid substance that at a given barometer height balances the pressure of the outside air. Thus, EG will be equal to the barometer height when mercury is used for the instrument, but with water or spirits it will have to be taken 14 or 16 times greater, because these substances are that many times lighter than mercury. In any case, it is good to determine the true ratio exactly. It is understood that EG changes at all times in proportion to the barometer height. If the liquid substance stands in the tube at C, and one draws MCN horizontal, then NH represents the volume of air in the thermometer, and mg, its elastic force, with the pressure of the outside air, is Eg, but this is opposed by the column CB. Consequently, there remains only mg, which then, according to the measure of the force with which the air in the erg thermometer is pressed, but this pressure is equal to the elastic force of the air in the erg thermometer. Heat, or the force of heat in the air, changes both in proportion to NH and in proportion to mg. For if, at the same density, it remains in the same proportion to the force of pressure. If, on the other hand, mg remains constant and NH changes, then under the same external pressure, the volume of the air in the erg thermometer changes, and with it, its density. But since heat must be expressed by its force in an air of a definite density, 53, and then the expansion can be set proportional, 50, it follows that he is also in proportion to NH. Accordingly, it is in proportion to the product MGJ, NH-67. It therefore comes down to this, that this product must be fixed for a particular case, namely, where both the weight of the air and the heat have a definite degree. For this one may take the mean barometric height at sea level, or that of 28 Paris inches, or 336 lines. And since it has been found that the degree of cold of freezing water is a very definite degree, it will likewise be good to adopt this as the basis. Now, if the liquid material used for the instrument is m times lighter than mercury, then a column of 335 N lines will balance a mercury column of 336 lines. And so for a given barometric height, 336 B N lines. EG must be set to 336 B. The length FH is indicated by a line, and the height BC is GE when B choose 0 and the cold of freezing water is found in the air whose warmth we wish to set as 1000. In other cases, it is HEME, where the barometric height is 336 down B and the warmth C is found. Under these assumptions, we have 336 N on BN, EF chaired 1000. CI4 C1300 EF 336 and NEF 3F. One therefore sees that so long as he does not change GCI in an arithmetic progression, but that, on the other hand, if y remains constant, changes with O as well as with H. Back in July 1751, I had already made such a thermometer with mercury in order to compare its behavior both with the barometer and with other thermometers. At that time, I had only the first guidelines, and the observations continued with them for several years. In February 1769, I made another one, of which the dimensions and calculations had been given. The diameter of the bulb is 9 lines, Paris measure, and the bulb held 1238 grains of mercury, Berlin 115 lines long, and held 105 grains of mercury. The length of 9 inches contained 102 grains. If, instead of the bulb, one had a tube of the same width and the same material, it would have to be 1311 lines long. If one adds to this the 115 lines, the total length would be 1426 lines. Subtract 4 lines from this, namely the depth to which the tube stands in the mercury at B, and thus let FH be 1022 lines. Since BD likewise is BD square 115 for Chicha 122. I now placed the bulb in boiling water to drive out the air, and when this had happened, I set the end of the tube B into the mercury, which then rose by the pressure of the atmosphere in the bulb up to the height BC of 3 inches. Since here in H1 and at H142 lines, the formula becomes 336 DG 336 by 1022 E. I therefore set the instrument there and found that the mercury stood at 63 lines. But the barometer then stood at 27 inches, 8 lines, chi 3 lines, accordingly. For this case, B, chi 60. Therefore, 336, E 1422, E 336, 4 to 63, 1422, 63. From this one finds H 68.9, or taking a round number, E 69 lines, and thus one obtains the Drebel thermometer, together with its modification. By means of this formula, the degrees of heat could now be determined. For example, 1770 on the 24th of August was one of the warmest days. The barometer then stood at 28 inches, 2 lines, that is 338 lines. And the instrument gave E var epsilon 44.5 lines. With this I find C kilo and 21 parts in 1772. On the 21st of June, in weather just as warm, I had B 1 fruit. On the other hand, in 1776, on the 27th of January, in the then severe cold, which, however, had already eased a little, I found BK 4 inches 5 lines. E very line. This gives CH 942 in order, moreover, to make the test easier and to compute such observations more quickly, I provided myself with a special step key scale, serving this purpose with obliquely running lines by which for B12 inches as well as for B12 inches as well. And for values of it has already been remarked by Leupold that the mercury in these thermometers moves somewhat sluggishly, as also happens in barometers when the tube is narrow. But one can easily help it along by tapping the instrument or by a slight shaking. Besides, it takes on changes of heat and cold very quickly. Al 70. If one tilts this instrument, the mercury rises in the tube. Let varphi be the angle that the tube then makes with the vertical line. And let XX be the length of the mercury in the tube measured from the surface, BD. Then at the same warmth in general, 336 N, EX 336. Where for mercury, one sets NH110, which then gives a 36 BB X, if X, varphi, BE, var epsilon, are determined by experiments, then can be found by means of this equation. Yet this procedure is somewhat troublesome because, so to speak, it proceeds from the small to the large. It has also been suggested to bend the tube at E and U so that it runs obliquely, or to lay it completely horizontal. But the movement of the mercury in the tube is thereby made even more sluggish. After this first and simplest form of the Drebel thermometer, various other forms have been given to it, of which in turn the simplest are shown in the second and third figures. The second differs from the first only in that the little vessel B is attached directly to the tube itself. At the top, at D, a small opening is left in it, so that air is not trapped in 2 places, namely, in A and in B. The calculation based on the first figure does not differ in any way from that based on the second, 72. A difference, however, appears in the third figure. Here the bulb is below, and the tube is open at the top at D. The air enclosed in it therefore sustains not only the pressure of the outside air, but also that of the liquid material in EC here, as above 60. The ratio of the space in the tube to the space in the bulb must be determined. One can fasten a small paper funnel to D, which fits tightly around the tube on the outside. It can also be attached with wax or sealing lacquer. One then sets the tube upright and pours mercury into the little funnel. In this way, the mercury will run down into the tube by its own weight, or with slight shaking, compress the air, and finally fill the bulb in part, more so the higher the tube is. One then determines, partly from the ratio of the spaces and partly from the height ED, which corresponds to the degree of heat, how far the mercury must rise in D. When I made such an instrument in 1776, I used the heat of boiling water for this purpose. I placed the bulb in it, held the tube straight upright, and let as much mercury run in from above as the heat of the boiling water could drive out. I collected the mercury that ran out by means of an arrangement that is easy to devise. When nothing more would run out, I lifted the glass vessel out of the water so that no more mercury would flow out through cooling. It soon came to the point where it was in equilibrium with the cooling air in the bulb. I noted the barometer height, partly because of the pressure of the outside air, partly because of the actual degree of heat of the boiling water. Since, according to the truth of the previously stated assumption, this degree is governed by the height of the barometer, instead of the heat of boiling water, one may choose other degrees of heat, whether greater or small. Only the degree must not be so great that the mercury begins to boil. Also, because of the chosen degree, the vessel of the mercury must remain steadily at the same level, so that all oscillations of the mercury are avoided. After the work is completed, the instrument is weighed in order to find how much mercury it now contains. How much is in the tube FEC can be found by calculation. And then it also follows how much is in the bulb, and from this further how much space the air in the bulb occupies. Since this air, before it is filled, occupied the bulb as well as the tube, it follows from this how much it has been compressed. And one can then see whether the ratio between the pressure of the outside air and the mercury column is the same as the pressure of the outside air alone, and how it is actually to be understood. If, meanwhile, neither the heaviness nor the warmth of the outside air has changed, 73. Amontage was the first to apply the principles GT 950 and thereby to make it possible to construct such a thermometer in a scientific manner. He gave the tube from E to B a length of about 48 inches and filled it with mercury in such a way that when the bulb was placed in standing water, the air within it could maintain a pressure of 73 inches of mercury, that is, the pressure of the outside air in equilibrium. Since all fine thermometers were supposed to satisfy this condition, he used, for the filling, a special procedure which he described in the memoirs of the Paris Academy for 1702. But this condition is not at all necessary, because it is much easier to set the scale according to the instrument than to arrange the instrument according to the scale. And because, since one has learned to know more precisely the expansion of air at various definite degrees of heat, the ratio of the bulb to the tube can be determined in advance by calculation, according to the desired convention. I also find that Poligny, Gravesonde, and others who made Amonton's thermometers did not adhere so exactly to this condition, all 74. In this thermometer, the height EC, which is read off each time from the barometer, is added. In this way, one obtains the measure of the force with which the air in A is compressed. The expansion of the air is determined by the rising and falling of the mercury in C. Here one chooses a somewhat large bulb so that when the mercury in C rises and falls, the height of the surface in B changes only imperceptibly. The tube must also be wide enough so that the surface in B comes nearer to the center point and thereby becomes broader. Assuming this, the quantity of mercury in the part of the tube Fe can be regarded as constant, and the height EC can be counted from E as from a fixed point. Only the height Fe is variable, and the step scale attached at E would have to rise and can be pushed down again, or else the calculation can be carried out by means of the variable height of point E75. Now imagine a tube of the same bore containing exactly as much space as the bulb. Let the length of this tube be a lines. Let the length of the tube FED be lines. It is understood that the tube must be of uniform bore, so that two parts of its capacity can be represented by the length of those two parts. Let the length EBE and ECGX. The mercury fills a length Q. Let the barometric height BB and the heat BC. It has been assumed that the pressure on the air in always by X done. Further, QEX is the space occupied by the mercury in the bulb. Consequently, a GEX is the space occupied by the air in the bulb. Now the heat is in the same ratio as the space is to the pressure. If one therefore takes M as a coefficient, then MC cheap Edmonton now says is that his bulb has a diameter of 39 lines, but that the tube is in clear width, 1 held line. The diameter of the bulb is therefore 78 times greater than that of the tube. The bulb consequently contains 78 sheet 369 times more space than a tube section 1 line long. Therefore, as much space as a tube 13,182 feet long. One easily sees that, even if a considerable part of the bulb were filled with mercury, the space for the air would still remain so large that the small height EX by contrast need not be considered, and thus without noticeable error, MCBX QE may be set, and consequently the heat remains proportional to the height of the pressure. All 77. This, then, is the reason why Amintons expresses the degrees of heat by the height BX, and gives it in it. Since his division is now very arbitrary, if one does not construct the thermometer exactly according to his instructions. And since it is far more useful to set the degree of cold of freezing water at 1,000, whereas Amundsen sets it at 5½ inches, one will first have to make this reduction, and then present the observations introduced here, which he made directly with his thermometer. One finds Drebel's thermometer, together with its variations. He also made other observations which he did indeed reduce to the degrees of his thermometer, but in a very incorrect way, and therefore they do not belong here. I will here once and for all remind the reader that when I speak of degrees of the air thermometer, I always understand by them the degree of cold of freezing water as 1,000. These degrees are at the same time the absolute degrees of heat, insofar as one understands by that the force of heat in air of a definite density. Here now follow Amundsen's observations. Table of Amundsen's thermometer. Degrees of the air thermometer, 51 inches, 6 lines, 1,000, freezing water, 54, 0, 1,049. In the cellar of the Paris Observatory, 54, 4, 1,055. Warmth of the hand in moderate summer air from various persons, 58, 2, 1,129. Warmth of the hand in moderate summer air from various persons, 58, 9, 1141. Warmth of the hand in moderate summer air from various persons, 55, 9, 1,082. Warmth of the air at the time when this warmth of the hand was observed, 59, 9, 1160. Melting butter, 61, 10, 12, and 1. Melting tallow, 64, 2, 1246. Congealing wax, 67, 3, 306. A little piece of wax weighing 10 to 12 grains has completely melted, 58, 5, 1,835. Water that appears to be tempered. Water that appears to be 73, 0, 14,017. Boiling water, 54, 0. Tempered air. On this table, it should be noted that all the degrees of the air thermometer depend on the first, because it was taken as the basis. What Amundsen calls tempered air is that of the cellar of the Paris Observatory, which from winter to summer almost does not change. It seems in summer cool and winter warm to us. And this shows that what we, according to our sensation, call tempered or moderate warmth is noticeably according to the changes with the season. This is also how one must understand what Amundsen calls tempered water of his two reference points, the melting and the frozen wax. The first is more reliable, for once the wax has melted, the finer degrees of heat can no longer be recognized by mere sight. But when it cools again, the heat at which it loses its glossy surface and transparency is a very definite degree of warmth. For this one must take a piece of wax about the size of a lens, because larger pieces lose their transparency only on the outside and not throughout. I carried out the experiment with white and yellow wax in winter and summer, and on the same thermometer, I always found the same degree of warmth. Yellow wax is better suited for use because when it cools, it shows the color again. The experiment with melting butter and tallow is somewhat uncertain. Tallow does not lose its glossy surface until it has already been congealed for some time and has noticeably cooled. Thus, the determination of the true degree of warmth remains uncertain, and so does the beginning of the butter's congealing. As for the degree of warmth of healthy people, Amundsen carried out the experiment with several persons, and besides the thermometer reading, also noted the number of pulse beats in 1 minute. He found these to vary from 56 to 80 without the differences increasing with warmth. Amonton's thermometer. Air thermometer. Pulse beats 58 degree. 2 1.129. 68 58 degree. 5 1.13 60. 70 80 58 degree 7. 1.038 56. 74 58 degree 9. Fewer observations have been made with Amonton's thermometers, and in general with air thermometers, than with other thermometers. Trucquess of Spadaro used such an instrument in weather observations in the years 1720-1023, which he made known in the English Philosophical Transactions, No. 281. In his thermometer, 1070 is the degree of freezing and 1510 the degree of boiling water. These degrees represent the expansion of the air by heat at equal pressure, or the Drebs thermometer, together with its variations. The force of heat, when the density is the same, is therefore proportional to the degrees of the Arga thermometer, which I shall henceforth use constantly, so that the degree of boiling water becomes 1518, 1518. Trucchius gives the following mean degrees, namely not the extreme ones, but the averages of all, for each month of the 4 years 1720, 1723, the average of these 4 years. Trucchius, January 1083. Trucchius, in his weather observations continued for 40 years, used an Amonton's thermometer, in which he determined the pressure in London inches and their decimal parts. He found it to be 47.3 inches for freezing water and 63.1 for boiling water, consequently exactly 1/3 greater. This, however, seems to be too little. But since the author does not speak clearly enough, or Poligny, for the sake of brevity, assume the ratio of 3 to 4. It may remain set down here in this way. The pressure of 47.3 inches for the cold of freezing water is already sufficient to reduce his thermometer to the corresponding air thermometer, if only the scale was large enough to be able to set the degrees proportional to the pressure. 76, 77. His observations have already been well enough used by Mr. Toldo in Padua. I content myself with adding the following degrees. Poligny erga thermometer, 47.3, 1056. Mean midday warmth at Padua, 52.54. The greatest heat and the greatest cold observed over 40 years are very moderate, because the thermometer stands in a room, and therefore cannot indicate the condition of the outside air. I shall now state more fully how I carried out the graduation and calculation of the thermometer mentioned above, P72. For this I used Berlin weights and the Paris measure, because I also used the latter for the barometer. The glass had a tube length of 291 lines and a bulb 13 lines in diameter. It weighed 364 grains. When I filled the bulb and the tube up to a marked point G with mercury, I found the weight to be 2,318 grains, of which, after subtracting the glass, 1954 grains remained for the mercury. When I then filled the tube up to the beginning, it weighed 2,678 grains in all. Consequently, after subtracting the weight of the glass, the mercury weighed 2,314 grains. Therefore, the amount in the tube from G to D is 2,314 minus 1954. That is 360 grains. In this way, the ratio of the volumes becomes known, and the volumes themselves are expressed in such parts that each is as large as 1 grain of heavy mercury. AE2. In order further to see whether the tube was equally wide, and, if necessary, to take the inequality into account in the calculation, I let some mercury into the tube and found that its length was not everywhere the same. It began at 21.8 lines from D and extended to 73.9 lines. From there, it extended to 124.2 lines. Then from there to 172.8 lines, and then from there to 219.2 lines. Finally to 263.6 lines. The lengths are therefore 73.9 minus 21.8 equals 52.124.2 minus 73.9 equals 50.3, 172.8 minus 124.4. This inequality had to be taken into account in the calculation. The weight of the mercury was 62.6 grains. After I had filled the instrument as described above, Pn. 72. with water which, on 31 January 1776, at a barometer height of 28 inches 5 lines, that is 341 lines, I took for the calculation the height EH 11 inches as the basis, in order from there to determine the irregularities in the width of the tube. This point lay 9 inches 3 lines below D. I then weighed the glass with the mercury contained in it, and found its weight to be 1283 grains. Subtracting the weight of the glass, 919 grains remained for the mercury. Now it followed, from the measurements given above P42, that in the part of the tube GH there were 208 grains of mercury. Consequently, the part BG contained 919 211 grains, namely when the mercury reached exactly to point HK. Since the space of the bulb in the part BE contains 1954 grains, there remain 1954 T711 grains for the space, a B, which the air occupies when it is shut up in the bulb. This space now becomes larger when the mercury rises above point H, and from the first measurement cited, P82, I found that if HC is set equal to Y inches, the space of the air amounts to EG43, 61 inches. If the barometer height is by inches, then the total pressure is about 11 inches. Consequently, if we take them as a coefficient and denote by C the degree of the air thermometer, we have mmH beats. This expression differs from the previous one, P75, in that here I express the space of the air not by lengths, but by grains of mercury, and at the same time take into account the unequal width of the tube. This, however, changes only the value of the coefficient m, which must be determined by an actual experiment. Since in this thermometer, I also wish to take all the smaller circumstances into consideration, I had to pay particular attention to the expansion of the mercury. According to Delisle and other experiments, from freezing to boiling water, it amounts to 3 degrees on 2000. It has a double effect on this thermometer. First, in higher warmth, that the mercury is lighter, therefore its pressure is by no means proportional to the height EC. The same is true of the barometer. This makes a reduction necessary. Let C be the heat of boiling water in degrees of the air thermometer. One must also take the expansion that the mercury has in freezing water, and for that reason its expansion in every other degree of heat C in freezing water will be as 1 C 200 to 1 to 1. Accordingly, the height EC must be divided by 1 through 200, C 1000, C 1000 mercury presses by that much less. In the same way, the barometer height must be reduced. And since the circumstance occurs that these two instruments are not always at the same temperature, one easily sees that. Then the degree of heat C must be determined separately for each. If, for example, the heat of the barometer is Y, then in the formula, P84, the expression Y11Y is transformed into the following. 200C, 200,000, 200C through AB, 203,000, 203,000, 200C, 200C. This is the first reduction, 86. The other is based on the fact that through the expansion of the mercury, the volume of the air can no longer be determined simply by Y, but must be increased by as much as the mercury's expansion amounts to. Now, the entire volume of the mercury is 919 grains. But this has been determined in a room whose warmth was moderate and amounted to 1040 grains of the air thermometer. Therefore, in order to bring it to the degree of freezing water, it must be divided by 1 through 200, 340, see, 1 cent. And thus, for each degree of warmth, Ci, it will amount to GG 919 NC Cedo to left one, Afrax 3 200, CC dot Afrac 919, Ichi Cedo Afrac 3 while 200 Dido T Afrac C on 40 CI 84 1243 Afrac 61 not 44 on the next 10 in order to obtain the true volume of the air in the thermometer. It should also be noted that since the thermometer is placed with its bulb in warm water up to above the bulb, the mercury in BBFEs and the lower part of the tube receives a different degree of warmth than what rises above the water, and this must accordingly be taken into account. I now report 2 experiments with this thermometer made on the 31st of January 1776. The severe cold at that time meant that I had the freezing point of water exactly in a closed, unheated room. In this, I placed the thermometer in water that was beginning to form a crust of ice. The mercury rose, 1 of Freck 7.8, lines above point. The barometer hung in a room where the warmth was 1040 degrees of the air thermometer and stood at 28 inches 5 lines. Consequently, each 28.407 inches and 1040 Sichuan. The expression 11 is transformed as follows. The volume of the air is 104.7 to the factor into H 200. C 128 they give 1000 mm.1083 28.467 13.467 13.4667 13.467. This is therefore the first equation between M and C only 8 immediately afterward. I brought the thermometer into the room where the barometer was and placed it in boiling water. The mercury rose 9 2/3 inches above point H, so that Chua was therefore 9.7083 inches. Since here CSC and BI 28.667 on 40, the second equation is found from these values. Metchi 77, 47, 42, 7, 42, 7. From these two equations, one now finds the value Chi 1000, 1354, which is therefore the degree of boiling water at a barometer height of 28 inches 5 lines. Without considering the reductions arising from the mercury, I find CT 75. Now, since the glass in boiling water must also have expanded somewhat, whereby partly more mercury was contained in the tube, and the space for the air at the top became larger, the value 1105 ought to be closer to the true one than the value 1354. I will therefore assume the round number CKT in 70. Amintons found 1417, 78, Truscott 1411, Delancey only 1333, 80. My determination therefore holds fairly well to the middle. One had previously assumed that boiling water expands the air by 1/3, but that was for air that was not at the coldness of freezing water, but was approximately temperate. I have, moreover, described this thermometer here more fully because I have used it for other observations. For common observations, I have attached a movable step scale to it, which can be shifted along it as the changes of the barometer require. 90. The glass shown in the third figure can also be used as a thermometer in another way. The easiest way is to do it as follows. If above at the bulb at A, there is still a small tube. The tube is then fused shut at D, and the glass is filled with mercury under pressure, as one would do if it were to become a barometer. The tube must also have the required height. After that, the tube is fused shut at A, and in this way the air in the air is held in equilibrium by the mercury column, EC. The pressure of the outside air is thereby removed because in CD there is empty space. As in the preceding calculations, section 83, letter F beats here. This can therefore also be applied to this kind of air thermometers. I had such an instrument made for myself in 1754 in order to compare its behavior with that of other thermometers. For the time being, I have only the scale and the observations made with it. Section 91. Wolf, in his useful experiments, also describes another kind of air thermometer. It consists solely of a thermometer glass into whose tube a little mercury is introduced. If, as in the first figure, the vessel B remains, and one leaves in the tube only a small quantity of mercury C, then it represents such a thermometer. One can lay it down or set it upright. When it lies, the inner air is always in equilibrium with the pressure of the outer air, and thus the warmth is proportional only to this pressure, that is, to the volume a C, which the air takes up each time. But if one sets it so that the bulb is at the top, then from the barometer height, one must subtract the height of the column CC. On the other hand, one must add it when the bulb comes to stand below. The mercury then moves back and forth, so to speak, in jumps, because each time an overpressure is required to overcome the adhesion. The mercury also easily breaks up, so that individual little pieces of it remain lying in the tube, or when it is set upright, fall down. Section 92. Among the various ways of determining the warmth of bodies by means of the expansion of air, or of comparing them with one another, there also belongs what Mr. Robin presented in his treatise on the air pump. He had an iron tube closed at one end, and with a very small opening at the other, made red hot in a forge fire. And in this way, the air in the tube was thinned so much that it could be thinned in the same degree as in the air pump. Before he took it out of the fire, he stopped up the opening with an iron wire and then let it cool in water without any water or vein able to enter. He then pulled the wire out afterward out of the water, and the water filled the whole space that the remaining air had been occupying. In 3 trials, he found that 610,595 and 600 grains of water had entered. The entire tube, however, holds 796 grains of water. Thus, there was still so much air left in it as would displace 186, 201, and 196 grains of water. If one now takes only the approximate value, namely 1/4, or if one takes the mean of the 3 trials, 194 parts out of 796, then the air has therefore expanded in the white glowing iron in proportion 194 to 796. That is, as 1 to 4.01. Now, Robin does not say what the warmth of the air was at that time, nor in what season he carried out the experiment. Since the water did not freeze, it can hardly have been in the severest winter, yet probably not in the greatest heat of summer either. If, however, we set the degree at 1050, which according to Duluth's observations, p. 79, I have assumed for the thermometer of M. Amonton's, it follows that the degree of white glowing iron may be set at 4.01 Ho. 1050 Chi 410 on the air thermometer. By this, then, the greatest heat of the fire is determined, so that not only white glowing, but completely melting and sharply flowing, iron may probably be set at 5,000 first part. Thermometers made with other liquid substances, first section. Preliminary considerations. 93. If, in the strict sense of the word, one understands by a thermometer an instrument that indicates the degree of heat directly and exactly, then the Drebel thermometer cannot properly be called a thermometer, because in it the pressure of the external air must be taken into account. It therefore does not show the degree of heat immediately. Rather, this must first be found by calculation. The method of making this calculation would still have to be discovered. It could, however, be found from Mariotta's law. Yet for that one would need to know the measure of the elasticity of the air, without having to assume how it must be altered by changes in heat. Amonton's did this and found it not difficult. The Drebel thermometer had already been rejected long before as far too imperfect to be brought into use. Amonton's, in the end, retained it even for his own purposes, only insofar as it could serve to compare the Florentine thermometers with it, and make them agree with it. 94. This was now, to be sure, a detour one did not wish to take. In the previous century, too, one had already adopted fixed degrees of heat that could now be used as reference points, and the thermometers could be divided accordingly. At first, one contented oneself with the admittedly rather indefinite degrees of summer warmth and winter cold, which were taken as the outermost points for thermometers set up for weather observations, and then added something further so that the scale would not be too short and the tubes would not turn out too narrow. See, 2632, the Florentine Academy did not go beyond this. I also find the first traces of a more definite division in Dalance's treatise on the barometer, thermometer, and noceometer. He says there, all thermometers could be made to agree if one did the following. Years ago, he wanted to make use of it. This procedure is twofold. In the first, he lets the air cool until it begins to freeze, and he notes the degree of warmth at which butter begins to melt. This degree is to be marked on the thermometer, and the interval between them is to be divided into 20 parts, 10 of which are to be counted upward from the middle, and the other 10 downward. The middle is then taken as the degree of moderate warmth. At depths of 20 degrees, one then has, above and below, the summer heat and the winter cold. Here, the degree at which butter melts is somewhat uncertain. According to Amonton's, it would have to be the 180th degree of the air thermometer, P78. This is too much. Amonton seems to have assumed a degree at which butter scarcely melts. And this is far above summer heat, since even according to Amonton's, the greatest heat he observed in the shade reaches only 141 degrees. I find that melted butter begins to boil at 106 degrees. And Daylanch says that in summer, a piece of butter placed on the thermometer can melt without lying directly in the sun. He therefore unquestionably shifts the lowest degree of warmth at which butter can melt. His division can therefore be compared with the air thermometer as follows. Day-lunch D15. Air thermometer 132.5. Summer heat 10 to 179.5. Warm 0, 1079.5. Warm 10, 1000, cold enough to freeze. 15, 973.5. Winter cold. Moderate warmth thus falls at the 1053rd degree. Not much is lacking. One also sees from the observations of Crucius, p. 79, that this degree is very close to the average degree of warmth in May and in the autumn month, 95. The other way of proceeding, which Dalens gives and which he himself regards as different from the former, is based first on the degree of temporal preliminary observations in deep enclosed cellars. Second, the degree of cold of the crushed ice mixed with common salt. For this latter degree, it would have had to be stated how much salt was to be used. I find that if snow and salt are mixed in equal parts, the mixture reaches 918 degrees on the thermometer. The snow may already have had this cold, or it may not. The only difference is that if the snow is already as cold in itself as it was on 27 January 1776, it does not melt when mixed with this. This mixture, moreover, is all the more effective and all the more rapid the less cold the snow is. But Dalens did not have so severe a degree of cold in mind. The temperature of deep cellars reaches 1054 degrees. Now, 1054 minus 918 equals 136. And Dalens wants one to count 136 degrees upward from 1054. That brings one to 1,190 degrees. This goes far beyond summer heat, even in the sun. Besides, Dalens what is meant by this degree. And so it seems he meant only to indicate a division that is by no means small. Yet it would be enough to say that one can determine the degree of frost by observation and mark it on the scale. 96. I have the statement from 1688, presumably the first of Dalens's treatise. 5 years later, he filled his profession with the determination of the degrees of warmth and of the expansion of air, of spirit of wine, and of mercury. 34. But he left it at the bare statement. There were still too many defects in thermometers, and even in the present century, it was a doctrine in aerometry that for this reason thermometers should be called merely thermoscopes. People asked whether the actual degrees of warmth were proportional to the degrees of expansion. And even if this were to be assumed, there was still the question at what degree one ought to begin counting. This question, in the case of spirit of wine thermometers, to which people were already quite accustomed, was indeed very important. Carlo Renaldini proposed, to this end, to take boiling and freezing water as fixed points, and then to proceed by equal steps in order to obtain degrees of warmth continuing in the same way, which could then be marked on the mixture placed in the spirit thermometer. Renaldini did not carry this out himself, and on the contrary, found an opponent in Wolff, who found in his proposal a help for thermometers that did not lie in the matter itself. Renaldini says one should count 1, 2, 3, free. Freezing water at 11, 10, 9, preliminary considerations. If one mixes 1 part cold with 11 equal parts warm, one will obtain 12 equal degrees of warmth. Wolff, however, says that these degrees will not be equal in size, but will be 1, 2, 3, and so on, up to 11. This would occur if, for example, from 1 part warm water, one could remove the excess of its warmth and transfer it into the 11 parts of cold water. But that is not possible. Therefore, Renaldini mixes 1 part warm water with 11 parts cold. The mixture then plainly consists of 12 parts, and the warmth is distributed among them. It is therefore in each part 1/12 and not 1/11, as Wolff claimed. I also know that Borhav-Martin, Richmond, Lesage de Luc, and others did not approve of Wolff's judgment, but rather sided with the experiments. From this, it became clear that Renaldini's proposal deserved to be received more favorably, even though neither a geometrical exactness is thereby achieved, nor can the degree of absolute cold be determined by it, in 97. With the beginning of the present century, thermometers began to have a better fate, as I have already indicated in the preceding main section. At the same time, Newton also gave his observations on various definite degrees of heat in the Philosophical Transactions, though not under his own name. At that time, one was also occupied with thermometers in Denmark. as Zanov reports in his Curiosities of Nature and Art. He says that one hung them outside the window. Zanov also found the record of the degrees of the thermometer observed by Fahrenheit during the cold winter of 1709. In 1713, Fahrenheit went away from Danzig and bequeathed to Wolf 2 of his thermometers, which always agreed with Wolf's measurements. Fahrenheit found the best reception in Holland and England, and especially in Boerhaave, a good advocate. He also began to fill his thermometers with mercury and to set the degree of boiling water at 212. Yet he nevertheless found that this degree varies with the state of the barometer. The question whether the degrees of expansion are proportional to the degrees of heat quite inevitably gave rise to another, namely, whether at equal degrees of heat the degrees of expansion in different materials remain proportional to one another. This question could now undoubtedly be determined by experiments. Fahrenheit would have been able to do so if he preliminary considerations. A thermometer that agreed when filled with alcohol and with mercury could be made. The attempt failed. At first, I thought the fault lay in the difference of the glass, but soon I had to admit another cause. The true reason should really be this, that in fluids, which are close to both boiling and freezing, their expansion tends to become irregular, and that when they are enclosed, their expansion likewise proceeds according to different laws than if they could expand entirely freely. 99. Reaumur is, as far as I know, the first who drew attention to this. Yet he gave alcohol an advantage over mercury in such a way that, although he did not entirely omit a more exact comparison, he at least did not make it known. This was later undertaken by Michel Ducrest. He improved thermometers of alcohol, oil, and mercury in order to compare their behavior with one another. He found differences among them that are by no means negligible. Before him, Brander, Deluc, Strohmeyer, and others had also found. These inequalities only increased the doubt that had already existed, namely, whether the degrees of heat advance in equal steps with the expansion of bodies or not. For since the expansion of different materials does not remain proportional to one another, it cannot so easily be accepted as the measure of warmth. The question therefore arises, which material should be taken as the nearest, or by whose expansion the degree of warmth could be determined most reliably? This question was precisely the occasion for which Lesage, and after him Deluc, proposed the thermometer of Rinaldi, 96, again, and especially the latter set up very detailed experiments on the matter. In all this, one seems to have forgotten, or at least not to have considered, that what one was seeking was already present in the Amundsen's thermometer. With thermometers, one wanted to attach such scale divisions that would indicate not merely the degree of expansion, but the actual degree of warmth. One should therefore have examined more closely what one meant by degree of warmth, for the vagueness in this expression is precisely what made it, so that one neither knew what one already had, nor what one still sought. In the degree of warmth, there occur, first, the quantity, second, the density, third, the force of the particles of fire, and these three things differ so greatly in different bodies that one must take special account of each. Preliminary Reflections, Section 101. By now people were accustomed to judging that two bodies have the same degree of warmth when the thermometer shows the same degree of expansion in both. But in making this judgment, one could understand the warmth as nothing other than the force of warmth. That is the force which is greater in warmer bodies and smaller in colder ones, and which therefore causes warmth to pass from the former into the latter until complete equilibrium has been reached, so that both are found equally warm. Now the measure of this force in the air has been very well and correctly determined with the help of Amundsen's gas thermometer, section 49, namely the true measure of the degrees of warmth, section 102. However, earlier, section 100, I mentioned, besides the force of the particles of fire, also their quantity and density. And in the preceding main chapter, I likewise restricted myself to the concept of the force of warmth in air of equal density, section 53, because in fact, Amundsen's gas gives only the true measure of this force. But since the force of warmth in air is directed according to its density, it follows that the same warmth has more force in denser air than in thinner. And so there is no doubt that in other bodies, too, the same warmth may have quite different forces. One must only note that this force is not determined by the bodies themselves, and therefore cannot occur without detriment to the equilibrium mentioned above, section 1. The force of warmth within the bodies themselves can be very different from the force it exerts against the surrounding and contacting bodies. Yet this equilibrium requires that the two increase and decrease in proportion when they change. One finds in Newton's Principia that he had already before the year 1686 given thought to determining degrees of warmth. On the occasion of the comet of 1680, he found by experience that the heat of boiling water is 3 times greater than summer heat, and he conjectured that the heat of glowing iron is 3 to 4 times greater than that of boiling water. From this, it follows that Newton must have assumed the heat of boiling water to be a fairly definite degree, and I also do not see why he should have thought otherwise. It had long been known that boiling water does not have the heat required for melting tin and lead, and therefore that boiling water cannot be regarded as a certain degree of warmth. Newton takes this as known in advance, yet at the same time he considers determining the degree itself. By contrast, Halley in 1692 and Amatons in 1702 concluded far too hastily from this that boiling water becomes warm only up to a certain degree, and that therefore it could be used to calibrate thermometers. And yet later it was found with sufficient certainty that this degree is not entirely unchangeable, but varies with the weight of the air. The variation, however, is small. Newton says nothing further at the place mentioned from which one could judge how he wished his degrees to be understood. But from the relationship of these degrees to one another, it may be supposed that he set the 0 degree of warmth at the point where, according to our sensation, it begins to feel cold. If we set, as Polanyi does, the summer warmth at 120, and as in another place, the degree of boiling water at 1370, then the difference is 1370 minus 120. That is 250. Subtracting this from 120 gives the 995th degree as that at which Newton may have set 0. Since this degree is only slightly lower than that of freezing water, it suggests that Newton actually took this degree as his basis. In this way, the following comparison arises. Newton's thermometer, according to Lutwell, Newton's thermometer 0, 1000, freezing water 11123 and 1/3, summer warmth 33070, boiling water 9 2000, blowing water. This degree for glowing iron is too low, see 92. Newton gives it only under the condition that he guessed correctly. Later, he found it to be considerably higher, 105. In the month of April, in the Philosophical Transactions of 1701, Newton, without naming himself, presented a scale of various degrees of heat and cold, although his method is probably imperfect. For the degrees that are lower than those produced by the heat of molten tin, he used a thermometer by Lutwell. He took the cold of melting snow as the starting point, and from it proceeded to the degrees of heat by dividing the volume of Lutwell's thermometer into 10,000 parts. Thus, boiling water expanded Lutwell's instrument to 10,725 parts, and molten tin, when it began to lose its stiffness, expanded it to 11,516 parts. This way of making and graduating a thermometer could have been improved. But Newton himself departed from it. He took the word warmth in the narrower sense, see 17. And since he presumably found the so-called temperate warmth too indefinite, he took the cold of freezing water as the first degree, or the beginning of cold, and at the same time as the beginning of warmth. He then regarded the outer warmth of the human body as the truly positive degree of warmth, divided it into 12 equal parts, and thus divided his thermometer. The degree of boiling water was, according to this division, 34. His observations made with Lutwell's thermometer were as follows. Newton's thermometer, according to Lindahl, freezing water, melting snow, warmth of spring and autumn, summer warmth, heat of the body, also for hatching eggs, water in which one can keep one's hand for a long time, water too warm for the hand, water in which melted wax begins to become opaque, water in which wax has not yet turned cloudy, strongly boiled water, a fusible alloy of 5 parts bismuth, 3 parts tin, and 2 parts lead remains almost liquid in it. He in which an alloy of 5 parts bismuth, 4 parts tin, and 1 part lead melts. Melting fusible alloy of equal parts tin and bismuth. Melting solder of 2 parts tin and 1 part bismuth, likewise of 3 parts tin and 2 parts lead. hard solder of 5 parts tin and 2 parts bismuth, likewise of equal parts tin and bismuth, melting solder of 1 part bismuth and 8 parts tin, hard tin. Melting tin. The degrees given for spring and summer warmth are in themselves rather indefinite, and the heat required to keep one's hand in water varies greatly with habit, and especially with the season. The warmth needed for hatching eggs may also differ somewhat in different birds. In general, however, it will be somewhat greater than the warmth of the hand indicated. Newton gives 34 degrees for strongly boiling and very fluid wax. Amundsen's found it somewhat higher, yet the difference is reduced if we subtract Amundsen's degree for the heat of boiling water, which he sets at 73 inches, and 1417 degrees of the air thermometer, by so much that it amounts to only 1370 degrees. CPP 7889. On closer reading, the circumstance that Newton did not make these degrees known under his own name gave Amundsen's occasion to attack this unnamed third part, and to censure the observations as much as possible, indeed more than was proper, and to set experiments against experiments. Newton had made things too easy for Cartes, and at that time Cartes was in Paris, where Aristotle was the idol of the scholastics. It is also still the case that the constant degree of heat of boiling water, which Amundsen in the year 1702 presented as his invention and as something entirely new, was no longer new in England. Amundsen, moreover, could very well have known nothing of earlier remarks, and his thermometer was such an occasion for making experiments that Amundsen's could hardly have let it pass unused. He could therefore indeed carry out, with his thermometer, the experiment on the heat of boiling water, an experiment which at that time was believed could not be undertaken with the Florentine thermometers because alcohol boils sooner than water. Newton was thus chiefly reproached for believing he had found the 0 degree of heat at freezing water, and from there counting the remaining degrees. But this reproach really meant nothing more than that Newton had not determined the degree of absolute cold. For besides, Newton speaks of degrees of cold in such a way that he counts them downward from the 0 of his thermometer. In this respect, the reproach therefore goes beyond a mere misunderstanding. Newton called warm only what we ourselves feel as warm. Amundsen's, on the other hand, called warm everything that could still be made colder. In this, Amundsen's therefore went further, and with good success. Amundsen's further insists strongly that his experiments and observations on spring and summer warmth, and on the warmth of the human body, differ from Newton's. He could always be content to say that these degrees are not always the same. Newton himself does not claim otherwise. He set winter cold at 0, 1, 2, spring at 3, 4, summer warmth at 4, 5, 6, 6. And since from freezing to boiling water he counts only 34 degrees, one sees that his degrees are very large, and that Newton gives them only in a rough way. Newton further contented himself not only with to indicate the degree shown by the thermometer when one holds it in the hand or against the body, he also wanted to know how it behaves when the hand is warm with warmth. Here he made a greater advance. Amundsen's, by contrast, did not carry out the experiment with hot or with warm water, but only with lukewarm water, which seemed to him neither warm nor cold. And since his thermometer did not reach beyond the degree of boiling water, although it might well have been able to go farther, Amundsen thought of other experiments by which he could also test the higher degrees of heat that Newton had indicated. But in this Amundsen fell far behind Newton. He imitated Newton where he could not follow him. Third section, Fahrenheit, thermometer 110. Fahrenheit appeared at about the same time as Amundsen's and Newton, although his name did not become better known until after 1715. This circumstance, and especially the fact that he did not wish to make the beginnings of his inventions known, has spread some obscurity over the origin of the history of his thermometers. Wolff relates in the Acta Eruditorum of 1714 scarcely anything more than that the 2 thermometers he received from Fahrenheit agreed well with one another. This was all the more undisturbed at that time because they were mounted side by side on a board and had a common scale. And this was in itself not necessary, since greater expansions can be indicated by larger degrees. But it did show, especially in the rapid changes of warmth, the uniformity of the movement of both thermometers, and at the same time served to keep them hidden. Wolff also did not discover the invention because he sought it in the salts, with which, in his opinion, the movement of the more strongly expanding spirit of wine must have been weakened. Wolff otherwise describes both thermometers and the common scale very precisely. Meanwhile, this common scale was neither the first nor the last that Fahrenheit used, although he retained the degrees that had been laid down as the basis even through these changes, 111. These degrees are 1. That of snow or crushed ice mixed with sal ammoniac. 2. That of the warmth of the human body, Fahrenheit's thermometer. At first, he divided the interval into 180 equal parts, of which he counted 90 upward, and just as many downward, perhaps also leaving about 10 degrees of room above and below, so as to have 100 degrees of heat and just as many degrees of cold. This is the division of the above-mentioned thermometer invented by Danzig, CP 97. Fahrenheit made such a thermometer in the year 1712 when he was in Berlin, and he shared it with one of the learned societies of that time, the Royal Society of Sciences, which has long since ceased to exist. According to what Grisha relates in the 6th volume of the Miscellanea Beryllentia, the young mathematician Arnsdorf learned something about Fahrenheit's arrangement of the scale there. Fahrenheit also made the scale finer and gave his thermometers a more convenient size, 112. This altered scale is the one that Fahrenheit then used on his thermometers. Instead of counting 2, 4, and 90 degrees, he now counted 24, and indeed in a continuous sequence from bottom to top. And since these degrees were still noticeably large, he also marked quarter divisions on each one. Finally, when experience had prompted him to take these quarters as whole units, he set 96 degrees between the frost of ice and the warmth of the human body. He also used the same division for the boiling point of mercury. And for his chemical experiments, he sought to extend the scale up to the heat of boiling mercury, which occurred at about this degree in Gooden's measurements, 113. Fahrenheit remained with this last division, and it is still customary long after his death. Boerhaave and Muschenbroek used it throughout, and moreover, a great many observations have been published that are given in Fahrenheit degrees. It is also generally assumed that these thermometers are filled with mercury, for Fahrenheit had abandoned the opening that he had made with those filled with spirit of wine, CP 98, and after him Prins in Amsterdam and other craftsmen followed suit by using mercury. Besides, Boerhaave and Fahrenheit had already found it more convenient to take the degree of freezing and of boiling water as the basis. But they decided not to confuse the degrees, and therefore set the point of freezing water at the 32nd, and that of boiling at the 212. Yet with the latter reservation that it yields somewhat to changes in barometric height. Martin found the degree of water beginning to melt or thawing at the 142nd degree, and the temperature of the cellar of the Paris Observatory was found to be at the 53rd or 54th degree. Good alcohol boils at the 175th degree, poorer alcohol at the 185th. These degrees may suffice for a preliminary comparison with the air thermometer, if we only assume that 180 degrees on the seasonal thermometer correspond to 370 on the air thermometer. Seasonal thermometer, air thermometer, 34. Melting ice, freezing water, 32, 54, 1045. Deep cellar warmth, 96, the 132. Warmth of the blood, 142 with 26. Boiling pitch, 212, 1370. Boiling water, 600, 2,168. Boiling mercury, 4th section. The Delisle thermometer and some other mercury thermometers. According to Reaumur, 99, Delisle in Petersburg also set out to give the thermometer a more convenient simplicity, and was especially concerned that one could manage with a single fixed point lying at the base. He chose mercury for this, and found that if its volume at the degree of boiling water is divided into 10,000 parts, then at freezing water it will amount to only 9,050. That is 150 degrees downward from the top. 115. This thermometer was much used in Russia. The fixed point was to be that of boiling water. But since Fahrenheit and after him several others found that boiling water at lower baro, so that it also becomes less warm on mountains than when the barometer stands high. Therefore, Delisle set the fixed point at the freezing point 150 degrees away, so that a reduction is made with it, and so that, as with other thermometers, a definite barometer height must be fixed. Besides, it is unnecessary for me to dwell longer here on Delisle's thermometer. It is a mercury thermometer like Fahrenheit's, and differs from it only in the way it is divided and arranged. And since the Swedish thermometers introduced by Celsius are also mercury thermometers, it is likewise enough here if I note that Celsius set the freezing point at 0 degrees and the boiling point at 1. Christian is said to have been the first to adopt this division. Finally, since some have begun to make Reaumur thermometers with mercury, these two belong here. One sets 80 degrees between the same 2 points. This gives the following comparison. Mercury thermometers, Fahrenheit 32, 212, difference 180, Delisle 150. Swedish Celsius 0, 150. Swedish Celsius 0, 100 according to Reaumur 0. Boiling water, difference, or parts of the interval, 5th section. Thermometers with spirit of wine, 116. In the comparisons given so far, I have assumed the expansion of materials by heat to be proportional. The materials were air, linseed oil, and mercury, and in fact they differ little from one another. I have also already remarked p. 98. That spirit of wine, especially when it is enclosed, makes an exception, and that it differs from all watery materials. Reaumur knew this, and nevertheless gave spirit of wine thermometers the preference. He had large bulbs made on his thermometers, 2 to 3 inches in diameter, and made them. Thus, it became all the less sensitive and slower in its movement. He chose the degree of freezing water or melting ice and that of boiling water as the basis of the division. And since he extended his tube from 1,000 to 180, he divided the interval into 80 parts, 117. All this seemed very well thought out, and many who preferred to pay Monsieur de Reaumur a compliment rather than examine the matter itself found his 2 treatises on it excellent. People are not all so credulous. Just as the Paris standard of weights, alongside the old Châtelet standard, was after some years exchanged for another that was supposed to be more accurate. So little by little, one began to hear of quite unbelievable degrees of heat being observed in various places with Reaumur's thermometer, nor would the comparison of these with mercury thermometer come out. Soon Michele du Crest appeared and accused Reaumur's thermometer of not being able to reach the degrees laid down in his scale, and in particular asserted that his degree of boiling water was nothing less than that, but only the degree of boiling spirit of wine of medium strength. Martin, in his treatises on thermometers and degrees of heat, raised similar objections and received the approval of Monsieur de Meuron. And quite recently, Herr de Luc, in his modifications of the atmosphere, has lingered long over the Reaumur thermometer and taken the trouble to construct a thermometer divided according to Reaumur's instructions in order to investigate the error more closely. Above all, it turned out that what Reaumur gave as 80 degrees in fact amounted on his thermometer 100, even 110 degrees, and that they agreed with one another no better than that, 118. Michele du Crest finally obtained the degree of boiling water on the spirit thermometer by first warming the tube, or the bulb, before placing it in boiling water. Perhaps, following the instruction of the Paris boiling test, he knew that enclosed water is capable of greater heat and expansion, and so he could conclude that the spirit of wine in the thermometer would have to be completely enclosed if it was to withstand the heat of boiling water. The result confirmed his suspicion, and so he now set about comparing the movement of his thermometer with that of linseed oil and myrrh. He found that these two latter materials differ little from one another, but differ greatly from alcohol. Others have found the same, and among them, de Luc and Strohmeyer have made their experiments known. The experiments proceed by steps of 10 degrees, and are lengthy and troublesome. It is also clear in itself that when enclosed alcohol is warmed more than it would be in an open vessel, one may say it is in a constrained state, and therefore the degrees of its expansion must follow a quite different law. 119. In the year 1765, I had 2 mercury thermometers made, and on them I divided the interval from freezing to boiling water into 80 equal parts. Beside these, I hung several alcohol thermometers, and by comparing their rise with those, I divided these as well, so that they agreed with one another at the ordinary degrees of air warmth. The mercury thermometers were soon ruined by accidents and experiments, and so there remained only those with alcohol, with which I continued to make observations and experiments. I also always tried to keep a supply of them, so that if some were broken, I would still have others left by which I could divide new ones. For I had already found in 1751, through experiments, that thermometers are made to agree most reliably when one hangs them side by side, and in this way marks on them the same degrees of heat and cold, 120. With these thermometers, I found the degree at which wax begins to boil and to melt to be between 57 and 53, in winter and summer alike, with white and yellow wax, without dip. The warmth of the body, according to the difference of day and season, lay between 30 and 32 degrees. I had already set freezing water itself at 0, and in snow mixed with an equal amount of salt, I found the 15th to 16th degree below 0. From this, I derived the following comparison. From this, it is easy to see that these differences are not proportional to one another, and that for freezing water, or for the 212 Fahrenheit degree, I would obtain two quite different degrees for the expansion of alcohol, 127. I also found without difficulty that if the Fahrenheit scale from freezing to boiling water is set at 180 degrees, the first difference gives the proportion 65-32. Now, 89 differs far too much from 104 for the difference to be attributable merely to the uncertainty of the observed degrees. I have divided the alcohol thermometers, as already mentioned, so that they agree with the mercury thermometers at the ordinary degrees of the weather, and thus the degree at boiling water ought to have been the same. But it appears here that the progression does not proceed uniformly. Rather, the expansion of alcohol increases more strongly with increasing warmth than that of mercury. Finally, in January 1776, I had an experiment undertaken. One of the alcohol thermometers was held over the steam of boiling water, and after it had already become fairly warm, I placed it completely in. It rose there to 102 degrees. I had meanwhile made another thermometer of mercury, and this, together with the air thermometer described above, 81 to 89, I compared both in boiling water and at lower temperatures, wine spirit thermometer, degrees of heat, and even in the severe cold of that time, in order to see how wine spirit, mercury, and air differ or agree in their motion. Air and mercury advanced almost exactly in equal steps, but with wine spirit, there was a very noticeable difference, 123. The comparison of mercury and wine spirit was as follows. Mercury, wine spirit, west 15.5 before the window. 0 freezing water, 29.7, 32 warmth of the body in bed, 57 melting wax 80, 102.6 boiling water. This comparison was sufficient, by means of the known methods of interpolation, to find an equation that gives all the degrees lying between the two observed extremes with adequate accuracy. And the equation was all the easier to find because both thermometers have the same degree at the freezing point. If, therefore, starting from this point and reckoning upward, the degrees of mercury are denoted by Q and those of wine spirit by W, then the observation in boiling water already yields the following equation, Q, 102.6, 80 Q. Instead of this equation, properly speaking, an entire series should be assumed. But since I wanted to stop at 2 terms, the question arose whether it would not be better to adopt the equation QGGWW 102.6, G80, or WHTWWW 465.8. For both are based on the same observations and give, for QHG0 and QHE80, the values WHT80, the values WHT2 will indicate the remaining degrees more closely. To examine this, I set Q50 in the first equation and obtained WH or 58.83. Experience gives WH57 and thus somewhat less. Now I set WH57 in the other equation and obtained QQ50.03. The X gave QQTO, which is no different from nothing. I have remarked that the second equation, for the sake of simplicity, had to be improved. And since I really wanted to find a QA from the ILR, I had to solve it as follows. GHT232.88. After this, I assumed QUA from 10 to 10 degrees and found the values of UVI, which appear in the second column of the following table. I then reduced these in the ratio of 102.6 to 80 in order to set the boiling point at the 80th degree. These reduced degrees appear in the third column. The three following columns give these degrees according to the observations of Ducrest, Deluc, and Strohmeyer, so that they can be compared with mine, 125. Michele Ducrest actually made his comparison in such degrees as he counts from the cellar warmth of the Paris Observatory up to boiling water as 100. He sets the degrees of the spirit thermometer from 10 to 10 as a basis, and by experiments determines the corresponding degrees of mercury and linseed oil. He does not give the experiments themselves. Rather, he gives a table that he calculated by interpolation, in which the second differences are constant. If I express his degrees, calculated upward for spirit, mercury, and linseed oil, by EVOO, then the following two formulas can serve for his table, which therefore state all their numbers exactly. The degrees VV, QO are here counted from the point of the cellar's warmth. De Cressay on his thermometer places the freezing point at degree 10.4. Yet at first he had much difficulty in determining the temperature of the earth rather than the point from which the scale ought to begin. By means of this degree, 10.44, the formulas can now be transformed into others, in which the freezing point is set at 0 and boiling water at 80. Such a calculation has been undertaken by Deluc, and since he has made it unnecessarily complicated, I have, in the preceding table, adopted the numbers that I found in the first volume of Deluc's work, P425 and P222. Strohmeyer likewise does not give his experiments themselves, but a table which he regards as exactly agreeing with the experiments. Between the freezing and boiling points, there are 80 degrees. He assumes, like de Cressay, that the expansion of the spirit of wine is uniform, and he takes the differences required for Deluc's tables as constant. In his instruction on making thermometers that agree, his table appears on P42. It is calculated according to the formula QCGL 1.272 W234 W87. One sees from the table that the last four columns differ from one another only in small matters, that the difference is greatest in Deluc, and that my determination holds pretty much the middle between those of de Cressay and Strohmeyer. I therefore find no reason to depart from my determination. Deluc was undeniably very sensitive, and in his work he takes extraordinary care that later readers should not remain ignorant of even the least of his efforts, so that they may owe him their finest thanks. But the matter itself is not improved by this. It remains what it is and must always be considered in and for itself. And in that way, Deluc, with values 4 times smaller, could have said 4 times more than he actually did say. I maintain that what is said must be measured not by the words, but by the thoughts. 128. The circumstance that when either Q or V increases by equal increments, it is not the greatest differences of V, but those of Q that remain constant, and that therefore not the first, but the ninth formula at 123, toe 9, must be used. This circumstance, I say, seems to have some bearing on the matter. Michele Ducrest and Strohmeyer give spirit of wine. If spirit of wine, with a view to uniformity of motion, the preference, and therefore divide spirit thermometers into equal parts, whereas they divide mercury thermometers into unequal parts, because they believe that in the latter, the degrees of heat can be expressed better. But I have already remarked, pp. 98-108, that the constrained state of the enclosed spirit of wine does not allow this. Ducrest himself found that the motion of linseed oil is almost as great as the motion of mercury differs from the motion of spirit of wine. So, the spirit of wine would have to begin to boil too easily, that is, to enter a violent state, if, when enclosed, it were to have something entirely its own, and to proportion its expansion exactly to the degrees of heat. The numbers in the left-hand column are the true degrees of my spirit thermometer. I have determined them as Réaumur degrees, and they are such insofar as they agree, near the freezing point, with a Réaumur mercury thermometer, 150. Yet I would still like to know what Réaumur himself would say to it, if he were still alive and could think as he did at the beginning, for Réaumur had instructed the Abbé Nollet to make thermometers in his manner. He also received from Muschenbroek yearly thermometric observations, but these were made with a Fahrenheit mercury thermometer. This led him to have Nollet Compare the motion of the Fahrenheit instrument with the motion of the linseed oil through knowledge. Memoirs of the Academy of Paris, 1739. This found that, in the region of the freezing point, 10 Réaumur degrees in spirit of wine are equal to 20 degrees of the Fahrenheit mercury thermometer. It is not stated, moreover, how this comparison was carried out, whether Nollet had a Fahrenheit thermometer made by Holland, or whether he made one himself. Réaumur admitted that it is unnecessary to present this ratio and the rather uncertain observations, or, properly speaking, only the greatest and least degrees of each month in degrees of the Réaumur thermometer. It follows from this that if the expansions of spirit of wine and of mercury remain proportional to one another, the spirit of wine would have to expand in boiling water up to the 87th degree on the Réaumur scale. Tullet also states this explicitly in his Leçons de Physique, where he reports that in one of his experiments, from freezing to boiling water, the mercury in the latter rose in 15 seconds by 1480, the water in half a minute and a few seconds by 3780, the spirit of wine in 82 seconds by 8780, and the oil in 3 minutes by 7280 of its tube. Here the statement about the oil agrees fairly well with Newton's experiment, 105. By contrast, the mercury falls short by 1/80 part, since according to Delisle and other experiments, it ought to have expanded by 1580, 114. Perhaps Tullet did not wait long enough for the expansion to be complete, and thus the 87 degrees for spirit of wine might also be increased somewhat, especially since Tullet did not immerse the tubes entirely in the water. Moreover, I have long since come across a table of Réaumur degrees of heat in which the degree of boiling water was set at 87, 131. Now, since Fahrenheit places 180 degrees between freezing and boiling water, Tullet could conclude that if 87 degrees correspond to 180, then 10 degrees would amount to as much as 22 through it. In doing so, however, it would have been quite forgotten that mercury and spirit of wine do not increase in equal steps in their expansions. All this makes the ratio stated by Réaumur between the degrees of his thermometer and the Fahrenheit scale so much the more unusable, on the other hand, since he sets the degree of the body's warmth at 32 degrees. And I find it the same on my spirit thermometer. I have more reason to conclude from this that my thermometer will differ little or not at all from his in the first 30 degrees. And from this it follows that by the procedure described in G119, one can always hit the Réaumur scale quite well. One also sees, however, that I have, so to speak, quite accidentally arrived at a method which, instead of Réaumur's, can be used much more conveniently on the Fahrenheit scale. This chance further shows in particular that, although Réaumur sets the degree of boiling, he has mistaken water, and in its place has taken the degree of boiling spirit of wine, and without knowing it, he has thereby obtained a step on the scale, which in the region of the freezing point makes his spirit of wine thermometer agree with the mercury thermometer named after him. I do not, however, wish to be understood as if I were denying all his thermometers, C117. It is often precisely those on which Réaumur bases his own observations and rules. Indeed, his whole manner of speaking, that are meant, and which therefore constitute the true Réaumur spirit of wine thermometer. From this it follows that, in the region near the freezing point, it must indicate 8 degrees too much, that is, 15 degrees on the spirit of wine scale, or 8 degrees on the mercury scale, since 15 spirit of wine degrees are equal to 8 Réaumur mercury. M. de Luc took great pains to find, in a very detailed way, what I happened to discover by chance. He set out, namely, to make a truly Réaumur thermometer. He chose the medium-strength spirit of wine required by Réaumur's prescription, and divided the thermometer likewise according to Réaumur's prescription and observations. And he also judged where the prescription or the observations might have consequences. This was necessary because Réaumur himself did not always follow his own prescription exactly in the execution, and therefore the observations were not always in accordance with the prescription, but rather with the execution as it actually was. M. de Luc then compared his truly Réaumur spirit of wine thermometer with his Réaumur mercury thermometer, and found the following corresponding degrees. Mercury spirit of wine 80, 100.4. 66.6, 80, Spirit of wine that is just about to boil, 29.9, 32.5. Warmth of the body, 9.6, 10.25. Cellar of the Paris Observatory, 0.8. It's freezing water, 17. Frozen ice. It is very unnecessary to evaluate here this extensive comparison and assessment by Monsieur de Luc. The difference in the last four columns of the table, 124, would have to be taken into consideration. It is enough that de Luc hit upon the true Réaumur thermometer fairly well, and that I therefore have no cause to depart from my view, even if I too have only arrived at it by chance. Réaumur's faulty thermometers are not thereby made good. Done well, and among the many observations made with it, one must always, as far as possible, decide from other observations to what degree one should set the freezing point. For according to Réaumur, it ought to be the 80th degree. With alcohol, it was 87 and more. De Luc found it to be 100, and there have also been those in which de Crécy found it to be 115. Presumably, there were also some that indicated an even higher degree. The cold in Syria is said to have risen to the 50th degree on the Réaumur scale. In Senegal, it is said to have risen to the 39th degree. In this way, the Réaumur thermometers, among which certainly many were merely copies, had little by little to give up all the claims that had been made for the Florentine thermometer in general. De Crécy's and Martin's reminders of the essential errors did indeed appear soon enough in public print. Moreover, Réaumur himself remembered that the movement of the mercury could not be proportional to that of the alcohol. Nevertheless, people calmly went on reducing the observations made with Fahrenheit, Delisle, and Swedish mercury thermometers to the Réaumur scale, and treating them, as in G 115, as if there were no difference at all between alcohol and mercury. Martin falls completely into this error, and therefore makes his comparison table of 15 different thermometers very incorrect. Brown, in the November Commentaries of the Academy of St. Petersburg, Part 7, is more accurate in his comparison table in that he takes into account the difference between alcohol and mercury, so that he gives the mercury thermometer for the boiling point 80 degrees on the Réaumur scale, but gives the alcohol thermometer 93 degrees, and therefore does not consider the true Réaumur alcohol thermometer to be correct, because it must have only 100 degrees. Besides, Brown does not take into account the inequality in the progress of the two thermometers. It will therefore be quite unnecessary to touch on other errors in his table. What has been said so far concerns the comparison of mercury and alcohol with respect to their unequal expansion, insofar as this can be determined by actual experiments. I shall now proceed to the comparison of alcohol and air. Amintons believed, as is well known, that his air thermometer advanced in the same steps as the alcohol thermometer. Of this, however, he had to assure himself beforehand, because he had to divide the latter according to the former. He does not, however, give any detailed experiments, and it is very likely that his comparison referred only to the usual degrees of weather, which do not extend very far. For this reason, de Luc could have spared his reproaches, and it was quite unnecessary to accuse Aminton's thermometer of all sorts of imperfections, and to say that it did not even come close to a mercury thermometer. This is not improved in the least by the blame he heaps on it. It remains what it is. Amintons gives his observations only in whole and half inches, and it seems to me that he was satisfied with that, because his conclusions, taken as a whole, agree with experience. That is what he really wanted to know. With a longer life, he would probably have applied himself more to a more exact determination. Thus, the first balance was probably not the finest gold scale. It is enough that the invention existed once. Refinement can come afterward. In order to see properly what relation the expansion of air has to that of alcohol, I have long since brought forward the observations made in 1751 with the air thermometers mentioned above, PPI 69, 90, because for 6 years I had recorded them simultaneously with the alcohol thermometer and the barometer. These were, however, scattered observations and therefore lay within narrow limits. But since I could take the mean from observations over several days, by which the smaller irregularities were removed, I found in fact that the expansion of air does not proceed in the same steps as that of alcohol. For, according to the mean of all observations, the following degrees coincide: alcohol thermometer, air thermometer 0, 115, 1059, 30, 110. The spirit thermometer was Reaumur's, and, as far as I can conclude from several comparisons, it agrees fairly well with my air thermometer. In the first construction of the air thermometer, I had not taken care to make the division perfectly correct. As I do not remember exactly, I determined the size of the degrees only by the inclination of the tube, but this method is somewhat uncertain. Yet whether the degrees are a little too large or too small, if its true reading at 1000 is correct, then the degrees are at least proportional to the true ones. This is sufficient to be able to conclude with certainty that the two instruments do not run alike. For the first 15 degrees of the spirit thermometer correspond to 59 degrees of the air thermometer, and for the following 15 degrees to 51. The severe cold in January 1776 gave me a fresh occasion to repeat the comparison, not only down to the freezing point, but down to the degree of boiling water, consequently to extend it to 117 Reaumur degrees, and to take every circumstance into account. I have described in detail above, pp. 72, 81, 80, 88, the air thermometer needed for this, and likewise the spirit thermometer, p. 119, followed. Wine spirit thermometer. The experiments, for the sake of comparison, yield the following table. These experiments I carried out on the 21st of January and on the 1st and 2nd of February 1776. I found the different degrees of warmth, first by the window in my unheated room, then in my heated study, then in the stove room, which was set on the stove, and finally, in boiling water. The bulbs of both thermometers were each time placed exactly next to one another, so that could not alter the difference of the place. They bent down from the little board on which the stepladder was fastened. On the air thermometer, I drew the line so that the mercury in C, figure 3, stood higher than in B by 9 decimal parts. This height EC contains the fourth column of the preceding table. In the third column are the barometer heights observed at the same time. The fourth gives the sums of these from above, and consequently the pressure that the air in the bulb had to withstand. In the fifth, the volume of the air is represented by the weight of an equal volume of mercury. These are therefore the observed measures, 138, since the force of warmth is in a compound ratio of the pressure. I therefore multiplied each number of the fourth column by the corresponding number of the fifth, but for brevity I have entered from the products only the first four numbers in the sixth column. These are therefore proportional to the force of warmth in air of equal density, 49, 50 to 139. Thereupon I plotted these numbers, or properly only, as ordinates, and took the numbers of the first column as abscissas, as ordinates, partly to see how far the points would lie on a uniformly rising line, and partly to draw through the points, as far as possible, a line that deviated least from them, and yet retained a curvature as uniform as possible. The construction showed that the abscissa 0 met the ordinate 5,933. I therefore divided 5,000. Wow, 140. This same drawing then served me further in place of a formula for interpolation. I divided the last ordinate, insofar as it rises above that of freezing water, into 8 equal parts, and through the division points I drew straight lines parallel to the abscissa line. Where these cut the curved line, I marked the points and measured the corresponding abscissas. In this way I obtained the following table. Here, the third column can now be compared with the second of the table given above, P124. For one sees here that if the degrees of the air thermometer from freezing to boiling water are divided into 80 parts, and these are taken arithmetically in steps of 10, the expansion of spirit of wine does not proceed in equal parts, but increases ever more rapidly. This is shown in the same way in the 21st section in the discussion of mercury. There, the degrees of the mercury thermometer were likewise carried forward by tens, and it was found that the degrees did not increase equally, but always more quickly. If then air and mercury are to proceed in equal steps, the third column of the present table must contain exactly the same numbers as the former, P124. The difference is very small, and may perhaps be attributed entirely to the small errors unavoidable in such experiments. It follows from this that, as far as these experiments reach, the mercury thermometer agrees with the air thermometer. if not completely, then at least without any noticeable difference in equal steps. Since the air thermometer indicates the true degrees of heat, it follows that in the mercury thermometer, equal degrees of expansion also indicate equally large differences of heat, at least as far as these experiments. But the same conclusion does not follow here. Rather, it follows from this that the degrees of the spirit of wine thermometer do not proceed in equal steps with the degrees of heat, but begin from about the 20th degree on the Reaumur scale to increase noticeably more rapidly. Since common weather observations seldom go beyond the 25th or 26th degree of summer warmth, the spirit of wine thermometer may always remain devoted to these observations. Its uses without. It is therefore advisable to set the spirit thermometer by the mercury thermometer, as I have just described, P119, and have myself done. They then agree, so far as the weather observations extend, and at the higher degrees, the reduction can easily be made. The numbers in the third column of the table increase toward the end so rapidly that they cannot at all be represented by an equation of the form GBEE. This sufficiently shows the already mentioned force condition of the enclosed spirit in strong heat. Besides, it is not necessary to seek a formula that is accurate beyond the 60th or 70th degree, since spirit thermometers are seldom used at such high degrees of heat, and as far as I know, never for any purpose other than the one for which I have used it here, namely to determine the degree of its expansion. For lower degrees, the following formula may be sufficient. W equals x 1/1/500, that's where x denotes the degrees of the second column and w those of the third. It gives the following values: x, w, 10, 10, t, 20, 21, 30, 32, 40, 40, 40, 50, 60, 69, which differ little from those in the table. Because of the trouble of maintaining the water at 1 degree of heat between the warmth of the air and that of boiling water, I performed the experiment only once, and so a slight circumstance may have caused a difference. Moreover, I do not offer this formula for testing, since it is really intended only to compare the values of x and w with one another in an easy and tolerably accurate way, without extending its use beyond what spirit thermometers are commonly used for. For this purpose, it will now be more convenient, instead of the numbers of the second column, to take those of the first. If we set x to 1000 a chin, then the formula is transformed into. From this it follows, once again, a formula by means of which the degrees of the spirit of wine thermometer can be converted into degrees of the air thermometer, yet with the necessary limitation that one must not extend its use as far as the degree of boiling water. Some well-known spirit of wine thermometers, however eagerly spirit of wine thermometers were received at first, they also caused much confusion and trouble, until one finally learned to understand their language better. Without regard to the preceding long section, we are still not at the end. With spirit of wine thermometers, an unpleasant amount of experiments has been undertaken, which must be so useless if one does not know their language. That is what I mean when one does not understand their scale divisions. Martin and Brown carried out very painstaking experiments. Crest also set about comparing some thermometers with his own. Deluc likewise gives some comparisons, and one finds comparisons again and again. But they also deviate from one another and do not make a renewed investigation superfluous. I do not mean by this that one should simply reduce mercury and spirit of wine thermometers to one another, but rather take the true degrees of heat as the basis. These degrees are, to be sure, in everything that concerns spirit of wine thermometers, so little different from one another that one must calculate in thousands in order to state the differences with sufficient precision. One cannot then say with Newton, the heat of glowing iron is 3 times greater than some well-known spirit thermometers. For the heat of summer, which comes from glowing iron, is 3 to 4 times greater than that of boiling water, etc. Thermometers would have to look quite different if the degrees of warmth were to be carried according to such a scale. But our author is very excusable if he must speak so, since this is the common way of speaking, that boiling water is about 1/4 warmer than summer heat, or that freezing water is not much more than 1/3 warmer than freezing. And yet, this manner of speaking is correct if one calls everything warm that can still become colder, but all this does not prevent it from being not entirely good when one wants to teach us the true language. This can be omitted here. It has already been shown above that the true Reaumur spirit thermometer, compared with the air thermometer, PP2 142, will be sufficient to reduce other spirit thermometers to the Reaumur scale. I de la Hire, 144. The first spirit thermometer to be mentioned here is that of La Hire, which I have already referred to above, P56. It has been in use since 1670, and for 30 years it was also used to record each year the greatest heat of summer and the greatest cold of winter. This was made known annually in the memoirs of the Paris Academy of Sciences. For a long time it was regarded as the only instrument with which the severe winter cold of 1709 was observed and recorded, and now, since it has been broken for so long, one must first see whether one can still trust his account. 145. La Hire himself gave 2 identifying marks for it. 1. In the cellar of the observatory it always stood at 8 degrees. This always is not quite correct. Marriott had long before shown La Hire that warmth in a cellar is not intelligible. 2. It freezes in the field when the thermometer in an open hall stands at the 32nd degree. By this, the degree of frost is not determined. One would have to be able to compare it with Amundsen's thermometer for that year. But La Hire first proposed this after Amundsen's death. He observed 2 degrees, namely, La Hire 28 and 63, Amundsen's 514 and 553. This is Amundsen's freezing point, 78. He adduces this in order to compare it with his 48th degree and with Amundsen's 54th, and finally to conclude that Amundsen's tube was probably more irregular than the one in his own thermometer, especially if, in Amundsen's thermometer, the irregularity of the tube had some influence. At last, he adds that La Hire in 1709 believed he could make a thermometer that agreed with it. From this, it follows that La Hire, in making the comparison, certainly did not have the intention of seeking out matching degrees, and then praising the agreement. This suspicion does not fall on him. Yet in this way, mutual suspicion can be stirred up more and more. Properly speaking, in such comparisons, one must take different degrees. La Hire made his in the year 1709. He must therefore have been somewhat curious to see how low, in the severe cold of that time, the Amundsen's thermometer would fall, since La Hire's own stood at the 5th degree. Reaumur later took up the matter more seriously, indeed only after La Hire's death, for La Hire could hardly have been instructed by Reaumur's thermometer about the improbability of his own, because he died much earlier. Reaumur had one of his thermometers made and then hung another beside it, next to La Hire's, in order to translate all of La Hire's observations into the scale of his own thermometer, and in particular, to be able to indicate the cold of 1709 on it, so that this cold could be compared with that of other less severe winters. To this end, he placed both thermometers in freshly made ice, and when La Hire stood at the aforementioned 5th degree, he marked the degree at which his own stood, and this was the first Reaumur degree below the freezing point. One had to examine whether the bulbs on both thermometers were of equal size, for smaller bulbs take on cold and heat more quickly than larger ones. The first Reaumur thermometer, hung beside La Hire's, was likewise observed from 1731 to 1738, and the following degrees from it are recorded in the Paris Memoirs, some well-known spirit thermometers. I have now added up the degrees in each column and divided their total by their number in order to obtain the true mean. Accordingly, they are as follows. La Hire, 74.67, Reaumur, 24. La Hire, 25.02, Reaumur, the 3.06, the mean of the winter degrees, different. La Hire, 49.5, Reaumur, 27.6. This therefore means that 49 degrees on La Hire's scale amount to as much as 27 on Reaumur. The ratio is as 197 to 111. This comparison can now serve to determine with which Reaumur degree the 5th degree on La Hire's scale agrees, namely, that taken from the winter cold of 1709 for 25.0 minus 5 equals 20.02, and 103.06, 14.34, thus it is 14 and 1/3 degrees below zero, or 15 degrees, CP 146. From this calculation, it follows that Reaumur 0, or freezing point, corresponds to the 30 and 1/3 degree on La Hire's scale. This can explain the previously asked question, P 145. Finally, since Réaumur sets the cellar temperature at 10½ degrees on his thermometer, the calculation likewise shows that this degree corresponds to the 48¾ or 49½ degree of La Hire's thermometer. La Hire gives 48. If, therefore, one does not insist on exactness, the comparison of the two thermometers is thereby established. Ducrest compared La Hire's thermometer with his own in 1741. CP 125 to First, he found it in the cellar of the Paris Observatory at the 47th degree on the 28th of January. In summer, it might well have been a degree higher. I note this here because Ducrest did not pay attention to it, but rather drew the conclusion that La Hire had assumed the expansion of Mercury. This conclusion does not follow, because La Hire, having found 48 degrees, depending on the season, makes no mention of any increase. Ducrest then hung both thermometers a roof's height above the ground, in free air, side by side, and found on the 10th of January at 6 o'clock in the morning La Hire's at 9½ degrees and his own at 22 degrees below his zero, which is the same cellar temperature of the observatory. Thus 48 minus 9½ equals 38½ La Hire degrees, just as 22 Ducrest degrees, since both are filled with spirit of wine, and Ducrest goes from freezing to boiling water, has 100 plus 10.4 equals 125. These 22 degrees correspond to 191½ La Hire degrees. For 22 is to 38½ is 110.4, is to 110.4. Further, 2 is to 38½ is 10.5. Consequently, on La Hire's thermometer, the freezing point lies 18.1 degrees below the cellar temperature, therefore at the 29.9th degree. The comparison with Réaumur's thermometer gave 30⅓ degrees, P on 48. So, on La Hire's thermometer, the freezing point may be set at the 30th degree, and thus the boiling point would fall at 221½ degrees. Finally, since 197 La Hire degrees, some so-called thermometers using alcohol are equal to 111 degrees Réaumur, CP 148. Thus, for 191.5 degrees La Hire, one finds 107.9 degrees Réaumur. Accordingly, the Réaumur thermometer used for the comparison counted 107.9 or 100 base from the freezing point to the boiling point. This Réaumur thermometer, therefore, deviated by several degrees from the true Réaumur, CP 132. With my Réaumur alcohol thermometer, I could now compare the La Hire thermometer without difficulty, since from freezing to boiling water, I count 102.6 degrees. By means of the freezing point set at 30 degrees on La Hire's scale, that La Hire 0 falls 191.5, 102.6, Ichichi 16.1 degrees below my thermometer. Consequently, it lies fairly close to the degree of the same snow which I have repeatedly found between 15 and 16 degrees. The beginning of La Hire's scale, therefore, seems not to have been chosen arbitrarily, but to have been determined according to the principles of that time. This prompted me to see whether the red La Hire degree might likewise have had to be determined on such grounds. The calculation gave, according to 191.5, 102.6 Chushu, 137½ degrees on my alcohol thermometer. I have found from this that melted tallow between the 37th and 39th degree becomes solid or congeals. Thus, La Hire's scale division falls between the freezing of the same snow and the congealing of melted tallow, very precise. Insofar as this was, in fact, the intention, it is one of the best that were made around the year 1670, Delta 151. With this La Hire thermometer, no observations were made, except meteorological ones. And of these, only the greatest and least degrees observed each year in the memoirs of the Academy of Sciences in Paris were made known. I have already presented those from 1731 to 1738, see P146. I shall therefore add the preceding ones here as well. Some notable spirit thermometers. Greatest heat and cold of the air are observed with the La Hire thermometer in an open hall of the Paris Observatory. 1727-21, 31 Dec 1728, 9, 19 John 1729, 23, 27 John 1730, 21, 25 Jan 1731. He was the first who, by careful observations with thermometers, refuted the old prejudice that cellars are warmer in winter than in summer, and showed that our sensation of warmth indicates only relative degrees. For several years, he took the trouble to place his thermometers in cellars of different depths and to observe them diligently. In all of them, he found that in winter they stand lower than in summer, but that they change all the less the deeper the cellar is and the more it is protected from drafts of outside air and from sunshine. He therefore visited cellars all over Paris. He also reports all his observations in detail. They may be found in his essay, which at the time attracted much attention, on heat and cold. Marriott gained no advantage from this labor, and in any case, the thermometers of that period were not very well suited to his observations. Yet there are other reasons why it is useful to become better acquainted with the nature of heat and cold in cellars. And since not everyone will take the trouble to carry out such observations for several years, Marriott's observations remain indispensable. For the same reason, it is good to make the language of his thermometers intelligible. He describes his first thermometer as well as he could according to the knowledge of that time. It was a Florentine, or spirit of wine, thermometer. He says that in winter the spirit rose almost to the bulb, but in summer it rose more than 3 feet in height. The length of the tube was about 42 inches. The scale had degrees, each spanning 4 lines. This would make 126 degrees and 42 inches, but since the scale was probably not as long as the tube, it may also be that it contained exactly 100 degrees. The degrees were counted from the bottom upward. Marriott found the summer warmth in the shade at the 80th degree, and in the cellar of the observatory, the spirit of wine stood at the 52nd and 53rd degree. That degree must therefore have been taken as the temperate point. From all these circumstances, the 80th degree can be regarded as no more than the 20th degree on Reaumur's scale. And since the 53rd coincides with 10.5 degrees on Reaumur, it follows that 80 minus 53, that is. 27 Marriott degrees correspond to 20 minus 10.5. That is 9.5 degrees Reaumur. Consequently, 1 degree Reaumur amounts to about 3 Marriott degrees. Greater exactness in the comparison is unnecessary if we only look to some well-known spirit thermometers. If one considers the change of warmth in the cellar of the observatory, which is 84 feet deep, Marriott reports the following observations. 1670, 60 52, 18 Dec 52 and 7/8, 1671, 25 Aug 53, and 3/4 15 September, 53 and 3/8, and a little more. 18 DQ and 1/4 16072, 15 February, 52 and 1/2 September, 53 and 3/8. The greatest warmth occurred in September, and the greatest cold in February. The total variation amounts to 1 Marriott degree, or 1/3 of a Reaumur degree. There he found the following degrees. 1672 November, 49 degrees. 1673 Jan, 44 February, 47, 4 April 47, 4 April 47, 14 April 47. Emperor 47 and 1/3, 48, 24 April 47 and 1/3. 5 June 48 and 1/2, 19 June 48 and 1/2, 3. July 49, 17, 49 and 1/2, 31. 50 and 1/2, 14 August, 50 and 3/4, 28. 51 and 15 September, 51 and 1/2. After this, the thermometer broke, so that but since in September it had almost reached the highest degree, Marriott judged that because it remained below 53 degrees, this cellar was colder than the one at the observatory. One sees that the total variation was 9 Marriott degrees, consequently 3 Reaumur degrees, and thus 3 times greater than in the observatory cellar. He took 2 other thermometers, of which he says that they were of equal strength. By this he means that they agreed exactly with one another, as well as with the broken one. Some well-known thermometers by Wiengist agree exactly with one another. I leave undecided. Marriott had accuracy enough not to be satisfied with comparisons that were merely made up. And so, at least the 2 thermometers that were then in Paris differed little from one another in their degrees. I shall now proceed to the experiment and place one of them in a cool cellar, the other in a room above, which in the same building lay on the 2nd story, or 2 flights of stairs up, and was not warmed by the sun. The degrees were smaller than on the broken one, and only by 2.5 lines. Marriott says he had it in July 1674 in the room and found that it stood at 89 degrees. They did not agree exactly with this degree. The observations are as follows. Thermometer readings in the room and in the cellar with the time of observation. Marriott says he regarded these observations as among the most remarkable ever made. Accordingly, the 92nd degree is to be taken as the greatest summer heat of the last 3 years, and it would therefore agree with the 24th degree on Reaumur scale. Further, since the cellar was not deep, the 24th degree, which indicates the greatest cold in the cellar, may have been only a little above the freezing point, if we set it equal to the first Reaumur degree. It follows that 92 minus 24 equals 68 Marriott degrees, which is as much as 24 minus 1 equals 23 Reaumur degrees. And thus, the tangent Reaumur degree would be the temperature of the cellar of the Paris Observatory on the Marriott scale. 24.3 degrees. These two thermometers, therefore, agree fairly well with the first broken one, and their meaning is thereby made clear. The 100th degree corresponds to the 27th degree of Reaumur, and thus indicates the greatest summer heat. The 21st degree is the freezing point, and the 0 degree corresponds to about 7 degrees below zero on Reaumur scale, which is a moderate winter cold, at which the snow does not melt, and it is still much too cold for spring. Hawksbee and London made spirit thermometers, with which observations have been made from time to time. Martin calls them the London Society's thermometer of the Danzig merchants, and says that in one of them he found only a single division. Meanwhile, they must not have been made very carefully according to the pattern, because complaints were made about them. Martin also says he found several that did not agree. The degrees are counted on them from top to bottom, and their inscription accordingly is meant to indicate 0 degrees very warm 25, warm 45, moderate 65. Frost Celsius, who at Jurin's urging had undertaken to make shared weather observations, also adopted this. Martin looked for such thermometers that matched the pattern kept by the society. He compared them by means of repeated observations with his Fahrenheit mercury thermometer. But since he did not, some well-known spirit thermometers. Since I knew that such a comparison requires a reduction, I will not apply his observations, together with the reduction, to my spirit thermometers, because I can regard these as true Reaumur scales. CP 122, Hawksbee spirit, freezing point. Mercury, Reaumur spirit. It follows, therefore, that 44 degrees on Hawksbee's scale amount to 14.9 degrees on the Reaumur scale. It further follows that the upper fixed point, or 0 point, of Hawksbee's scale falls at 26.6 degrees Reaumur, which indicates a strong summer heat at which butter melts without even lying in the sun. The standard Hawksbee thermometer may therefore be set down as quite good up to 126 degrees at the 0 point, or great heat. If, however, one pays attention to the inscription that 65 degrees indicate frost, then the freezing point cannot be meant by this, since that falls at 78 degrees. This applies to the standard instrument and to Hawksbee thermometers that agree with it. Any that do not agree must, accordingly, be examined separately. 158 among these, that of Celsius occurs most often. Because of the quantity of observations made with it, it deserves investigation, and Celsius partly carried this out himself and partly provided circumstances for it. In January 1740, he found that of his thermometers, the Hawksbee showed 26, the Reaumur 19, and that of Lisle 192 degrees. Compared with Ul's, the Reaumur was too low. The 192nd degree on de Lisle's mercury thermometer corresponds to 22.4 on the Reaumur mercury thermometer, and to 21 on the true Reaumur spirit thermometer. This 21st degree must be taken for the comparison. It corresponds to the 126th degree on Hawksbee's. According to Martin, however, it should not be the 126th, but 14.5, 2178.5. Each one applied. Furthermore, Celsius sets the 65th degree as the true freezing point. If one actually finds it so, then it lies 13 degrees higher than Martin's, since Martin finds 78 degrees. One may therefore suppose that the scale divisions are indeed the same, but that they have an unequal starting point. It has not, however, been proved that the 65th degree is truly the freezing point. In the 10th volume of the A Miscellanea Beroliniana, I find that Celsius had no intention of making his observations outside. Rather, he set up his thermometer in a room that was not heated. It could therefore indeed indicate the 65th degree, even when it was already freezing hard in the open air. But for that very reason, the 65th degree is not the degree of freezing water, because rooms do not cool as quickly as the open air. Moreover, in the year 1731, Celsius found the greatest summer heat to be at his 20th degree, and says that the usual summer warmth is the 30th degree. If Celsius had 65 degrees where Martine has 78, then Celsius' 20th degree would correspond to Martin's 43, and would thus lie fairly above the freezing temperature. And this would have to mean that in Sweden there is no summer warmth. From the conversion of the Hawksby degrees into Swedish degrees, which Wargentin presented in the 19th volume of the Swedish Transactions, I also see that Celsius' thermometer differs little or not at all from Martin's. It will therefore be more correct, when we look at the inscriptions on Hawksby's thermometer, to take them as indicating the state of the outer warmth and cold only when the thermometer is observed not at the window, but in an unheated room. This is the case with most of the former weather observations. One can thus easily explain how it came about that, in Naples in 1731-1732, Hawksby's thermometer was found at the 65th degree while it was freezing in the street. One need only remember that the thermometer was hanging indoors, and that the frost in Naples does not last so long, that the rooms could cool even to the 65th degree, let alone to the 78th degree. Hales, as he relates in his Statics of Vegetation, made a very scientific garden thermometer, namely, in the year 1724, at a time when scientific thermometers were still very rare. He wanted an instrument that would indicate the degrees of warmth and cold as required by the theory of the growth of plants. For this purpose, he set the degree of boiling water. On the other side, he set the cold of freezing water as the degree at which the growth of plants ceases. He marked these 2 points on his thermometer and divide the interval into 100 parts, counting them upward from the freezing point. According to my Réaumur thermometer, wax begins to melt at the 56th degree. The Halley scale, therefore, presents not the slightest difficulty. In the above-mentioned work, Halley reports many observations that he made with his thermometer. The principal ones are as follows: 0, freezing point, 100, boiling wax, 64, blood in living animals, 54, warmth under the arm, 55, fresh milk, 58, urine warmth, 56, warmth for hatching eggs, 50, summer warmth, 85, warmth, 88, greatest heat of the sun. Halley was concerned not only with the twigs and leaves, but also with the roots of plants. For this purpose, he sank thermometers in the garden 2, 4, 8, 16, and 24 inches deep into the earth, and left another standing above ground, with its bulb touching only the soil. He does not report the observations at depths of 4 and 8 inches. Of the others, the most noteworthy are the following: at 0, 2, 16, and 24 inches under the earth, in August 1724, at the end of October, in winter, in summer 1725. Martine could not make sense of this thermometer when he wanted to compare it with the Fahrenheit scale. At first, the matter seemed easy to him. Halley had, after all, set 2 very definite degrees, namely the freezing point and the warmth of boiling wax, as the basis. Martin therefore took his Fahrenheit mercury thermometer and found for coagulating wax the 142nd degree. Now, since the freezing point falls at 32, the difference amounts to 110 Fahrenheit degrees, and this is just as much as the 100 degrees of the Halley thermometer. It still remained to be seen how the other degrees observed by Halley stood. Martine, however, is content to say that at the beginning of spring, Halley had found his thermometer at the 13th degree, when the Fahrenheit thermometer stood at 48. Thus, 13 Halley degrees would be as much as 16 Fahrenheit degrees. In the copperplate, Martine makes 60 Halley degrees equal to 74 Fahrenheit degrees. From this, 3 different ratios result, namely 100, 100, and 13. This difference disappears entirely if taking into account the unequal progression of mercury and of alcohol, or, to put it more briefly, comparing the Halley thermometer with the Réaumur alcohol thermometer. For since 100 Halley degrees are as much as 56 Réaumur degrees, the following comparison results without difficulty. Halley Reaumur 54, 32, warmth under the arm. 58, 32, urine warmth. This is very accurate. And it remains correct, notwithstanding this, that the 13th Halley degree properly coincides with the 48 Fahrenheit degree. For 13 Halley degrees, give 13 cho 0.56 Chi 7.28 Reaumur degrees of alcohol. Consequently, according to the second formula, P 123.77 Reaumur degrees of mercury, and these give 180 100 Shui 7.7 Chi 16.30 or 16 Fahrenheit degrees. Added to the freezing point of 32 degrees, this gives 48 degrees. V. Fowler, 164. Here is yet another alcohol thermometer, which Martin could not correctly compare with the Fahrenheit mercury thermometer. Fowler had it made for the use of plant houses. He wrote beside the degrees of it the names of the plants which thrive best at such degrees of warmth. They are as follows, as Halley likewise states them, according to his thermometer. Fowler, Halley plants. 25-29. Pineapple, 326 pimento. Some name spirit thermometers. Savler, Hales plant. Plus 15-24. Euphorbium, plus 10-21.5. Sirius, plus 5-19.5. Aloe, 0-16.5. Indian fig. Aenas 5-14 ficoids. Minus 10, 12. Orange, minus 15, 9, Myrtle. Martin now says that at his request, Savler determined the degree of freezing mercury and found it at minus 34. This already indicates the relation to the Hales degrees in itself. But when Martin further says that, from various comparisons, he finds that the 16th Savler degree corresponds to the 64th Fahrenheit degree, then he is off by 3 degrees, for it should be only the 61st Fahrenheit. This thermometer has become known to me from J. Gesner's botanical thermometer. It is purely botanical and counts onward by 2 degrees at a time, whereas Savler counts by 5 degrees at a time. The comparison is easy to make and yields the following. Savler Benart plants, minus 35, 0 minus 15, 8 Myrtle, minus 10, Amaryllis sarniensis, 11 Olive, minus 5, 12 ficoids, 13 capers, 0-14 Indian fig, 0-14 Indian fig, 15 pomegranate, plus 5, 16 aloe, 17 cassia, plus 10, 18 Sirius, 19 Gerius, 19 ginger, plus 15, 20 euphorbia, 21 tamarind, 23 coffee, some well-known spirit thermometers, Solar, 25, 30, Renard, 24, 26, 27. Plants, Pinus exotica, Rum persicum, Laura cinnamomea. 7th section, on other spirit thermometers used up to now, 166. A great many weather observations are available that were made with old or common de Lisle or Florentine thermometers and were continued for many years. One finds a large supply of them in the Breslau collections, in Buchner's continuation of these, in the Commercio Epistolico, and in several other yearbooks. Those who were fond of such observations usually obtained thermometers that were already finished and delivered on boards. With these boards, one could, for example, take the bulb in the hand, or place it under the armpit, or put it into fresh blood, urine, milk, snow, freezing water, and so on, in order to mark these degrees of warmth, things that occurred to few or to none. And so what is lacking is precisely the information by which one could most reliably see how the scale divisions were made. God 167. Some of these observers did indicate the thickness of their thermometers. They usually gave only the length of the tube in inches. Very few gave the diameter of the bulb. And even when the diameter of the tube was considered, it was the outer diameter of the glass. Yet the inner diameter would have had to be measured very precisely. For optical reasons, this seems to be about half again as large when one does not see it directly, because the refraction of the rays in the air and the glass makes the apparent size about 3:2. But since the diameter is very small, it cannot be measured in this way with any considerable accuracy. For the sake of brevity, I therefore omit the proof of this optical point, especially since it can be found without difficulty. Nothing further is required for it than to assume that the rays run parallel to the eye, which, if one holds the tube 2 inches or more away from the eye, can be accepted without noticeable error, given its small diameter. So there is hardly anything left to do except to set down the observations themselves. And then the question is, how can one, from the degrees observed each day on a thermometer, Determine the scale divisions of that thermometer and compare it with known thermometers. This is now more difficult or easier, depending on the circumstances that are reported. First, I look to see whether the place of observation is known, since not all countries have the same alternation of warmth and cold. Then one considers whether the observer has stated where the thermometer was placed, namely, whether it stood by a window or in an open corridor or in a closed room, whether it was hung at midday or at midnight, whether the surroundings and the house are described as standing free or being enclosed by buildings. Further, whether the observations were made in the morning, at midday, or in the evening, or whether the hours of the day were not set regularly. One can easily see that from such circumstances, even if they are all known, no very great accuracy can be expected. But this is not always required. One then begins by seeking out the degrees of the greatest warmth. In our regions, these extend from the 20th to the 26th degree on Reaumur's scale. If one already knows from that or from other observations whether the summer was cold or moderate or very hot, then one can, between these Reaumur degrees, make a fairly good estimate. Once the warmth has penetrated into the masonry and walls, the position of the room makes no noticeable difference anymore, unless it remains shut off from daylight, as happens when one wants to keep a room cool. With winter cold, there is more difficulty because it varies much more strongly from one year to another. In our regions, the limits lie between 6 and 18 Reaumur degrees below the freezing point. In mountainous regions, they are deeper. But if the thermometer is hung in the open air, and the observer has indicated on which days it began to freeze or to thaw, then one will miss the freezing point on such a thermometer by little or not. If one takes the average of all the degrees observed on such days, these degrees will also differ little among themselves. On the other hand, they differ more when the thermometer is not observed in the open air, but indoors, where it is not heated, and where the outer air has no free access. If one has water in such a room and finds it frozen, as happens after a long and in such rooms, the thermometer shows very different degrees at the beginning and at the end of a frost, depending on whether the thaw was mild or whether the frost was harder and more persistent. Since I have observed the thermometer for several days in the room, in 2 unheated rooms, and at the window facing north, especially in the morning, I find the following. At the first frost in October, the Reaumur thermometer stood at 0 in front of the window. In the rooms, it stood at 8 degrees above 0, 2. At the beginning of the frost in November, it stood in the rooms at 6 degrees, but at 4 or 5 degrees when it thawed again. 3. In December, at the beginning of the frost, it was at 5 degrees when it thawed. In these months, the frost did not last long. 4. In January, the thermometer in the rooms, when it began to freeze, when at 4 degrees, went also at 1 degree, and when the frost did not last long, at 3 degrees. In February, when there are sometimes several truly spring-like days, the thermometer then rose to 6 or 7 degrees. Yet when frost returned, it usually fell to 4 or 5 degrees, at the thaw to 3 degrees. The same is found in March as well, at freezing and at thawing. 7 in April, it usually thaws completely. And then the thermometer in the room remains at 3, 4, or 5 degrees. After these propositions, I have now taken up again the observation mentioned above of Celsius in the Miscellanea, Berlinensia, volume 5, and find that his Hawksby thermometer in October, when it began to freeze, stood at the 56th, 57th, or 58th degree, in November at the 60th to 64th, and when it thawed at the 62nd. In December likewise. In January and June at the 69th or 70th. In March at the 60th to 67th, and when it froze again at the 54th. These degrees are so different that one should not conclude that the thermometer was hanging in a room. It follows, therefore, that from other cold weather thermometers used up to now, that the 5004th or 5005th degree of Celsius agrees very closely with the 80th degree of Reaumur, and that the 69th or 70th agrees very closely with the 100th of Reaumur. And from this, it follows that, on the Celsius scale, the true freezing point must fall at 78 or 79. This agrees very well with the experiment by de la Perrière. Even if these observations can help us find the freezing point and thus learn to understand the thermometer scale, we nevertheless learn from them only the condition of the room and the cold in the room where the thermometer happened to be. The condition of the outside air must first be inferred from this by means of a table, and the freezing point itself cannot be determined with such great accuracy. Still, the effort is not wasted. From my observations mentioned earlier, I find the following. 1. In September, the thermometer in the room, compared with the one before the window, generally shows the same readings. 2. In October, the difference, taken in general, amounts to 3 to 5 degrees or more. 3. In November, it is 5 to 7 degrees. 4. In December 5th to 8 degrees. 5. In January 8, 10, and sometimes even 12 degrees. 6. In February, it decreases again, so that it amounts to 4 to 8 degrees. 7. In March, it comes closer again to equality, which in April is almost completely restored. This concerns the thermometer's course in general, namely that the thermometer, disregarding the smaller daily changes, falls from October to January and from then on rises again. Yet it does not happen so uniformly. For besides the daily changes, there are also those in which the cold increases for several days and then decreases again. The thermometer in the room indicates these 2, 3, or 4 times less strongly than the one in the outside air, depending on whether they are stronger or weaker. Moreover, the thermometer by the window always shows these changes earlier, especially when they are sudden, because it takes time for the outside warmth and cold to penetrate through the masonry walls. Celsius speaks with amazement of what kind of cold it was when his Hawksby thermometer, on 11 January 1732, fell to the 124th degree, and yet this is only the 15th or 16th degree on the Réaumur scale, below zero. Such a cold will not seem very great to us, but we may assume at least 10 degrees more, thus the 25th or 26th degree Réaumur below zero, if we want to draw a conclusion about the coldness of the outdoor air. See 173, Prop. 5. That would then indeed be a cold that can be called extraordinary in Sweden. Section 176, the entire yearly variation of the thermometer in a room, is generally speaking about 1/3 smaller than in the open air. In the greatest summer heat, the readings scarcely differ from one another by a single degree, so that the former stands at the 24th or 25th degree. In winter, on the other hand, the difference is much greater, so that when the thermometer in the open air already stands 10 degrees below the freezing point, the one in the room has scarcely yet reached the freezing point. From this one sees how, where one does not have the scale itself, one must nevertheless make a correction if one wants to infer the condition of the outdoor air from the thermometer in a room. On the Réaumur thermometer one can write, A 24 degrees, greatest heat E13, moderate 7, frost 0, great cold I have already said. 159 that the Hawksby thermometer had this arrangement. One also finds Réaumur Hawksby. 27, 0, greatest heat 18. 25, warm 11, 45, moderate 7. 56, frost in Naples, E44. 65, stronger frost that Hawksby sets the greatest heat higher can be explained if one assumes that he took account of rooms that have the midday sun. If one assumes that he took account of rooms that have the midday sun, and preferred to set the degree rather too high than too low. Likewise, he sets on other spirit thermometers used up to now its frost point somewhat lower, because a slight frost falls only in the morning hour. Such, however, was the case at Naples. 177. I have found several observations on the severe winter cold of the years 1709 and 1728, in which the scale of the thermometer must be clarified by considerations of this kind, partly because the division is unknown, partly because the thermometers were not hanging in the open air but in rooms. Among these observations belongs Wolf's dissertation De Hema 1709. He does indeed give the degrees of his thermometer, and the weather observations are not incorrect from day to day, but he says absolutely nothing about the degrees of summer. On the 19th of October 1708, he found his thermometer in the room at minus 36 degrees, and when he put it to the window, it fell to minus 65. This may have been the first onset of frost. On the 26th of January 1709, when after the severe cold a thaw set in, his thermometer in the room showed minus 72 degrees. This degree may have differed little from the actual freezing point. If the degree for summer heat had also been given, a fairly exact comparison could still be made. In April 1709, Wolf's thermometer rose to 0 degrees, that is, to the degree of solar warmth. From this, it follows that about 7 Wolf degrees amount to 1 Réaumur degree. And according to this ratio, on Wolf's thermometer, the 100th degree of warmth would be equal to the 25th or 26th Réaumur degree. I have looked through Wolf's remaining printed writings to see whether any later report might be found about the thermometer he used in the winter of 1709. And in the 10th volume, pages 63, 65, 67, I find that he complains about the weakness of a large old thermometer which he had acquired in 1708. He complains that it no longer wants to rise properly to the higher degrees of warmth. But this now probably means nothing more than that spring and summer were not particularly warm at that time. Nevertheless, it follows from this that Wolf's thermometer in some preceding summers really rose to the higher degrees, and consequently its scale, which includes 100 degrees of warmth and 100 degrees of cold, was not badly chosen. This was all the more remarkable because there were thermometers that had one and the same scale, and yet their behavior was quite different. And we would be missing little if, with its 100th degree, Wolf's scale would place the boiling point at 72 or 73 degrees. In my own experiments, I compared Wolf's thermometer with the 2 Fahrenheit thermometers whose scale divisions I have already described in the preceding section, pp 110, 112. But what I learned from this comparison is as follows. Wolf not only failed to observe correctly, he also used somewhat different degrees, and I present the comparison here only to show that the 2 Fahrenheit thermometers agree with each other, but do not agree with his old large Florentine thermometer, and that his readings are lower. This, however, is simply because the larger thermometer bulb and tube warm up more slowly. Wolf's observations are arranged in the following table. Fahrenheit P. 112. Wolf, the mean 8.2, Seichi 34, 64, 8.3, Chh 65, 65, 64, 62, 64, 62, 64, 64, 65, 62, 62, 69, 57, 69, 65, 62, 60, 52, 52, 51, 52, 10.1, Chh 41, 49, 45, 47, 10.2, He 42, 45, 45, 10.2, He 45. This would correspond to the degrees of the Fahrenheit thermometer. I then took these as abscissas and the numbers of the third column as ordinates and made the drawing. The points of the ordinates do not lie entirely in a straight line, yet in such a way that a fairly straight line can be drawn through the point. And I found that Fahrenheit 8.335 corresponds to Wolf 71 on Fahrenheit 1030 Chi 43, corresponds to Wolf 41 on coincide. Accordingly, 3 degrees on Wolf's scale correspond to 1 degree on Fahrenheit's. And from this, it follows that on Wolf's thermometer, 74, of other spirit thermometers that have been used up to now, the freezing point is, according to Wolf, at 0 on the Fahrenheit scale, or at 25.4 degrees. Thus, Wolf's 100th degree is exactly the same as the 26th degree on Réaumur's scale. This comparison therefore shows that the previously stated agreement is of little or no value. Wolf, in 1721, certainly did not believe that what he then presented as proof against the division of the thermometer would later be used not only as proof for that division, but even for determining the ratios. So much depends on the method of making comparisons. It is only a pity that in 1709, on the 11th and 12th of January, when the cold was extremely severe, the spirit fell into the bulb. We can therefore say nothing more about it, except that his thermometer stood at the 114th degree of cold, which corresponds to 6 degrees below Réaumur's 0. Wolf had indeed had some windows open so that the air in the room might take on the cold of the outside air, but that did not help much. And so the cold in the open air may well have been 10 to 12 degrees stronger. That is, it may have been about 18 to 16 degrees on the Réaumur scale. I have compared all the spirit thermometers mentioned so far with the Réaumur mercury thermometer, and by doing so, I have made a general standard from them. Nor do I see why one should choose any other. For some time now, Fahrenheit, Delisle, and Réaumur have gained the upper hand. People have also become accustomed to setting up the Fahrenheit and Delisle thermometers as those made of mercury, whereas the Réaumur thermometer is mostly made of spirit and has therefore brought its own division into use. In the end, Réaumur himself, without intending it, and by a fortunate chance, arranged the division so that his spirit thermometer agrees with his mercury thermometer in the region of the freezing point. If one begins, see 131. If one begins, as has been done in Sweden, Rome, and England, to indicate the boiling and freezing point of water as 100 degrees, because in such useful matters one generally likes to introduce a decimal division. Then this departs from Reaumur only insofar as one assumes that his thermometer is made of mercury. For one must then set the spirit 0 between freezing and boiling water at 102.6, and consequently the lower barometer at 100 Reaumur degrees. Moreover, Reaumur's degrees fit very well with weather observations and are easy to understand. For one had -20, the most severe winter cold, -15, cold with settled snow, -10, strong winter cold, -5, slight winter cold, 0, freezing water, warmth, +20, ordinary summer warmth, +20, ordinary summer warmth, +25, great summer heat, +30, the heat of the dog days. Section 180. Custom also varies greatly, moreover, in the use of thermometers with respect to their different scales. It will therefore be best if I set down all the scales, those that are of some importance, on a single engraved plate, and in doing so take account of the difference as to whether they are of air, mercury, spirit of wine, or linseed oil. Since most are spirit thermometers, I have made the degrees on these equally large. The unequal degrees of air, mercury, and linseed oil had to be retained, so that the degrees of a single liquid would everywhere lie on the same parallel lines. I also, as far as possible, indicated on each thermometer the observations made with it. Among these, I have especially noted the following: 1. Boiling water. 2. Melting wax. 3. The warmth of the body. 4. Cellar warmth. 5. Freezing water. Frozen ice or snow. And through these degrees I have drawn parallel lines so that on those thermometers with which they were observed, they can be compared with one another without all measures having to be compared among themselves. Above each scale, it is noted of what material the thermometer was or must be if the scale is to apply. At the bottom is the name, together with the section number, which can be consulted to find more information. Section 181. In this plate, the Reaumur thermometer appears in 3 forms. First, of mercury, and this counts 80 degrees from freezing to boiling water on other spirit thermometers used up to now. 2, on spirit, this one likewise counts 80 degrees. It is the one that Reaumur, I believe, claimed to have made, though he did not in fact make it. Deluc, however, did make it, and only with the intention of showing, for 1 degree, the comparison with the mercury thermometer and the most different subdivisions of the scale. For that purpose it may serve. Beyond that, I would not recommend it, since one already has enough different divisions anyway. 3, also on spirit. This is Reaumur's own, and it coincides near the freezing point with the mercury thermometer. The 3 spirit thermometers that are presented in the first, third, and second column above P124 belong in the comparison table 182. I have drawn the air thermometers of Ammontons, Crucius, and Polenia according to their descriptions, without dwelling on the fact that for the expansion of air in freezing and in boiling water, they yield different ratios, P89. The latter two use their thermometers only for weather observations, and so the higher degrees do not occur for them at all. Ammonton's, by contrast, extends his scale up to the heat of boiling water. But his procedure is so compressed that slight inaccuracies could easily creep in, and for that very reason it happened that his thermometers did not all turn out equally well. 8th section, thermometers for particular purposes. Among the thermometers that are designed for particular purposes, the Ammonton's thermometer belongs here as well, because Ammonton's was really concerned with being able to determine the true degree of warmth, or its strength, in equally dense air. This aim was undeniably very important. Ammonton's conclusions are also very correct. Wolf already included them in his Elements in 1709, and since then they have always been used. Only he did not want the conclusion from degrees of warmth in the air to degrees of warmth in water to be regarded as absolutely necessary. And in view of the ambiguity of the word warmth, he was not entirely wrong. Besides the thermometers already mentioned, others can still be devised for special purposes. To these belongs the thermometer divided by joules for use in the field of weights and measures, CP 160, as well as those by Fowler and Renard. Yet with these one really knows only the inscriptions in the scale, because the step divisions are quite arbitrary, pp 164, 165. It would also be much better if, instead of the names of plants, the summer warmth and winter cold of the countries were indicated where the plants are native and grow in the open air. Well, Monsieur de Luc is, as far as I know, the first who divided the scale for particular purposes. It had already been noticed by Amintons that, although heat causes the mercury in the barometer to expand, the same barometer height does not always indicate the same heaviness of the air. One can therefore conceive of a thermometer that shows the ratio by which each time the barometer height is greater or smaller than it would be at a certain degree of warmth. Monsieur de Luc sets the freezing point at 0 and assigns 6 lines of rise to the degree of boiling water. Each of these 6 lines he divides into 16 parts, and thus obtains 96 parts, each of which amounts to 1/16th of a line, so that with this thermometer, one can just as easily determine how many 1/16ths of a line the barometer height must be increased or decreased because of the difference in warmth. For barometer heights that differ noticeably, a further correction must also be made, which is easy to devise and to which others have already paid attention. I mention this only by way of explanation. The said 6 lines are more than one finds in Delisle and other authors, where for mercury the expansion from freezing to boiling water is only 1/200, and therefore with a barometer height of 336 lines amounts to only 5.04 lines. The other thermometer that Monsieur de Luc divided for special purposes concerns the change in the density of the air brought about by heat under the same pressure. Here, however, one must necessarily take this into account if one wishes to determine the heights of places by means of barometer readings. Monsieur de Luc uses all his observations for this, and works through them again with much effort and diligence. Finally, he finds that, under the same pressure, the air expands by 1/173 of its volume. When the Réaumur mercury thermometer rises by 1 degree, this holds for the difference between freezing and boiling water, 80 degrees or 4,000 parts. And thus, it corresponds to the air pressure at which water freezes, namely 1,000 parts, and to that at which it boils, namely 1372 parts. I've taken 1370 as a round number, C89. De Luc therefore divides his thermometer in order to obtain somewhat larger degrees between freezing and boiling water into 1372 minus 186 parts. In doing so, he uses Aminton's hypothesis and assumes that the expansions of air and of mercury are in proper proportion. But since one finds from other experiments that the expansions of mercury do not everywhere, though very nearly proceed in equal steps with the degrees of heat, this must also be the case with the expansions of air. And then, with correct application of Aminton's doctrine, it would follow that the air thermometer does not merely indicate the arithmetic difference of warmth, but the absolute ratios of its degrees. Mr. de Luc did not wish to concede this to Mr. de Isaac 187. Mr. de Luc further relies on the astronomical refraction, which differs at different states of the barometer and the thermometer. Tables already exist that give the improvements. And indeed, one can attach to both the barometer and the thermometer a little step ladder that immediately indicates the correction to be made in advance for the refraction. But the theory must first be improved because besides gravity and elasticity, one must also take account of the density. Ninth section. Some remarks on the grounds of dividing the thermometer scale, 188. People have now pretty well agreed to take the degrees of freezing and boiling water as the basis for dividing the thermometer. And so only the question remains, which degrees are to be examined more precisely? In determining the first degree, people were not entirely agreed whether one should use freezing water, water beneath the ice, melting snow, and so on. I do not find that the difference is noticeable unless one intentionally makes it large. One can indeed make it quite large because the water does not freeze instantly, nor do ice and snow melt instantly, and because the thermometer likewise does not instantly assume the degree it is supposed to reach. If one places a thermometer in the greatest cold, water that has already cooled down to the point of freezing, then one notices if one puts in crushed ice or snow that is 10, 12, or more Réaumur degrees colder, the water will not freeze at once. and yet it will be much colder than is required for the desired freezing point of the thermometer. Again, if one sets a thermometer that has just come directly from a warm room into a vessel of water that is just about to freeze, then, in severe cold, one will see the water begin to freeze on the surface, while the thermometer has not yet even taken on the temperature of the inner water. If the vessel is large, and one brings it full of water from the warm room, then in severe cold the surface will freeze, while the inner parts still retain noticeably more warmth. If one wishes to avoid such uncertainties, it is best when carrying out the experiments to bring the cold to the point where it's just about to freeze. One should take water that has already acquired the necessary cold up to freezing. One should likewise let the thermometer first assume this degree so that it does not introduce into the water a warmth or cold that it does not have. It will therefore be good if the thermometer has already been underwater for some time and its surface is frozen. The more slowly the water freezes, the more reliably the experiment proceeds. That one should not take much water is self-evident, and likewise that the water must not be salty, because salty water requires more cold to freeze than pure water. In setting the other degree, namely that of boiling water, I've noticed a variability that depends on the height of the barometer. One finds that when the barometer stands 1 inch lower, boiling water has about 2.5 Fahrenheit degrees less heat. To determine this small difference more precisely, barometer and thermometer were taken up high mountains, where the barometer was many inches lower. In the Memoire de l'Académie de Paris for 1740, I find that Mr. Lemonnier at Perpignan, with the barometer height at 28 inches 2 lines, and on the at Canigou, with the barometer at 20 inches 2 lines. The experiment was made, and on the mountain, the boiling water was found to be 15 degrees on the Réaumur scale, less warm. The difference in barometer height amounts to 8 Paris inches 30 lines, and the 15 degrees on the Réaumur scale are as much as 18 degrees on the Fahrenheit scale, or 8 degrees on the Celsius scale. In the years 1760 and 1770, Abbé Fougeres found the heat of boiling water as follows. At Bordeaux, 80 degrees Réaumur, barometer 28 inches 0 lines. At Barrages, 77.34 degrees, barometer 24 inches 3 lines. On the Pic du Midi, 72 degrees, barometer 20 inches 7 lines, Dol 192. But in this investigation, no one has taken more trouble than Mr. Deluc. His Réaumur thermometer shows 80 degrees for boiling water, when the barometer stands at 27 Paris inches. From his numerous observations, it will be enough to cite the following: 1770, 2 July at Beaucaire, barometer 28 inches 5.1 lines, thermometer 81.09. 2 Augie, at Oriol, barometer 27 inches 11 lines, thermometer 20 at Geneva, barometer 25 inches 11.4 lines, thermometer 79.9 in 1617. Grange des Arbres, barometer 24 inches 10.6 lines. Thermometer 78.221, Grange des Fonds. 22, Grasse Chèvre, barometer 22 inches 11.9 lines, thermometer 76.5425 Augier, Grenoble. Barometer 20 inches 4.9 lines, thermometer 73.94, 25 Septi, Glacier du Bois, barometer 19. I have plotted the barometer heights as abscissas and the thermometer degrees as ordinates, and found that the points determined in this way deviate very little from a straight line, and that one may therefore, for each inch of barometer height, reckon 0.9 degree on the Réaumur boiling point thermometer. This is more than sufficient for ordinary use. The straight line that I have drawn through all the points gives some remarks on the grounds for dividing the thermometer scale. Thermometer, 29 inches, 81.8, 28, 80.9, 27, 80, 26. 79.19, 72.8. Mr. Deluc further believes that above boiling water, he could maintain a more rarefied space, and says that the water then took on only 65 degrees of warmth. But when it was heated again, it rose to 89.8 degrees. Yet, after more air had been drawn in, the heat of the same water at a barometer height of 27 inches fell again to 80 degrees. These are 3 different degrees, of which only the first 2 can be compared with one another. They give 89.8 minus 65 equals 24.8 degrees difference. And if, In this case, the water was as rarefied as air. Then these 24.8 degrees correspond to a barometer height of 27 inches. That yields 0.91 degree for each inch and agrees exactly with what my straight line gives. It therefore follows from these observations that the pressure of the air when the barometer stands at 27 inches increases the heat of boiling water by 24 to 25 degrees on the Rheum or mercury thermometer. As for Mr. Deluc's theory on this matter, I do not find it necessary to linger over it here. He begins by denying the air pressure any force to keep the water from boiling, and maintains that, in order to bring it to boiling, a greater degree of heat is required. I will not take up that theory. Fifth chapter, Hydrostatic Thermometers, 194. The fact that heat expands bodies has the consequence that bodies become lighter through warmth than through cold. So that, for example, a cubic inch of water weighs less at a higher temperature than at a lower. If this difference were more noticeable in water than it is in most bodies, people would long ago have tried to estimate degrees of heat from the change in weight. Yet the small difference does not prevent one from thinking along these lines. It would only be necessary to determine it with greater accuracy. Now, the means of investigating the specific gravity of bodies are already so well known that they can be applied to indicating those degrees of heat, which for present purposes are the most useful. I shall mention them only insofar as is necessary, so as not to take up the space required for the matters at hand. To this end, I shall begin with liquid substances. To determine changes in their weight, one may take a glass bulb or some other glass vessel with a narrow neck and fill it with the liquid to be examined, then seal it. The neck must be narrow so that one can determine more precisely the height at which the liquid stands in it, and so that any error one might make in determining this height produces only a small difference in the weight. If one wishes always to keep the same volume, a mark must be made on the neck so that the glass can always be filled up to the mark. 195. For such determinations, glass is the most suitable material for several reasons. For because of its transparency, one can see without difficulty whether the liquid stands exactly at the mark made on the neck. Further, it is attacked least by other liquids, especially if it is hard glass. And finally, it expands very little through heat, according to Zerbert's experiments, P. 45. The expansion that glass undergoes from freezing to boiling water amounts to only 1 part in 1157 of its length, which corresponds to 1 part in 3001 of its volume. One can therefore judge whether or in which cases it is necessary to take this into account. Hydrostatic Thermometers, 196, on the 19th of July, 1765. I filled such a glass with boiling water in the boiling water itself. It goes without saying that at first I had to hold it above the steam of the water so that it could gradually take on the heat, otherwise it would easily have burst. It also goes without saying that I did not dip it into the boiling water with my hand, but used tongs for that, or else wound a wire around it. When it was now full of boiling water, I drew it out with its neck upright, dried it on the outside with a damp sponge and set it, without any further covering, on a balance so that it would evaporate as little as possible until I had weighed it. For this purpose, I had already placed so much weight on the scale beforehand that only a few grains and their decimal parts still needed to be added. The water weighed 169.4 grains. I then let it cool until it had reached the warmth of the outside air. In doing so, the water fell in the neck of the glass, partly because a little evaporated, partly because a little evaporated. After this, I filled the glass again with other water, which likewise had the warmth of the outside air, completely full, and now found that it weighed 174.8 grains. The Nuremberg thermometer then stood at 19 grains. This is the amount of grains of the warmth of the cooled water. Now, since the expansion is in inverse proportion to the increase of weight in the same volume, it is as 169.4 to 174.8, consequently, as 31 to 32. The expansion of the glass amounted to scarcely 1/450th part, and is therefore far too small to need to be taken into account. One sees without difficulty that, if one has a glass actually intended for this purpose, one can, without any trouble, fill it at different seasons of the year with any desired liquid substances and weigh them. in order to determine their expansion from the weight, for if the materials already have the warmth of the outside air, no other precaution is needed. It also goes without saying that one must have a thermometer nearby, so that, besides the ratios of expansion, one can also state definite degrees of warmth. And since certain materials, such as vinegar, brandy, and the like, are not always of the same quality, it is likewise clear that one must take these differences into account. Eisenschmidt has made use of this method in order to determine the specific gravity of many liquid substances in winter and in summer. In summer, in his little book, Ide Ponderibus et Mensurae, he states the weight of a cubic zoll without describing how he determined it. The weight is given there in whole grains and is therefore not exactly specified. Likewise, he leaves the degrees of cold and warmth undetermined. He speaks to me of summer and winter, but since he generally had much accuracy, I have reason to suspect that he indicated the degrees of both summer warmth and winter cold. How great the latter may have been, I cannot yet determine quite precisely from his table. Among the metals that he weighed in summer were also silver and mercury. These two metals were at the time of the winter cold still fluid, and had not frozen. In Hingen, spring water and brandy had not frozen, 199. On the 9th of February, 1769, I had the Baumstark thermometer set up in front of the window, where it was freezing. The thermometer stood 3 Reaumur degrees above the freezing point. I then brought it into the room. The mercury thermometer rose a few degrees, without the spirit thermometer rising at all. In the evening, in front of the window, the cold stood at 0. I set the Baumstark thermometer there, and it did not want to freeze. This is what I find recorded among my observations. It follows from this that at the time when Eisenschmidt made his experiments in winter, the cold can hardly have been much above the freezing point. As for the degree of summer warmth, Eisenschmidt's table likewise provides circumstances by which it can be fairly well determined. He used a troy weight of 16 ounces, each ounce divided into 8 drams, and 1 dram into 72 grains, so that 9,216 grains make a pound. In such grains, a Paris cubic zoll of mercury weighed in summer 4,170, in winter 4,190. This now serves as the first thermometer. We can set the winter cold at the 148th degree of the first scale. This gives for the expansion of the mercury in the first thermometer 10,000 minus 148 equals 9,1852 degrees, 4,107, and 10,000 minus 9,1899 equals 101. Consequently, the summer warmth reached the 101st degree of the first scale, or the 91st Fahrenheit degree. This indicates the greatest summer heat in a room exposed to the midday sun. I have not included the table of the ironworker Fahrenheit here without reason, and it is always worth the trouble to know that in his experiments the winter cold and summer heat differed from one another by 47 degrees on the Lyell scale, or 57 degrees on Fahrenheit, or 25 degrees on Reaumurs. The table itself is as follows, except that the weights are expressed in grams, and an additional column has been added showing the proportion by which each material must expand. For 1 Paris cubic inch of mercury, weight in summer 4,170, weight in winter 4,190, ratio 563, 575, 1.0213, 393, 398, 1.0398, 1.07, spirit of sun, spirit of urine 405, 413, 1.019, 537, 1.03. Almond oils frozen in 341, sweet almond in 47, 334, 1.0 CL water 447, 302. Spring water 371, 374, 1.0081. Distilled water 368, 368, 302. Hamburg reports in the memoirs of the Paris Academy for 1699 some similar experiments. According to these, the same measure of mercury, in summer 5,287, in winter fall 312, ratio 1.0746, 691, 745 spirit of wine, 713, 718, 723, 1.07. Whether printing errors have made the numbers incorrect, or whether Hamburg did not take the measures accurately, must remain undecided. The density of liquid bodies is also found by determining through experiments how much a heavy body loses of its weight in each of them. For this, one may use a glass sphere into which one puts as much mercury, lead, sand, and the like as is needed, so that it sinks in the liquids, yet still has a considerable part of its weight. One would have to make it without any irregularities, because otherwise one would cause the balance to give an uncertain reading. A short tube is left in the sphere, which is melted shut when the sphere is heavy enough. It must be hung from the balance on a fine metal wire and lowered into the liquid materials whose density one wishes to weigh. One must also see to it that no air bubbles remain attached to it. Since weighing in this way is somewhat troublesome, people long ago began to make it more convenient. It was found that bodies, which are lighter than all liquid materials, do not sink completely in them. The depth to which such a body sinks could therefore provide a means of determining the density of the materials. One only had to ensure that very small differences could still be observed accurately. This was achieved by making the upper part very thin. Those who work with glass grinding, barometers, and thermometers make such instruments, likewise made of glass, and sell them under the name of wine testers or beer testers. I had obtained such an instrument in 1750. Since I now wish to know what sort of scale it really followed, I undertook the following investigation. Figure 4 shows it, though not in its true size. The lower bulb C is not quite up to the mark. It begins to narrow toward the tube. The tube from E to D is charged with 25 grains of shot made of brownish glass, though 6 of the 25 are of milky white glass, so that they may be counted more easily. Before the instrument is placed in water or any other liquid substance, it is held upright and shaken, so that the shot may come to lie entirely at the bottom in C. I found that in well water, which had a warmth of 14 degrees Réaumur, the instrument sank down to the 42nd division at F. I then placed a weight of 10 grains on the ring at the top, in order to make the instrument sink further. With this, it sank in the water 18 divisions deeper, down to G. It follows from this that the space of the tube from F to G displaces as much water as 10 grains weigh. Since the instrument by itself weighs 193 grains, I could, by the rule of 310 grains, 18 divisions, each weigh 193 grains, 347.4 divisions. Conclude that when the instrument stands in water up to F, it occupies in the water just as much space as a tube would if it were 347.4 divisions long. Accordingly, I could take the first point E as the 343rd division, point F as the 347th, point C as the 355th, and point D as the 367th division, and thus calculate for each division the ratio of the volume that the instrument occupies in any. To find this volume in known measures, I calculated that 1 Rhineland cubic foot of water weighs 506 to 800 grains. Since the weight of the instrument is 193 grains, it follows that 193 grains of water fill the 1/1625 part of a Rhineland cubic foot, and therefore amount to 137 cubic lines. Thus, the bulb up to the tube at F must contain 1137 cubic lines, corresponding to the 347th division, C, or 206th. From this, it is then easy to determine that the volume of the tube from E to D amounts to 78 cubic lines, and consequently each division is to be reckoned as 2.27 cubic lines. I now placed the instrument, together with a thermometer, in water that stood on the stove, when it had a warmth of 48 degrees Réaumur. So the instrument sank to the mark H, that is 3T divisions, more than it had sunk in water at 14 degrees of warmth. Now, C 206, in P it is 347 divisions, in H 351. Therefore, for the difference between 48 and 14, that is 34 Réaumur degrees of warmth, the expansion of the water is as 347 to 351, that is as 1,000 to 110. I cite this only as an example. For such experiments, the tube ED would have to be much thinner, so that smaller differences could be noticed. But since the tube would then have to be longer, and to avoid making this greater length unnecessary, one has made use of other means. The instrument is made so that it sinks in the liquid matter. One intends to examine until D sinks in. But since in heavier matters it would not sink down to the tube, it is weighted with weights that are either hung below at C or laid on above. the stepladder remains as it is. It is the same as the previously stated calculation, 206, namely the space that the instrument occupies in the liquid matter. The weight of the instrument, together with what has been laid on above, makes up the weight of the matter whose space the instrument occupies, and thus weight and space are proportionally related. For example, the instrument sinks in water to F to 347 divisions and weighs 193 grains. If I lay 10 grains on top, it weighs 203 grains, and it sinks in the same water to G to 365 divisions, that is 18 divisions. Now, it is all the same whether one reckons 193 grains of weight for 347 of space, or 203 grains of weight for 365 divisions of space. This is for the case where the weights are laid on above, but if one hangs them below, they come into the liquid matter and are therefore less heavy in it. That changes the calculation. One can best proceed by using special weights and considering each, to begin with, as if it formed a mass together with the instrument. One then takes the test, see 206, separately for each of these weights to determine how much space must be reckoned for each division of the step ladder, e.d. 211. If one wishes to have such an instrument made, one begins by looking for a tube that is thin and everywhere of the same outer diameter. If the instrument is to sink from E down to D in substances whose specific weight differs by only 1/100th part, then the little spheres in the tube must take up to E 100 times more space than the tube from E to D. How large the spheres must be can then be determined from known geometric principles. It is also good if one does not make the lower sphere C larger than just enough to hold the mercury or the small lead shot that must be put into it to give the instrument the required weight. This can presumably be found easily from the known specific weight of such bodies. And the iron chemical balance, P211, is here of especially good use, 212. This instrument, considered as a thermometer, has the advantage that, besides the particular weight of liquid substances, it also indicates their warmth, and indeed without any delay. With other thermometers, one must wait until they have taken on the degree of warmth, and one must keep the substance at that degree of warmth for so long, because otherwise the thermometer does not reach it, since the substance cools sooner. In experiments, the air bubbles that readily cling to it must be brushed off. If metals and stones expanded more than they do through heat, then by weighing them in water, one could determine how much more or less they expand than water at the same degrees of warmth. And then one would only need to determine the expansion of water in order also to find that of the metals. But their expansion is so small that this method cannot possibly be used. Sixth main section, on the expansion of solid bodies by heat, 214. The extremely slight expansion of solid bodies by heat brings with it several difficulties. If one wishes to determine it precisely, one must take bodies of great length, so that the change caused by heat may be large enough to be measured. If one uses a measuring rod, there is the difficulty, if one wishes to avoid error, that the rod itself must not also expand from the heat, since otherwise one would find only the difference between the expansions. Delancey, who already recognized this difficulty in 1688, proposed other means, and in particular pendulum oscillation. These, however, depend on the true distance of the point of oscillation from the point of suspension and can easily be counted. But one must also take care that the duration of the oscillations is not altered by the driving force by resistance, and by the air's density not always remaining the same, so that one can attribute the observed change only to heat after subtracting these other hindrances. For this reason, people have preferred to reverse the question and to try to determine the expansion of pendulum rods by heat by means of other experiments, in order then to make use of it to correct the inequalities in the motion of pendulum clocks that arise from it. He found there in 1672 that a pendulum he had brought from Paris went too slowly each day by 2 minutes 28 seconds, and that he had to shorten it by 1 a line so that it would beat seconds. At first, it was feared that something else might have been disturbed in it. Therefore, it was brought back to Paris again with all care, and the concern proved unfounded. So, the cause was sought in the greater heat at Cayenne, and perhaps also in the thinner air there. These causes could indeed have some effect, and so it was to be seen whether they were strong enough to produce so great a difference. Picard found that an iron rod, which in winter cold was 6 feet long, lengthened at the fire by E line. That is, by the 1/375 part diet. Lahayer found that an iron rod, which in winter cold was 6 feet long, became longer in summer in the sun by E line. That is, by the 1 part 2. From this, he rightly concluded that one must not attribute the pendulum's irregularities to such great differences in warmth, and that Richter's observation must be explained on other grounds. Here, the uneven and flattened shape of the earth was taken into consideration. Yet, in France, people long remained unwilling to believe it, because they still hoped to uphold the Cartesian system of teaching, which was greatly shaken by this. 216. Some 60 years and more after Richter's experience, and thus very late, a new epoch began in France. Newton and his followers undertook new investigations of the expansion of pendulum rods caused by heat, and in doing so, sought the utmost precision. Micrometers were introduced in order to determine the slight expansion more accurately, and the motion produced by the expansion was made larger and more visible by means of levers. The investigation became even more important when, in England, people began to assemble pendulum rods from different pieces of metal to see that the metal that expands more should serve to cancel out the lengthening of the pendulum caused by the metal that expands less, and thus, so to speak, to make it zero. 217. It will be enough if I present the results of these investigations in a table so that everything can be easily surveyed. I therefore set the length of the rod equal to 1 if it has the length of the Paris foot. Then the same rod, either in boiling water or wherever else it may be, can retain the degree of heat. The lengthening caused by this is given in decimal parts by the following table: iron, steel, copper, brass, silver, tin, lead, gold, glass. From this table, one sees that Herbert gives a decidedly greater expansion than Muschenbroek. This gives reason to conclude that, in the instruments, there must have been some circumstance that caused this difference. Bouguer gives less than Muschenbroek. On the other hand, Dijon, Condiment, and Berthad give more. Among these experiments, there are some in which the numbers had to be found by calculation, namely those in which one passed from the smaller to the greater by a leap. One measured the expansion only for 10 degrees Réaumur, and then increased it by calculation until one believed one had obtained the expansion from the freezing point to the boiling point. One also placed thermometers and rods in the sun, where the thermometer rose 10 degrees, just as if the rods too had acquired 10 degrees of heat, although size, shape, material, and color all remained different. In Franzens Staatsgeographie I find an experiment that Louis carried out on April 27, 1753, at Marienburg with an iron rod 20 feet long. Early in the morning, he placed it in the sun, together with a thermometer, and noted the lengthenings it received from the sun's warmth up to 11 o'clock, recording the thermometer's degrees very often as well. The thermometer is said to have been corrected according to an old Fahrenheit scale, CP11, and to have been improved in Berlin. On that scale, the heat of boiling water would be I90, and the cold of ice mixed with sal ammoniac would be 90. In the morning, it stood at 11 degrees at 11 o'clock at 114, and in the evening before 5 o'clock at E46 degrees. The degree in the midday sun thus reaches 33 or 34 degrees on the Réaumur-Muschenbroek scale. Presumably, the warming of the fastening to which the thermometer was attached contributed to the strong heat shown by the thermometer. In any case, it is quite certain that the iron rod became warmer, and it is at least not impossible that it could have melted immediately afterward. We may therefore set the heat of the iron at 11 o'clock at no less than 142 degrees on the Fahrenheit scale, and since the morning warmth was only 52 degrees, the rod was warmed by 90 Fahrenheit degrees. Now Louis found that it had lengthened by 1/2,500. From this, it follows that from freezing water to boiling water, it must have expanded by at most 1/1250, or 0.008 of its length. This determination comes closest to that of Muschenbroek, P217. As for wood, Celsius found an exception. He had wooden rods in a room that was warm to 14 degrees on the Réaumur scale. When he put them in a cold of minus 14 degrees, he found them not shorter, but longer. Now we know that water expands when it freezes. We also know that wood, especially in the cold, draws moisture into itself. From this, the seemingly contradictory result can easily be explained. In the cold, the wood did not truly expand. Rather, it swelled. That it expanded so little may well have come from the fact that cold and moisture counteracted one another. This is noted here because in other cases, too, one must distinguish hygrometric effects from thermometric ones. Kraft and others have cited woods, plants, roots, leather, intestines, bones, and so on, as examples to show that heat does not expand all bodies. If by this they mean only that one must not speak of the expansion of bodies by heat without regard to other effects of heat, then it is entirely correct. The examples cited concern such bodies from which heat drifts. With that, the swelling caused by moisture ceases, and so it can easily happen that the bodies, as they dry out, contract far more than they are expanded by heat. 7th chapter. Thermometers for solid bodies. Liquid substances take on the shape of every vessel into which they are poured, and therefore it was easy to make even the slightest expansion they receive from heat visible by enclosing them in a bulb with a narrow tube. One also made use of the advantage that one could convert the expansion that proceeds in all three dimensions of space, that is, in length, breadth, and thickness, into an expansion proceeding only in length, and thus make it 3 times more noticeable by expansion, even if instead of a bulb with a narrow tube, one wished to use only a cylinder. Since they expand only very little, this increased the difficulty of making thermometers from them. Yet there was no small need for such thermometers, especially for those that could be made of iron, because their use could extend up to the heat of glowing iron. One had to be content with proving expansion by heat, by means of metal rings and balls, made so that, when cold, the balls fit exactly into the rings. When the balls were heated, it was found that they no longer fit, but were too large, and therefore remained above the opening, outside the ring. From this, one could determine in some measure how much they had expanded. But since measuring takes some time, the ball in the ring it touches cool down in the meantime, and for both reasons one finds the expansion smaller than it was at first. 224. Heat causes some bodies, for example wooden laths, rods, boards, and to warp so that they bend, and this necessarily happens as soon as they expand more on one side than on the other. But since in wood, leather, horn, and the like this warping is more hygrometric than thermometric, it cannot be used here, and all the less because with time it becomes quite imperceptible if one does not expose the wood to a strong heat or moisten it again. It has also been proposed in England that the unequal expansion first observed, and the curvature that results from it, could be produced in metals as well, if one had plates that were copper on one side and iron on the other. This could be achieved without soldering by means of rolling mills. Plates made of 2 metals in this way must be very thin. They are made narrow, but several inches long. Then in the cold they are bent so that the curvature is toward the side on which the iron, or in general the less expansible metal, is. The bending should be quite considerable, so that such plates could be used as thermometers. The idea is very ingenious, yet such thermometers do not seem to be of any particular practical use. Muschenbroek proposes making the expansion of solid bodies more visible by means of attached gear whips. The rod whose expansion is to be measured is clamped firmly at one end. In this way, he ensures that the other end, through expansion, moves lengthwise, and by means of a small rod fastened to it, drives the teeth of a small pinion, or even only the end of a screw. On the axle of the screw there is a large wheel with many teeth, which meshes with another pinion, on whose axle there is likewise a larger wheel with many teeth, which meshes with the third pinion, and so on. On the axle of the last pinion there is a pointer which, however little the rod expands, turns strongly and not imperceptibly, and on a dial indicates divisions proportional to the expansion, so that the latter can be calculated from them. For the motion of the pointer to occur at the very moment the rod is warmed, the pointer must be turned back far enough that all the pinions and wheels and the teeth that are to move one another touch each other. Moreover, the rod must be placed and the whole instrument arranged so that only the rod is warmed, so that the frame does not also expand, since otherwise one would find only the difference of the expansions. Muschenbroek devised an arrangement by which he could place 5 lamp flames under the rod, but instead of oil he burned spirits of wine. The flame is indeed somewhat more uneven and flickering than that of oil, but it does very little or no harm. Muschenbroek also arranged things so that he could keep the rod in boiling water and nevertheless observe its expansion by means of the pointer. In this way, he was able to determine very precisely how much rods of different metals expand when they are heated, from the freezing point up to the boiling point, and this expansion could then be compared with the expansion of other degrees of warmth. These higher degrees were really the purpose of the instrument, and for that reason it was called by Muschenbroek not a thermometer, but a pyrometer. With this pyrometer, Muschenbroek carried out a great many experiments, which he describes in his remarks on the experiments of the Florentine Academy. Among them are the experiments already mentioned earlier, 217, on the expansion of different metals when they are heated from the freezing point to the boiling point. He also reports the following, which are likewise noteworthy. He gives the expansion in degrees of his pyrometer. These degrees therefore change their meaning when the rod is made of a different metal. Since I shall keep the degrees as Muschenbroek states them, I have arranged the following table with several columns which must not be confused with one another. In each column, the degree of expansion is given that the metal has undergone from the freezing point to the boiling point. The number therefore corresponds to as much as 180 degrees of Fahrenheit, or 370 degrees of the air thermometer, if the former is reckoned from 32, the latter from 1,000 degrees, even if the degrees of expansion of the metals of mercury and of air do not proceed in entirely equal steps with the degrees of warmth. This does not prevent us from substituting other degrees for Muschenbroek's, in themselves arbitrary degrees, degrees that remain proportional, even if they are counted from a different starting point. For this reason, I have also added two columns that give the degrees of expansion or of warmth in degrees of Fahrenheit and of the air thermometer. Degrees of the pyrometer for iron, steel, tin, copper, freezing water, 32 Fahrenheit, 1,000 air thermometer, boiling water, 212, 1370, melting tin, 402, 1765, melting gold assay, 606, 2008, melting lead, 706, 29, 2 out of sand, 507, 2,402 iron still not glowing, 969, 2,926, bismuth melts, 1,051, 3,106 steel begins to glow, 185 glowing copper, 1512. 4,000 Muschenbroek in determining such high degrees of heat had Newton as a predecessor. From Newton's observations, as far as they have come to my knowledge, I have already presented above P 105, a table in which the degrees of the air thermometer are added. In it, one also finds the degree for melting tin, which can be compared with the one given here by Muschenbroek. For Newton, melting tin is 17,856. For Muschenbroek, it is the 17.65th degree. Newton says of this that the tin was not hotter than just enough to be able to flow. These degrees therefore agree very closely. Moreover, they may differ from one another, both because of differences in the tin and because of the difficulty of such experiments. The degree of heat at which a metal begins to glow is not easy to determine, especially with larger masses, because these do not melt all at once. With the semi-metals, it is even harder, because they must be heated very strongly if they are truly to flow, and even then they still remain in a very crumbly form. I mention this because Muschenbroek sets the degree of melting lead, and even more that of melting bismuth, very high when one compares it with that of melting tin. Bismuth melts at least as easily as lead, and only much more slowly. Cinnabar and borax remain fluid at a good red heat degree, like boiling mercury. Muschenbroek gives the 7.75 on his degree when he speaks of boiling or foaming fervens quicksilver. By this, however, he means that it is boiling up to the point of ignition. Among the degrees given by Muschenbroek, there is still the last one, which we can compare in some measure with the one that Robin found for white-hot iron, and which amounts to the 4.21th degree of the air thermometer, P92. According to the preceding table, Muschenbroek's glowing copper falls at the 4th degree of the air thermometer. Copper, in fact, does not become glowing much more easily than iron, even though melting iron requires far more heat than melting copper, since Robin's degree was found by means of the expansion of air, but Muschenbroek's by means of the expansion of copper. One may therefore conclude that the expansion of air proceeds in equal steps with the expansion of copper up to the degree of glowing copper. Muschenbroek's pyrometer has been copied by several lovers of natural science, and in part also altered. But I have no experiments known to me that were made with such copied or altered pyrometers, except those by Herbert's, which have already been mentioned in the case cited above. I have also already remarked that Muschenbroek's own figures seem to me to be more correct. Muschenbroek himself shows, through several comparisons, that his pyrometer cannot have any considerable error. So, even if it indicates a few degrees too high, the fault does not lie with the pyrometer. 8th chapter. Expansion of vapors by heat. Vapors are, in general, all so-called volatile parts that separate from bodies and float in the air. In particular, however, they are the subtle and for the most part watery parts, which are often mixed with earthy and salty parts. In the air, they occur in two forms, which otherwise differ only by degrees, insofar as truly dry air differs from moist air. The air is not dry because it contains little or no water particles, but because these do not cling to bodies. Yet bodies must be excluded that contain much salt, because the salt takes up the water particles and, so to speak, draws them to itself, even when these seem to flee other bodies. For this reason, one makes special use of a hygroscope when one wants to prove that even the driest air is laden with water particles. On the other hand, one calls the air moist when the water particles gather together and adhere to bodies in the form of small drops. The difference lies in the fact that now the force of attraction, now the force of cohesion, predominates. And since this does not happen by itself, other acting causes must be assumed. Among these is heat, and besides heat, the air itself, through its other changes, can also contribute a great deal. Since, in my experiments in hygrometry, I have discussed this matter in detail, it will be enough if I draw from them only the following. Dry air dries moist bodies all the more quickly, the drier it is itself. This does not really mean that dry air takes the moisture from bodies and absorbs it into itself. From this, it must rather be concluded, if one wishes to explain what experience and the experiments undertaken for that purpose have taught, that the quantity of water that evaporates is not determined by depth, but only by that portion of the surface that is touched by the air. The air continues to carry off water particles until it is, so to speak, saturated. Then even a slight decrease in its density and buoyant force may already be enough to prevent the air from holding all the water particles within itself, and to let some of them fall again, in the form of mist, dew, frost, snow, rain, hail, and so on. This moisture-attracting power of the air also shows itself with frozen water. Pieces of ice have been placed on a scale, and even in very cold air, it was found that they lost some weight every day. Everything melts faster in greater warmth. That warmth dries is as well known as that I need hardly say why one puts what one wishes to dry quickly in the sun, or by an oven, or over a fire. The question was rather to determine, by experiments, how drying or evaporation depends on degrees of warmth. In this regard, I found, according to the real mercury thermometer, that at a warmth of 61 degrees, the daily evaporation amounts to 67 lines. At 60 degrees, 65 lines. At 49 degrees, 39.5 lines. At 35 degrees, 17.5. And at 27 Paris. And from this, it follows that for each degree, the evaporation increases by more than at 0 degrees, 0 lines. At 10 degrees, 2 lines. At 20 degrees, 6. At 30 degrees, 13, at 40 degrees, 24. These experiments, which are described in detail in the section on hygrometry, I carried out with flasks on the warm stove. A thermometer stood in the water by which the degree of its warmth was determined. Now, since the humidity could not spread through the whole room, this was the reason why the evaporation was so remarkably strong. In moist air, it is, at the same warmth, much less, for when in summer, at an equal degree of warmth. I observed the evaporation from a flask filled with water that stood in the shade beside the thermometer. I found that the surface sank in 24 hours only 1, or at most 1.5 lines, and in winter at 10 degrees of warmth. Only a third, or at most a half, a line, at higher degrees of warmth than the so-called Réaumur scale, evaporation begins to become more violent. The air draws itself out of the little spaces within the water and rises upward in the form of small bubbles. As these air bubbles rise, they visibly grow larger, partly because they are compressed less, partly because they unite with the portions of air they meet on the way. Finally, they tear themselves loose from the surface and take tiny particles of water up into the air. Besides these, there are also little drops of water that spring upward from the surface, but because of their weight soon fall back down again. Thus the matter seems to proceed so that, at still higher degrees of heat, the water is changed into vapor ever more quickly and finally in an instant. One therefore observes with some astonishment that when water is poured onto molten silver or glowing iron, only at first does a rapid steam arise. All the water, however, that is not carried off with this steam remains lying on the molten silver or glowing iron, or rather skitters about upon it, and only very slowly dries up and seems to glow brightly. Leidenfrost, in his work, Gone Certain Qualities of Common Water, relates some experiments that can be performed with such glowing drops of water, and believes they could serve in place of a pyrometer, if one observes how long they take to dry up. For this one can use a spoon that is smooth and clean in every respect. Leidenfrost found that if the spoon had only the heat of boiling water, a small quantity of water, a drop that evaporated completely in 1 second required 6 to 7 seconds on molten lead. On boiling lead, it required 14 seconds, and on glowing iron, 30. And when it was extremely red hot, it required 35 seconds. Leidenfrost used a glass measure to It is obvious that one must compare drops of equal size with one another, for larger drops naturally need more time to dry up. Ziegler, in his treatise A Digestor Papinae, carried out similar experiments. But since he not only measured the time, but also determined the degrees of heat with his Fahrenheit thermometer, he raised the heat only up to 520 degrees. The principal values are as follows. Degrees on the Fahrenheit thermometer, seconds required for the water drop to dry. 520, 89, 500, and 80, 7420. 60, 380, 35, 360, 4, 350, 33, 220, 38, 210, 70, 208, 90, and therefore did not locate it at 212 degrees Fahrenheit. Ziegler, on the other hand, investigated more precisely and found it at 300 degrees. It is also likely that Ziegler used larger drops of water, for whereas at 520 degrees he found 89 seconds, Leidenfrost found only 6 to 7 seconds on molten lead and only 35 seconds on highly glowing iron. Since the water drops could not be measured so exactly, because they did not have exactly the same size, an irregularity arises in the times that were observed. Thus, for example, Ziegler found 60 seconds both at the 400th degree and at the 420th and 440th degrees. In order to recognize these irregularities more easily, in the figure I have arranged Ziegler's thermometer scale on the abscissa line, EB, but the times as ordinates. The ordinates of the times then lie in two fairly different curved lines, a C and DF, so that at the 358th degree of the thermometer, a completely new change begins to appear in the water drop. From that point on, the water becomes, and indeed very quickly, all the more fiery the greater the heat of the metal on which it is placed. It then ceases to cling to the metal, takes on a spherical shape, and glides over the surface of the glowing metal as if it did not touch it at all, U240, just as the curved line at GC between the somewhat irregularly placed endpoints of the ordinate seems not to differ much from a parabola. One could just as well regard it as a hyperbola or as another line that towards C gradually becomes asymptotic. The Leiden measurements also seem to indicate this, for they extend to much higher degrees of heat than are required here, because for glowing iron, they assume a time 5 times longer than for melting lead. And from the 300th Fahrenheit degree, the excess heat of the iron is probably also 5 times greater than that of melting lead. When the vapors of water are confined, heat gives them an expansive force by which they can burst even the strongest vessels, and the water itself becomes capable of softening the hardest stones. The Papen steam pot is well known in this respect. Yet, apart from Mr. Ziegler, no one, to my knowledge, has undertaken to determine by experiments the force of such vapors. He reports such experiments very fully in his treatise Digestor Papinae. He, so to speak, turned the steam pot into a manometric thermometer, and in this way he could determine the force of the vapors by the height of a column of mercury, which, besides the pressure of the outside air, counterbalanced the force of the vapors by its weight. At the same time, however, he also attached a Fahrenheit mercury thermometer in order to be able to determine the degree of heat. I will mention only one of his experiments here, from which it will be seen how different the force of the vapors is from the force of the air. In one experiment, the vessel remained completely empty, so that apart from the little container holding the mercury, which, driven by the pressure of the air or vapors, had to rise in the glass tube, there was only air inside. This air had a temperature of 59 degrees Fahrenheit. It was then heated up to 310 degrees, and in this way, its elastic force was increased so greatly that the mercury in the tube rose to a height of 17 inches. To these 17 inches, one must still add 27 inches for the pressure of the outside air. Thus, the total pressure is equal to that of a mercury column, 44 inches high. Consequently, it was 44 divided by 27. That is 1.63 times stronger than the pressure at 59 degrees of heat. Now, Fahrenheit, 59. Air thermometer, 1055. Fahrenheit, 310. Air thermometer, 1572. Therefore, 1572 divided by 1055 equals 1.49. This ratio is noticeably smaller than 1.63 and seems to indicate that the vapors contained in the air, when strongly heated, somewhat diminish the force of the air. This also suggests that in this experiment the elastic force increased more quickly than the heat did. Moreover, the thermometer did not show the degree of internal heat, because it stood in a vessel filled with oil, which indeed went down into the vessel but was open at the top, and therefore required more time to reach each degree of heat than the enclosed air did. In the other experiment, the vessel was half filled with water. In this case, when heated, more vapors arose. The result also shows that their force was very considerable. The initial temperature was about 50 degrees Fahrenheit. It rose to 289 degrees, and the mercury in the tube reached a height of 130. If one adds to this the 27 inches, one obtains 157 inches for the total pressure, which accordingly was 157 divided by 27. That is 5.815 times greater than the pressure of the outside air. Now together, Fahrenheit, 50, air thermometer, 1037 Fahrenheit, 289. Air thermometer, 1528.33, and one obtains 1528.3. Expansion of vapors by heat, accordingly. If there had been only air in the vessel, its force would have been increased by heat 1.74 times. The combined force of the vapors and the air, assumed to be 5.815, was therefore almost 4 times stronger than the force of the air alone at the same degree of heating. But this ratio depends only on the degree of heat the vapors had, that is, on the 289th degree on the Fahrenheit scale. At lower degrees of heat, the force of the vapors becomes very noticeably weaker. This is shown by the following table. This table is an extract from a much more extensive one, which could have been calculated from Ziegler's, because Ziegler observed the thermometer whenever the mercury had risen 5 inches higher. The lowest numbers are precisely those that were calculated above 243. They therefore serve to explain the whole table. From this it follows that at lower degrees of heat, the air contributes the most to driving the mercury upward, and that only when the water has 212 degrees of heat, that is, the heat of boiling water, does the force of the air through the force of the vapors increase up to double. From that point on, the force of the vapors increases very rapidly and becomes ever stronger. Yet this does not proceed in a perfectly uniform way, but somewhat faster. The difference, however, does not matter much, because the increase occurred very slowly. In Savory's machine in London, the vapors are cooled by poured in cold water, and then their elastic force immediately ceases. This table can, moreover, be used advantageously to calculate the force of the London machine, but one also sees that this force changes very noticeably according to the degree of heat. And since the If the steam boiler is not completely closed and the vapors are continually allowed to escape again, then the degree of heat will not be able to be assumed to be much greater than that of boiling water. The force of vapors or of moisture in cold is no less considerable, even though cold, considered in itself, is a diminution of the force of heat. But the force of heat is not the only one that is active in bodies. The cohesive forces are not weakened by it, and moisture itself can produce very violent effects. Wooden wedges that are driven into rocks and then moistened with water swell up with such power that the rock is split. The small amount of moisture that remains in trees during winter causes the trees to burst in the most severe cold, because the watery parts expand as they freeze. 247. This expansion by frost is very unequal in the various liquid materials. Arnold, who is known through his work De Virbus Nivi, carried out several experiments on this, determining by how many thousandths the frozen materials take up more space than they did before freezing. He found for water, 0.108 wine vinegar, 0.08 milk, 0.57 beer, 0.67 must, 0.07 for further for distilled water of roses, 0.0 eyebright, 0.08 bright, 0.8 eyebright, 0.1 Melissa, 0.08, 0.0 Melissa, 0.1 Melissa, 0. For saturated solutions of alum, 0.014 saltpeter, 0.096 borax, 0.083 white vitriol, 0.1 green vitriol, 0.1 green vitriol, 0.1. I have also found that saltpeter does not freeze in a single solid piece, but becomes flaky ice. The increase in volume when water freezes therefore arises because the particles of ice assume a three-sided arrangement from which hexagons and rhombi and even elongated parallelograms can be formed. In this way, larger spaces remain between the particles. Now, since the particles of ice do not of themselves fall into such an arrangement, a force is certainly required for it. This force may be very small in each individual particle, but its total, when reckoned over large surfaces, is always great enough to produce the remarkable effects. Much also depends on the manner and speed of freezing. If the surface has already frozen before the inner parts have cooled sufficiently, then between the ice, which gradually builds up, many larger and small bubbles of ice, which are full of air and in part perhaps even completely empty. Because of such bubbles, the ice becomes lighter than it would be without them. Section 248. As for the expansive force of ice, many experiments have already been made on it. Stones have been split, thick iron pipes and inner vessels have been burst, and even an iron bomb has been torn apart. Yet this only proves in general that the force is very great. The Florentine Academy burst metal spheres, one of which, made of brass, had a considerable thickness. From the figure, which, as far as I can judge, represents this sphere life-size, I find the outer diameter to be 29 and 3/5 lines, and the inner 13 lines Rhineland measure. Muschenbroek, in his notes on this, calculates the force required for the tier at 27/1720 pounds. The calculation is not fully clear. Presumably, it is the force with which the sphere would have had to be torn straight outward, and thus the force with which a brass rod 2 inches thick and 2 inches wide, or 4 square inches in cross-section, would be torn apart. That would therefore be equal to a pressure of about 460 atmospheres. Hales, or rather Buffon, since he corrected the former calculation, finds in the bursting of such a bomb a pressure of 1550 atmospheres. Yet, because cast iron breaks more easily than forged or wire-drawn iron, something must be deducted from this. Pyrometrie, or on the measure of fire and heat. Third part, on the warming and cooling of bodies. First chapter, communication of heat. Section 249, the complaints, repeated in the preceding century and still repeated in the present one, that thermometers do not instruct us about the true degrees of heat, that their divisions are arbitrary, that one does not know how the first beginning of counting the degrees was made, and that even if one did know this, it would still not be settled whether equal degrees of expansion also indicate equal degrees of heat. All this could more readily discourage further investigations than encourage. Yet the last of these uncertainties seemed to me capable of being removed by a few external clarifications. It came down to finding a means by which a thermometer could be made to receive equal amounts of heat at equal times, and then to see whether it would always expand by equal amounts as well, section 250. Such a means seemed to me to be the sun, when it shines from a completely clear sky and in calm windless weather at midday. I chose this hour because the height of the sun changes very little. On the 1st of June 1751, and I placed the spirit thermometer as it was in the midday sun in order to write down the rise of the spirit every minute. But I found already after the second minute that the expansion began to become smaller, and this became more and more evident during the 14 minutes for which I continued the observation. The spirit rose in the first minute by 1.5 degrees, but in the 13th minute by only 2/3 of a degree. It was now obvious that this inequality could not come from the sun, since the sky was equally bright, the air equally clear, and the height of the sun had changed only imperceptibly. Without difficulty, I therefore concluded that the thermometer received more warmth from the sun than from the air, because a thermometer hanging in the shade had, during those 14 minutes, risen steadily. Now, since I knew that a body in the air cools as soon as it is warmer than the air, it was very understandable to me why the expansion of the spirit did not increase by the same amount each minute, but remained more and more behind. The thermometer was again losing heat that it had received from the sun. I therefore also concluded that in each minute it lost all the more heat it had. This conclusion seemed to me to be very suitable for incorporating into the earlier calculation of heat, adding it to what still remained, and then seeing whether the total would be proportional to time. I therefore repeated the experiment and continued it for a longer time. I also set up others in which a warmed thermometer in the shade cooled only in the air. But I found that the experience did not quite agree with what these conclusions and the same calculations indicated. Yet since I regarded the conclusions as sufficiently correct, I examined the circumstances of the experiment more closely and realized that I had to take the thermometer away from the board, leave it open above, and also ensure that the air touched nothing. The experiment was repeated in this way and agreed better with the calculation. Some of these experiments I have made known in the Acts of the Helvetic Society, volume 2 and 51 times. Among the 4 propositions set out here, the one that is chiefly to be considered more closely is this, that the heat which a cooling body loses in each minute is proportional to the heat it has. This proposition is the first fundamental law of the communication of heat. It seemed so natural and unforced that, at the time, I did not think at all about whether it needed to be proved. When I later looked at Newton's Opuscula, I found that Newton, in the appendix to his treatise on the graduated scale, P 105, used precisely this law in order also to determine such degrees. Newton accepted the law as self-evident, without further proof, and used it to infer from it and from his experiments that the expansion of linseed oil increases in equal steps with the degrees of heat. These doctrines appeared in the Philosophical Transactions in 1701, and in 1703 they found in Amonton's a rather vigorous opponent. Amonton's first says that the Englishman does not express himself precisely enough when he says, the heat which a hot iron in a certain time imparts to the colder bodies that touch it is 1/4 of the whole heat of the iron. Here Amonton's wants the whole heat to be stated instead of the remaining heat, yet Newton surely meant nothing else. Amonton's repeats this criticism twice in succession. I suspect, however, that the second time he meant to say something different, namely, that since the first time he spoke of the remaining heat, the second time he intended to speak of the heat that is taken up, respectively. For colder bodies are warmed by warmer ones only insofar as the latter had more heat. Newton had not understood this in that way. It is clear from everything he says about heat and cold that he regarded the degree of freezing as the 0 degree of heat. He therefore brought glowing iron into cold air, and so that this air would not be warmed, he expressly says that he placed it in a spot where the wind flowed through uniformly, and thus continually brought fresh, equally cold air to the iron. Of the bodies laid upon the iron, Newton believes that they had absorbed the heat of the iron and then cooled down again with it, little by little. This is correct only if these bodies were very small, for large bodies do not become warm in an instant. 253. Amonton finally finds that, From Newton's statement, it follows that a cooling body would lose its heat in geometric progression. So that if in a certain time it lost 1/4 of its heat, then in each subsequent equal interval of time, it would retain only 3/4, then 9/16, then 27/64, and so on. But Amontons found many doubts, and these may have prevented him from letting the matter come to an experiment. Besides, he died not long afterward. Martin defended Newton's statement without making so many difficulties. Indeed, he believed it could be tested by experiments, and since he partly had the necessary, partly because he compared his own experiments with the proposition, he believed he had found that from Newton's geometric progression and arithmetic one must be subtracted. Barnard, in an inaugural dissertation delivered at Utrecht in 1772, found this alleged improvement good. On the other hand, it seemed less good to him and Newton's proposition more correct than the improvement made by Pereira. Richman, in the commentaries of the St. Petersburg Academy, Hartforns, gives Newton's experiments even more approval. Martin, moreover, is not satisfied with having only seemingly refuted Newton's proposition. He therefore pursues the matter further, and in Newton's Principia finds that a geometric decreasing progression occurs when a moving body suffers a resistance proportional to its speed. But it is surely enough that Newton could never have intended to apply this merely hypothetical, mathematically derived resistance to heat. By 254. If Newton's proposition is to be explained according to his way of thinking, and as far as possible proved, we must draw quite different conclusions. Newton calls warm only what we, according to our sensation, call warm, 105. And so understood, we attribute to every body the degree of warmth that we feel through touch, and we call a body warmer the more warmth we feel in it. That is to say, the more it warms us when we touch it, the more warmth it imparts to us, or at least causes us to lose less warmth. In this way, I had likewise imagined it in 1751, without knowing anything of Newton's proposition. But I found it advisable to rely on experience rather than to let myself be guided by conjectures, and therefore carried out the experiment mentioned above 251. These showed me at the time that the proposition held very accurately for spirit thermometers that were open at the top and whose bulbs were quite free. A body cools in the air insofar as the air surrounding it is cold. But I also understand at the same time that it is surrounded solely by air, and is not, for example, touched by other bodies. I understand this just as clearly when I say that a body in water or other liquid materials cools or warms. If, however, a body is touched by another so that it is not completely enclosed by it, then it is understood that if the two bodies have unequal warmth, warmth passes from the warmer into the colder. Yet the air or the space in which the bodies are located also plays a part. For this reason, the two bodies cannot be considered alone. The same is also found in regard to evaporation of several bodies, and one understands that the calculation thereby becomes more complicated than if only a single body were to be considered. Section 256. But such a single body, especially if it is large and of irregular shape, and does not have the same amount of heat in all its parts, can almost be regarded as though it were composed of several bodies joined together. The only difference is that its parts lie closer together than if several bodies merely touched one another. We must therefore take the spherical shape as the one that, during warming and cooling, exhibits the greatest uniformity. The difference in size, however, does make some difference, because heat flows out, and in more slowly. Thus, the surface of a warm sphere becomes cold, sooner than the parts that are nearer the center. And if the sphere is at first equally warm in all its parts, its heat must first pass from the middle outward before it can lose heat, according to our first fundamental law. We also see from experiments that, in the first minute of warming and cooling, an inequality commonly occurs, and that the law only begins to hold exactly in the following minutes. Toward the end of warming and cooling, such an inequality sometimes occurs again. Such inequalities at the beginning and at the end are smaller with smaller spheres, because the proper distribution of heat requires less time. I've also found that, since in the thermometer the mercury does not lie directly against the glass, but is separated from it by the spirit of wine, the transition of heat from the glass into the mercury, or, if you will, the friction between the warmth of the glass and of the mercury, produces a difference that is much smaller when, instead of mercury, spirit of wine is used. Section 257. This was noted only in order to make it at least understandable in advance that our first fundamental law cannot be applied quite additionally. But everything will become clearer when we consider this law and its consequences. To this end, I take the simplest case, where a small sphere in a fluid matter, say, the air, is cooled. The heat that goes from the sphere into the air disperses in it, so that nothing more acts back upon the sphere. And thus the air immediately around the sphere can at first be regarded as if it had only the warmth that it would, in any case, already possess. But this can only be regarded as constant so long as the cooling lasts. For if it does not remain constant, then special consid, when a sphere cools, what we really have to consider is only the heat that the sphere has in excess of the surrounding air. It is this surplus of heat, and it gradually leaves the body. I shall denote this surplus for any time whatever by psi. In the small interval of time, a quantity ADI leaves the sphere, and if K is constant, then according to the assumed law, D stands in a constant ratio to G. Accordingly, I set DI7, because if one does not keep one in constant, then D is proportional to GD. In this formula, 7 is of the same kind as height, and therefore represents a time of definite magnitude. One sees at once that by this formula, y can be represented by the ordinates of a logarithmic curve whose subtangent is 7, and whose abscissas are h. If for h0, and we have log 7, if then a body cools or is warmed according to this law, I shall, for brevity, use the expression that it cools or warms logarithmically, and I shall call the subtangent 7 the cooling or warming subtangent of the body. This subtangent represents the time in which the sphere would lose all its heat if it were to lose it in arithmetical progression, and in each small interval of time, it would lose just as much as it loses in the first ID. This subtangent is also in inverse proportion to what one may call the speed of cooling or warming, and one truly means this when one says, for example, that a smaller sphere warms or cools faster than a larger. Newton, on the occasion of the comet of 1680, had already taken this rate of cooling into account. He assumes that the quantity of heat which is in a body is proportional to the body's volume, whereas the quantity that escapes in each moment is proportional to the surface. Consequently, for spheres as for cubes, the time required for cooling is proportional to the diameter, because the volume, like that of a cube, increases as the cube of the diameter, and the surface, like the square, increases as the square of the diameter. Yet Newton suspected that something might detract from this, and he wished that someone would undertake experiments on it. Martin has now carried out such experiments, and from them found that Newton's idea is fairly correct. However, Martin's experiments are not simple enough for this purpose. He poured water into porcelain vessels and placed mercury thermometers in the water. Thus, there are porcelain, water, glass, and mercury, 4 bodies instead of 1. Newton's proposition can be regarded as correct in itself only if one assumes that the heat is evenly distributed within the body, but this occurs only with very small spheres. With spheres the size of heavenly bodies, to which Newton's attention was chiefly directed, a remarkable exception could occur. We see on the earth that the greatest summer heat penetrates only a little way into the ground, so that cellars maintain a remarkably uniform temperature throughout the whole year, with small spheres such as those of thermometers. The proposition can be accepted, and one may properly say that the cooling constant is proportional to the diameter of the sphere, or to the radius, provided the sphere is of any material, and is cooled or warmed in any fluid material. For bodies of other, yet not overly irregular shapes, one can in general consider, and if one does not fear a somewhat vague expression, assume that the cooling constant is directly proportional to the volume and inversely proportional to the surface, under the condition just stated of uniform material. In January 1773, when I filled some thermometer tubes with alcohol, I repeated the experiment once more with one of them before sealing the tube at the top, by which I had previously tested the law of logarithmic cooling. At the same time, I also wanted to determine how the cooling constant relates to the diameter of the sphere. I fastened the tube to a small wooden rod, on which there was already a step-like scale from a former there, was glued to the thermometer in such a way that the little ball did not touch the rod, but stood 2 inches away from it. I subsequently found that the scale divisions did not correspond exactly to the new thermometer, but that 29 degrees on it amounted to 31 degrees on a real mercury thermometer. This has no bearing here, where it is only the ratios that matter, and it is unnecessary to say anything further, since the real degrees are likewise arbitrary. I shall therefore not convert the observed degrees into real degrees, but will leave them as I observed them. I first placed the thermometer on the stove on January 30th, 1777, at 1 o'clock in the afternoon, at a time when the room had reached the maximum of its warmth. After it had risen to 39.4 degrees, I placed it by the window, where a little table stood on a book, so that the ball projected outward and touched neither the book nor the table. The room was kept closed during the experiment so that the air would not cool through the opening of the door. The thermometer, before which I remained seated quite still, I observed at the end of each minute and found that it fell as follows. Because the thermometer began to fall so slowly that the change of warmth in the room, which did not remain the same for 7 hours, could, in the further decline of the mercury, have had a noticeable influence. I shall therefore say that, with the warmth remaining the same, it would have fallen by y degrees in whole. Now it fell in the 28 minutes. 39.4 minus 16.2 equals 23.2 degrees. And the first half of this time, 39.4 minus. Since the times differ by equal amounts, these ordinates are therefore in geometric progression. Hence, y, 23.2, y 19, from which one finds y 24.4. The thermometer would therefore, with the heat of the air remaining constant, fall from 39.4 to 24.44. That is by 15 degrees, the further application of the formula. Section 259 gives the duration of cooling. And in general, if one uses the Brigesian logarithms, the degree shown by the thermometer is YGC15NL 139, 0.036 Ti, where I indicate for brevity by NL the value of them that is represented by 1.39. Using this formula, I have calculated the degree Y for each minute. The following table presents both the observed and the calculated degrees. From this, it can be seen that the calculation gives only, for the first ordinate, 2 decimal places more. For the others, it gives only at times 1 decimal place, more or less, but in most cases, it agrees exactly with the experiment. The diameter of the sphere was 933 lines, Paris measure. Since the cooling time is 7 minutes, that is 9.33 minutes, I therefore assume that for the cooling of a sphere, the time is in proportion to the diameter of the sphere, see 260. So that for each line of the sphere's diameter, for the spirit thermometer, 1 minute of time can be reckoned for the cooling time, provided that the thermometer cools in air. Air, that is more or less dense and moist, may moreover make some difference here. 262. For other reasons, I had left this thermometer open for several days. Before I closed it again, I carried out another experiment in order to see how it would cool if I heated it over a charcoal fire so far that I had to fear the spirit would boil. I immediately had the charcoal fire removed and placed the thermometer in the same spot as the first time in order to note its degrees every minute. I will therefore set down the observed degrees together with those calculated by the formula G13 den 1.6 1805 0497 in the following table. Observe 54.7, calculated 54.5. Observe 50, calculated 54.5. Calculated 46.3. Observe 45.8, calculated 46.3. Observe 42.3. Calculated 42.4. Observe 39.9. Calculated 36.2. Calculated 36.8. Calculated 32.97. Observe 31.5. Calculated 31.7. Calculated 31.68. Observe 26.2. Calculated 26.211. Observe 24.8. Calculated 23.7. Calculated 23.5. Calculated 22.14. Observe 24.8. Observe 21. Calculated 19.6 to 17. Observed 19.918. Observed 18.4. Calculated 18.7. Calculated 17.720. Observed 17.7. Calculated 17.20. Observed 17.721. Observed 16.7. Calculated 7.477. Calculate. Observed 15.8, calculated 1624. Observed 15.4, calculated 15.7. I had expected larger differences because the alcohol this time was so warm that it came very close to the violent state of boiling. The cooling subtangent is in fact also somewhat smaller than in the first experiment, namely 7 equals 8.73 minutes. And this shows that the spirit of wine at higher degrees of warmth expands somewhat more than in proportion to the warmth. I carried out this experiment on the 31st of February, 1777, in the morning between 10:30 and 11 o'clock. With sealed alcohol thermometers, I have always likewise found the cooling subtangent smaller. Yet I have also found that the cooling is not completely logarithmic. With mercury thermometers for an equal diameter, I found the cooling subtangent in air to be 2 seconds shorter, so that for a sphere of 10 Paris lines, 7 equals 6 minutes. But if I let the thermometers cool in water, I found the subtangent to be 8 to 10 times shorter than when they cooled in air, 264. Now, I shall be able to complete the Newtonian scale of degrees given above P. 105. For several further degrees of heat, Newton had a piece of iron made red hot in the fire and then let it cool in a place where the wind blew past uniformly. He placed various pieces of metal and other materials upon it and observed the time when they began to lose their fluidity, or also when they were just barely fluid. Some of these degrees he had already determined by means of the linseed oil thermometer, and for these he had expressed the ordinates in terms of the degrees of the thermometer. The higher degrees he then calculated by doubling having the time, on the assumption that the cooling was logarithmic. Some observations to which I at once add the corresponding degrees of the alcohol thermometer and the air thermometer are now as follows. Key communication of heat: melting bismuth, likewise melting solder made of 4 parts lead and 1 part tin. Likewise glowing solder made of 5 parts lead and 1 part tin. Glowing lead, melting lead. Melting lead, glowing iron ceases to appear red in the dark. Melting mixture of equal parts tin and Regulus of Mars. Glowing iron ceases to shine in twilight. Glowing mixture of 1 part bismuth and 2 parts Regulus of Mars. Likewise glowing mixture of 1 part tin and 5 parts Regulus of Mars. Glowing Regulus of Mars. Glowing iron ceases to shine in full daylight. Glowing iron, likewise the heat of a stone coal fire, heat of a wood fire. CP 265. This table is a continuation of the one given above, P some items. It can be compared with the Muschenbroek table, P 27, and it agrees with it in the main point, namely that iron which begins to glow or ceases to glow must have a heat of about 3,000 to 300 degrees on the air thermometer. That Muschenbroek set the degree for melting lead, and also for melting bismuth, too high, or rather did not reach the correct degree. I have already noted above. Ziegler, who made similar experiments on his own melting pot, and in doing so observed the degrees of Fahrenheit's mercury thermometer, reports the following observations, for which I also confirmed the degrees of the air thermometer. Communication of heat, hardness, fusibility, degrees, molten lead, molten bismuth, molten tin, flowing turpentine oil. Melting alloy of 3 parts tin, 2 parts lead. Melting alloy of 5 parts bismuth, 2 parts lead. 5BR, 2T4, L5, 2552, 652, 752, 135, 223. With molten tin, Newton, Muschenbroek, and Hensler agree fairly closely. With lead, Hensler is off by a third. With molten bismuth, he comes closer to Newton. It should also be noted that not all lead or bismuth is equally easily fusible. And finally, I must remark once more that Newton, by using the smaller value, calculated the higher one, so that a small difference in the assumed cooling constant can greatly alter the degree of heat. Martin carried out several experiments on the warming and cooling of different bodies. He filled glasses of the same size and shape with water, mercury, balsam of Peru, and olive oil, and placed one glass after another before the fire to warm it. In each there was a thermometer whose rise he observed at intervals of 4 minutes. Then he let them cool again in the open air, and in such a way as to reach the same degree of warmth. I read his observations carefully, and found that those made on warming were very irregular, because both the unevenness of the flame and the unequal supply of air make the warming uneven. In cooling, there is more uniform. From these experiments, I find the cooling constants of these materials, when they are taken in vessels of the same size and shape, to have the following ratio of transmission of heat to mercury: 56 tree oil, 64 alcohol, 77 water. 100 these substances cooled in the air. Yet it must be noted that only their surface was exposed to the air, and that they therefore lost most of their heat through the glass. This, however, is not entirely insignificant. Instead of open vessels, I used sealed thermometers in which alcohol and mercury cooled entirely through the glass. CP 263. This is the reason why I found the ratio of the substances to be 56 to 100, rather than the 5 to 7, that one finds in Martin as I do. In the end, Martin also finds that his mercury thermometer in air cooled 8 to 9 times more slowly than in water or in mercury. For these two substances showed no very noticeable difference. Moreover, Martin does not dwell long on the fact that the experiments of Boerhaave, Muschenbroek, and others differ so greatly. They conclude in general that a dense body warms and cools more slowly than a loose one, and the former explains it as though the cooling were to take place all at once. Experience, however, makes certain exceptions here, and shows that these circumstances must be considered more carefully. Since liquid substances cannot be given definite shapes except by means of vessels, the cooling of air can likewise be determined only by means of vessels. Yet I find it very strange that one has so far paid almost no attention to this. If I place the bulb of the air thermometer described in NOG91 in cold air or in warm water, the small column of mercury in the tube moves at once so quickly that one can see without measuring that the complete warming of the air in the bulb requires only a few seconds, because the glass of the bulb needs that much time to become warm. The mercury column begins with a truly accelerated motion from the very first moment, and if the water is very warm, it shoots out toward the tube with considerable speed as soon as the bulb touches the water. If, on the other hand, I immerse the bulb of the same air thermometer in cold water, or place it in warm water, the mercury in the tube likewise rises quickly upward within a few seconds. After that, it continues to rise only very slowly. Namely, in the first seconds, the air in the bulb receives almost all its heat. But since the mercury lying at the bottom of the bulb is much slower, as it becomes warmed, the air likewise takes on a share of the heat it has received from the very beginning, until at last it has also attained the heat of the body. The speed with which heat spreads through the air depends on the fact that the air everywhere has only the heat of the bodies it touches, and that if the earth and other bodies did not retain the sun's heat better than the air does, we would have little to enjoy from the sun's warmth, since all other bodies in the air would otherwise, in the course of time, become warmed and cooled again. This is the reason why thin window panes keep the heat in the room, and especially why the effect is doubled when there are double windows. One readily sees, too, that a room stays warmer when the heat is prevented by wallpaper or paneling from escaping through the walls. From this, one also understands why water seems to us colder than equally cold air. For the cooling capacity in air is 8 to 10 times greater than in water, and so in the first second we lose 8 to 10 times more heat in water than in air. I should also note that the warming capacity and the cooling capacity have the same magnitude in every body and in every kind of fluid matter. If the thermometer is warmer or colder than the air by the same number of degrees, then it approaches the air's warmth along a certain logarithmic curve. The number of degrees of heat that it loses in the same time in the first case and gains in the other case is equally great. From this, one may conclude that equal degrees of heat in the thermometer, in the air, and in other fluid materials have equal preponderance. I say preponderance deliberately, for the word force would be more ambiguous here, since the force of heat within a body must necessarily be distinguished from the force with which it acts upon other bodies it touches. CP 102, second chapter, warming and cooling in compound cases, first section, warming by the fire and by the sun. If, however, one assumes that the action of the fire has been the same over a certain period of time, then one may reckon from one moment to the next and take an average. And in this way, one may say that the fire has in equal times imparted equal amounts of heat to a body. I assume further that the body is not in the fire, for then it would belong to the cases considered in the preceding chapter. The body is to be outside the fire, receiving from it, in equal times, equal degrees of heat, but at the same time, losing this heat again, so that it is warmed only up to a certain degree. I set down these assumptions only because they are the simplest under which a body is warmed, and at the same time loses again the heat it has received. The same is also the case with bodies that are warmed by the sun when the sun continues to shine with equal brightness. Child 270. Let Y, then, be the heat that the body has after the lapse of time t, and let its cooling constant be 7. If, in each portion of time ddo, it receives from the fire n degrees of heat, then ndia will be the heat it receives in the time interval ddo. But since it is y degrees warmer than the surrounding air, it will in the same little time interval lose yd divided by 7. Consequently, the heat it retains will be di n ddia. One sees at once that if one lets n vary, this formula in general also includes all cases in which the warming takes place unevenly. Further, one sees that in the same generality one may set di 0, and thereby the maximum heat. The greatest heat is then equal to that which the body would have at time, if it did not cool again in the meantime. Ju 271. But if we now take N as constant, we obtain the integral formula always 707g. One therefore sees that the warming is logarithmic and entirely the same as it would be if the air had the warmth in 7, and the body were to warm in that air. If several bodies are of the same material and shape, and differ from one another only in size, then for each of them, the excess of He is in direct proportion to the surface exposed to the fire, and in inverse proportion to the volume of the body. By contrast, the cooling subtangent 7 is directly proportional to the volume and inversely proportional to the entire surface. Since the maximum of the heat is 0.7, it follows that when, for all such bodies, the surface exposed to the fire is proportional to the whole surface, they will all attain the same degree of heat. The only difference will be that the larger bodies will reach this degree more slowly, and later. I also assume that they stand at the same distance from the fire, so that the rays from the fire fall upon their surfaces with equal density. Otherwise, the resulting difference would have to be included in the calculation. This also holds with respect to the sun as long as it shines with equal strength and the air retains the same warmth. But with respect to the sun, there is also an additional circumstance, which arises from the color of the body. For the most part, however, one has been content to prove this difference from optical principles, and at most, to appeal only to general experience. Delancey, who placed 2 pieces of marble in the sun in order to determine their expansion by heat, pieces that were of the same shape and size and were equally exposed to the sun, noticed on this occasion that the white piece was still cold, while the black one had become very strongly warmed. Warming by fire and by the sun, Pistoy of Siena blackened a Reaumur mercury thermometer on half of its surface in the smoke of the lamp. When he turned the blackened side toward the sun, the mercury rose to the 35th degree. But when the side that had remained white was turned toward the sun, it rose only to the 32nd degree. In the shade, it showed 21 degrees. This fact seems to me to deserve closer investigation. I therefore propose the following experiments. 274. On May 23, 1772, at midday, I set 3 spirit thermometers in the sun. 2 were colored red with Brazil wood, and the diameters of their bulbs were 9 and 6 lines, Paris measure. In the third, the spirit was not colored at all, but was crystal clear. The diameter of its bulb was 9 lines. I then placed a 4th thermometer beside them in the shade. When those lying in the sun had reached the maximum of their warmth, I found the 2 with colored spirit, 25 degrees, the uncolored one, 21 degrees, the one. 10 degrees thus. The 2 colored ones had risen 15 degrees, while the uncolored one had risen only 11 degrees, 275. On June 14th, at 11:30, I repeated the experiment, and also set a mercury thermometer in the sun, whose bulb had an average diameter of 9 lines. When they had reached the maximum of their warmth, it was the mercury thermometer, 23 degrees, the larger red-colored one, 24.1 degrees, the smaller one, 24 degrees, the uncolored one, 21.8 degrees, the one in the shade. 16 degrees, thus the mercury thermometer had risen 7 degrees. The two colored spirit thermometers, 8 and 8.1 degrees. The uncolored one, 5.8 degrees, 276. After this, on June 15th, I repeatedly dipped the uncolored spirit thermometer into black ink and let it dry each time, and in this way, it became coated with a black, opaque crust. The smaller red-colored one, I coated it with very white lime so that the ball now had a diameter of 7.5 inches. I immediately set it in the sun at 10 o'clock in the morning, and after 11 o'clock I found the blackened one. 28.2 degrees, the coated one. 13.8 degrees, the uncoated one. 26 degrees, the one in the shade. 16.5 degrees, thus the blackened one had risen 11.7 degrees, the red one 9.5 degrees. But the coated one had not only not risen, it had fallen by 3.7 degrees, although it too lay in the sun. I could easily suppose that this must have been because the lime with which it had been coated was still damp. When I then hung the thermometers back in their place, I found that the coated one fell a further 1.1 degrees, and only after an hour did it rise again so far that it matched the one that had raged. In the meantime, it had dried completely, 277. On the following 16th of Brachmanat, I again set these thermometers in the sun, together with the mercury one, and when they had reached the maximum of their warmth, I found the mercury one, 24.3 degrees, the blackened one, 30.2 degrees, the coated one, 23 degrees, 26.6 degrees, the one in the shade, 17.4 degrees, thus the mercury one had risen 6.9 degrees, the blackened one 2.8, the coated one 2.9, the coated one 2.8, the coated one 2.9, and the one with red-colored spirit of wine 9.2 degrees, 278. Finally, I coated another spirit of wine thermometer with lime, and painted the one from the 15th over with cinnabar, so that it looked vermilion colored. When they had long since dried, I set them in the sun on the 26th of Brachmanat in the morning. After they had reached the maximum of their warmth, I found the mercury one, 30 degrees, the blackened one, 37.2 degrees, the one painted was 29.9 degrees, the coated one, 26.3 degrees, the one with red-colored spirit wine, 32.6 degrees, the one in the shade, 22.8 degrees warming by the fire and in the sun. Thus the mercury thermometer rose 7.2 degrees, the blackened one 14 degrees. The one coated with cinnabar 7.1 degrees, the white coated one 3.5 degrees. The one with red-colored alcohol rose 9.8 degrees, 279. The alcohol in the bulb of the uncoated thermometer looked dark red, yet it was still transparent. The bulb of the mercury thermometer was likewise somewhat dulled by smoke, so that the mercury did not shine through quite as brightly, and therefore reflected back somewhat fewer sunbeams. Since, moreover, the mercury thermometer was about 1/3 larger, c. 124, than in the last experiment, the 7.2 degrees of mercury must be reckoned as 8 degrees of alcohol. The white-coated thermometer was like the whitest wall, I must say, as white as it could possibly be. Now, the first two experiments, CL 274, 275, show that as long as the two colored alcohol thermometers were not coated, they rose in the sun by the same amount, even though their bulbs were of unequal size. From what was said above, 272, this could have been expected in advance, for since the size of the bulbs does not matter, so long as they are not coated, it would have been the same if they had been equally large. Thus, in the same time, equally many sunbeams would have fallen on all of them. If, accordingly, all the sunbeams had penetrated inward, then at least all the alcohol thermometers would have risen by the same number of degrees. But too many rays were reflected back from the surface. Therefore, the darker the color was, the fewer rays penetrated inward. And in the last experiment, this was the white one. 3.5 degrees, the light red one. 7.1 degrees, the dark red one. 9.8 degrees, the black one. 14.4 degrees. The mercury thermometer is not included in this comparison because several circumstances are different in its case. Whether in the case of the coating there is a special reason why the coated thermometer rose so little in the sun, I cannot determine with certainty. I have already mentioned above that when the coating was still moist, the thermometer did not rise in the sun, but fell. See 276. It has long been known that if water is poured onto the bulb of a thermometer and the water has the same warmth as the air, the thermometer still falls. On the 24th of June, 1772, I placed a thermometer in water that had the same temperature as the air. When I took it out again, without drying the bulb, it fell from 19.8 degrees to 18. I then put a few drops of water on the bulb and the mercury fell to 16 degrees, but no further. From this it follows that, in drying, not only water but also heat is carried off, and indeed more heat than the drying water itself already contained. When I repeated this on the 24th of June with the 15th thermometer, which had been moistened with spirit of wine, the mercury fell from 19 degrees to 15 degrees, and then rose again so slowly that it did not reach the warmth of the air until after 6 hours. On the same day, I moistened another spirit thermometer. When it was dry at 4 o'clock in the afternoon, I dipped it for 20 seconds in water. During the short time, it fell from 20.1 degrees to 20. When I took it out, it fell within 12 minutes to 15.2 degrees, and then began to rise again very slowly. From this, one may conclude that damp walls are colder than dry ones. Since cold increases with moisture, this may be one reason why the moistened thermometer, which had been left overnight, lost more than it gained. I have determined by experiments with the photometer that the whitest lead white reflects only 2/3 of the incident sunbeams, so that 1/3 penetrates. If, therefore, in the thermometer left overnight all the incident sunbeams had penetrated, it would have had to rise by 14.4 degrees. That is, by 14.4 divided by 3 equals 8. Yet it rose only 3 degrees, thus more than half less. It may also be that since the lime has more pores, the heat can escape from it again more easily. In that way, the cooling phase is shorter and the maximum warmth is smaller, 282. If, in the first thermometer, the cooling phase in the air is considered only with respect to its moisture and density, and thus in general changes little, then the maximum warmth in the sun depends chiefly on the density of the incident sunbeams. This circumstance has long given me occasion for various experiments. On the 21st of July, 1755, I set a thermometer in the sun and observed for several minutes how it rose. When I had cooled it again in water and dried it, I placed it behind a mirror glass through which the sun shone brightly. In the evening, I placed it likewise behind 2 panes of glass, and then behind 3 panes. This was done in order to see how many sunbeams would be intercepted by the glass. Finally, I let the sun shine through one of these panes of glass onto the thermometer at an angle of incidence of 30 degrees. And now I directed the sun's rays, falling back from the glass, at the same angle of 30 degrees, onto the thermometer, and observed each time how much it rose in half to 1 minute. Since not much time passed during these experiments and the sun's altitude did not change noticeably, I could not wait each time until the thermometer had reached the maximum of its warmth. It was sufficient in general to determine the initial rate. The result is contained in the following table. Time in the sun, through 1 pane, perpendicular, through 2 panes, perpendicular, through 3 panes, perpendicular, through 1 pane at 30 degrees, reflected from 1 pane at 30 degrees. The warmth of the air at that time was 20.4 degrees. From this point, the rise of the thermometer must properly be calculated. For this purpose, I have taken the numbers of the first column, or the time, as the abscissas, and the numbers of the other columns as the ordinates, and thereby found that the density of the sun's rays stood in the following ratio, direct. 100 through 1 pane perpendicular, 84 through 2 panes, 69 through 3 panes, 59. These determinations may now be compared with those which I found in 474 of the photometry, by means of other glasses, in a purely optical way. From the comparison, it follows that the glasses used here were more transparent, for there I found 181, 66, 54, numbers which decrease in a somewhat faster ratio, although otherwise the difference is not great. I also remarked already in Aki 475 of the photometry that Bouguer used glasses that were still much less transparent, because with him even 2 glasses were enough to intercept half of the sun's rays, 283. In the same way as I had determined, by experiments, the intensity of the sun's rays diminished by glasses, I determined it insofar as it is diminished by the earth's haze. I set one thermometer in the sun and another close by in the shade. This was done several times in the morning at 10 o'clock, when the sun began to shine on the window. First, I had to let an hour or more pass before the thermometer exposed to the sun had risen so far that from then on its rising and falling was governed solely by the increasing intensity of the sun's rays. But I seldom found a day when clouds did not sometimes pass before the sun, or the wind did not cool the thermometer in the sun. A little among the still usable observations, I found those from 1756 to be the most regular. I found the thermometer in the sun higher than that in the shade in the afternoon at the following solar altitudes. Solar altitude 60 degrees, 15.8 degrees 50 degrees, 14.6 degrees 40 degrees, 12.8 degrees 30 degrees. 10 degrees from this, I concluded the determination given in the photometry 886 of the weakening of sunlight by the air. I further found day solar altitude degrees on the spirit thermometer. Degrees on the mercury 1756. 12 February, 31 degrees. 5/28 February, 35 degrees. 8/28 March, 45 degrees. 10/31 March, 47. That the quicksilver thermometer rises less in the sun than Mr. Deluse's spirit thermometer follows from these observations, just as it does from those cited earlier, pp. 275, 200. Moreover, I must once and for all remind the reader that in all my thermometers I set the bulb more than an inch away from the little board, so that the warming of the board has no influence on the warming of the bulb. And since I am accustomed to the Romer spirit thermometer, I understand it as such, unless the contrary is expressly stated. To these observations, I will add the following, which were made in Saxony by Mr. D. Hoffman. They are, according to the Romer thermometer, the greatest degrees of summer heat observed over several years, both in the sun and in the shade. It does not, in fact, attain a maximum of warmth, but rather its warming by the fire and by the sun. Heat increases in such a way that, if the strength of the fire or of the sun remains constantly the same, it finally changes only within certain limits. Let these limits be U and OU, so that warming be tau. Then the formula found above, P271, gives chart 7. Let the time of cooling again be 7. Since the body cools again from degree, down to degree, the formula, P2I, G7, but N7 is the amount of heat the body would attain if it were kept continuously at the fire or in the sun. One easily feels that with alternating warming and cooling, it cannot reach this degree. And from this, it follows in turn that a weaker force of the fire or of the sun, if it acts continuously on the body, can impart to it just as much heat as a stronger force that acts only intermittently on the body. One can make some application of this to the warming of rooms by stoves. From this, too, one can understand that in the polar regions, the earth is warmed just as well by the sun's constant shining as it is between the tropics, where the sun stands much higher at midday, but does not remain above the horizon for even half an hour. Moreover, in this calculation, I have assumed the times, ET, to be constantly equal, in order to make the computation simpler and to show what happens in this simplest case. In the Paris Memoirs of 1719, Morin relates a very curious experiment. He brought a small kettle in the open air to the fire, and in less than 7 minutes it began to boil. On the other hand, it took a little more than 38 minutes when he set the same amount of water in the same kettle, alternately on the fire, and off the fire for 4 minutes, and then removed it for 2 minutes. When he alternately set it on for 2 minutes and removed it for 4 minutes, the water did not boil at all, even though the fire was strong. The air must have been fully temperate. No thermometer, however, was used in this. Besides those cases in which a body is exposed to the fire or the sun alternately, and then removed again, there are also cases in which only one side of the body is continually exposed directly to the action of the fire or the sun. Such are, for example, bodies that one keeps turning over at the fire. If such bodies are so small that the heat at once spreads through the whole body, then turning them over has little effect. But with larger bodies, one thereby has the advantage that the heat is distributed more uniformly through them, and that they do not scorch on one side while remaining almost cold on the other. With respect to the total amount of heat, considered in general, it is all the same. But if the bodies are not very round, but flat or angular, then because of the inequality of the side exposed to the fire or the sun, a noticeable difference can arise. From this, one can derive various rules for the art of cooking and roasting, partly concerning the shape of the roast, partly the speed of turning. The sun is often covered by clouds, sometimes intermittently, sometimes for the whole day. The latter, however, does not cause a complete withdrawal of the sun's warmth. Sunlight warms in whatever way it falls upon bodies, and therefore also in the form of mere daylight. In photometry, section 985, I showed that a surface which is illuminated by the whole sky, at moderate heights of the sun, receives about 1/3 of the light that it would receive if the sun shone on it perpendicularly, and its rays were not intercepted by the air. But since the air itself, even at great heights of the sun, intercepts at least 2/3 of the rays, so that only 1/3 gets through, photometry, section 86, the illumination of a surface by full daylight compares to its illumination by the sun as 1/3 to 1/3, that is, as 1 to 3. It follows from this that in cloudy weather, the thermometer can still rise during the day to 1/3, as much as it does when the earth is illuminated and warmed directly by the sun. Experience also confirms this, if one takes into account what warm or cold winds and rain can change in this rule. The thermometer also stands higher on cloudy afternoons than in the morning. Finally, with fire as with the sun, the angle of incidence must be taken into account, because a surface that lies more obliquely receives less fire or light rays than when they strike it perpendicularly. But this still does not explain everything, because it is especially with sunlight that the rays are known not merely to fall upon bodies, but to penetrate into them. And at small angles of incidence, this is the least part. From IT 312 of photometry, it follows that the logarithm of the penetrating light rays is in inverse proportion to the square of the sine of the angle of incidence. It is now easy to judge what is to be expected from the above-mentioned experiments, D218, in which, in order to investigate the expansion of metal rods, one laid the rods together with thermometers in the sun and imagined that the degree of warmth in the thermometer and in the rods would be the same. For this experiment, 219 was not only already shown to be faulty for other reasons, but the difference in color and in material is already evident even in the thermometer, 274, 281. With rods, there is also the difference in shape and in angle of incidence. And then the cooling by evaporation is also very different. Thus, one can easily understand why Dr. Jung found, for the Réaumur degree, quite different expansions of the rods when he warmed them in the sun and cooled them in snow. According to his experiments, rods 6 feet long expanded as follows. Iron. In the sun, 0.266. In snow, 0.1 lines. Steel in the sun, 0.249. In snow, 0.39. In snow, 0.15. Tin plate. Brass rod. In the sun, 0.41. The experiment in the sun was repeated several times, and the result was fairly consistent. For example, the expansion of the copper was once 0.24. Another time, 0.41. One cannot say that this comes from unequal transparency of the air, for the iron rod laid in the sun at the same time expanded both times by the same amount, namely 0.266. Perhaps the angle of incidence was not observed precisely enough. The rods may not have been well polished, whereas the tin plate may still have had some shine, but a shiny metal reflects more sunbeams. Therefore, the sheet seems to have been warmed less than the brass rod. In any case, these experiments carried out in the sun do not provide anything reliable. From the experiments in the snow, however, the warming by the fire and in the sun, compared with the expansions set down in the table, 217, in the fourth column, for if, for example, near the freezing point, an iron rod 6 feet long is found to expand by 1/10 of a line when warmed by 10 degrees Réaumur, then this expansion amounts to 1/8435th of the whole length. Now, since, in the true Réaumur thermometer, The degrees of spirit are the same as those of mercury, p. 132. The expansion of iron found for 10 degrees can therefore be taken tenfold, and the expansion from freezing to boiling can be stated with sufficient accuracy. There remains only the doubt whether the Reaumur thermometers used by Dr. Juan, as well as those used by his companions Ulloa, Condamine, Bouguer, and Godin, were true Reaumur thermometers. This doubt is not insignificant, pp. 132. 217. So that the fire or the sun does not always impart the same amount of heat to the body in equal times, then can for the most part be expressed as a function of E. And to that extent, the variable quantities in this formula can easily be separated. One obtains UINO 7, DONO 7, where A is the constant quantity to be added after completing the integration, and can usually be determined by means of the known value of Y. The simplest case here is that in which anyway EBI, and consequently the strength of the fire increases or decreases according to an arithmetic progression. For this case, we obtain the integral formula y77 bres 7 agia 7, and if for each AC y fish y, this becomes Jevin 7b s7 bres 7b. Accordingly, the body warms exactly as if it were an air whose heat were a 7. And in addition, in the time OD, the heat BE were communicated to it. If, therefore, the body had right at the beginning the heat A7 by 7, then A7 G do 7 pure, its warmth would therefore increase in an arithmetic progression. 291. If the intensity of the fire, or of the sun's heat, has remained constant for so long that the body has already reached its maximum warmth, and from that point the heating power begins to become greater or also smaller than let X7. And then we have YGS7, B7, BP7, or R7, or if one expands the R7 into a series Y7BR, etc., from this one sees that the warmth of 7 at first does not increase strongly, provided B does not have a very large value. Moreover, one finds similar formulas for cases in which a body is warmed in air, water, or another fluid material whose warmth is not constant. For if Y is the warmth of the body, and a B per A is that of the fluid material, then one will have dIGA Y7, from which YJ B7 I gets Earth 7 follows. If B is constant, that is, if the warmth of the fluid material increases by the same amount in equal times. In this case, the body, even if it was at first warmer than the fluid material, will nevertheless become less warm. If one performs experiments in which the formulas given so far are applicable, one must check whether the fire warms the surrounding bodies in such a way that the air itself is thereby warm. This happens of itself already in enclosed rooms and likewise in the sun. For since Y and Y properly represent only the excess of the body's warmth over the warmth of air, it is necessary to take the change in the air's warmth into account. One therefore places a thermometer first in the shade from the sun or the fire, and observes from time to time its degree, so that one can see whether and to what extent during the experiment the warmth of the air has changed. If the body that casts the shade is warmed by the sun or by the fire, then the thermometer must not stand too close to it, because otherwise it would partake of that body's warmth. In the case of warming at a fire, it is still to be noted that the maximum NC 270 can indicate a higher degree of heat than the body is capable of sustaining. For one may place water in a vessel so close to the fire that, at the same distance, tin or lead would melt, and yet the water will attain at most only the heat of the boiling point, which is much lower. See ancient 4. One therefore sees that circumstances can occur which are not included in the formulas given above, and consequently where they occur must still be brought under the calculation. The boiling water is in a violent state. From it, a great number of bubbles rise, which, if the water were solid, would be filled more with particles of fire than with air. In this way, the particles of fire, so to speak, are carried away in large quantities from the water. With so little heat, the water would be warmer on the side toward the fire, and toward the other side would have progressively less heat. But with such an agitation, the heat spreads with force in all directions. This contributes to the fact that more heat is carried away. If, therefore, the calculation is to be applied to these cases, one must, in the fundamental equation, Cu 270, ddU regard the subtangent as variable, regard the subtangent time as variable, so that it becomes smaller the nearer the degree of heat Y is to the boiling point. Now, since the maximum of heat, when a quantity of water is placed close enough to the fire, is the degree of boiling, the smallest value of E can be determined by the maximum in E guide. For A is the excess of the heat at the boiling point over the heat of the air, in which the water standing at the fire cools. But the initial value of E does not extend beyond 1 to 5, up to the degree of melting tin or lead, etc., depending on how much closer the water stands to the fire. Second section. Warming of one body by another. A warm body gives a cold body, which it touches, or even which is only near it, a portion of its warmth, and the more so the closer they are together and the larger the surfaces are that face one another or touch one another, the more exactly they touch. If air, or even only an airless empty space, lies between the bodies that are touching, then the warmth must first pass out of the one body into the air or into the empty space. Therefore, it proceeds much more slowly, pp. 263, 266. Siegler, in his Citigester Papinae, gives the advice that if one wants to know whether a body is hot enough to melt, for example, lead, one can learn this more quickly by first dipping a leaden rod into oil and then touching the body with it. Then the heat passes more quickly because the oil that exactly touches both bodies conducts the heat better than the lead. If one also makes both touching surfaces mirror smooth, so that they, as it were, cling to one another, then the transfer of heat from one to the other is better still. I note this here because it has no small influence on determining the cooling substances. L295. Since heat does not spread instantaneously through larger bodies, one proceeds best, when both are fluid and not altogether of unequal weight, by pouring them together and stirring. I have already mentioned above 66 that such mixtures of warm and cold water have been used to divide the degrees of heat on thermometers into equal parts. Boerhaave, without considering this precaution, relates that when he mixed equal amounts of boiling water and freezing water, the warmth still remaining in the cold seemed as it were to be lost. The boiling had, namely, 212 degrees. The freezing 32 degrees of warmth, according to the Fahrenheit thermometer. The difference is 180 degrees. Of these, 90 should pass over into the freezing water, and 90 should remain in the boiling. And consequently, the mixture should retain 3290 Chichu and 122 degrees of warmth. Boerhaave found only 90. Kraft likewise performed the experiment, and found only 108. But if one does not pay attention to all circumstances, one can err by any amount. For example, let the cold water be in a vessel of metal, the warm in a vessel of thin sheet metal, pour the latter into the former, and so on. It already loses some of its heat while being poured in of what remains. It shares it not only with the cold water, but also with the thick metal of the kettle. If one then puts in a thermometer that is colder than the mixture, the thermometer itself still takes away some heat, and during the time this takes, the thermometer reaches the proper warmth. Meanwhile, the mixture cools. One can avoid all this as far as possible by mixing only small quantities of water. Boerhaave speaks of a pound. The force may perhaps have been taken as greater. Richmond expressly reminds us that one must take the vessels into account, and so one will find that the loss of heat is distributed over the whole mass of the mixture, and in relation to the whole mass, the heat given to the warmer water will be less. The most thorough experiments on this are found in Deluc. But in the application he makes of them, he assumes in advance that if in the same quantity of water there are twice as many particles of fire, the warmth must be twice as great, and that may well not be mistaken. But if one takes equal quantities by weight or by volume, then the expansion of water by heat unquestionably makes some difference, which extends from the freezing point to the boiling point to about 1/25 of the whole. Then one can indeed determine the density of the fire particles by the water's warmth, but one can also determine their force by it, and one must first see how far force and density proceed in equal steps. The difference may be small. I mention this only because Herr de Luc pays attention precisely to such small differences in his experiments. His aim was not to determine the warmth of the mixture by the thermometer, but by means of it to take that division into account. Such mixtures now apply to the most watery substances, such as water, wine, vinegar, spirits of wine, and so on. And likewise to pressed oils as well, because they really can be mixed. If one takes equal parts of water and oil or water and quicksilver, the difference is especially not great in the latter case. Boerhaave states that 3 parts, measured not weighed, of quicksilver and 2 parts of water poured together give exactly the warmth that he found in equal parts of water. So quicksilver or water must have been warmer. From this, it follows that in water, 3 fire particles have no more force of warmth than 2 fire particles in quicksilver, if water and quicksilver occupy the same space. Boerhaave also says that for the sake of clarity, he arranged this comparison. Barnard made similar experiments, and with regard to mixtures, he leaves the effect of warm and cold water on the human body to physicians. But with water and quicksilver, he encounters difficulties which he leaves to more skillful natural philosophers to resolve. If bodies are not mixed in the manner first mentioned, but only touch one another, then there can be a difference depending on whether one completely surrounds the other, or whether the contact occurs only on one side. The first case is simpler, because it requires only one equation of radiation. I shall therefore take it up first and assume that the enclosed body is warmer than the one surrounding it. A double radiation then occurs. The inner body loses heat. This passes into the outer one, and finally from that into the air. I assume here, as in the cases considered earlier, that the bodies are small enough that the heat they receive immediately spreads uniformly through them. If, at the beginning, the outer body is already warmer than the air, then we must take the degree of the air's warmth as 0, and from then on count the warmth of each of the 2 bodies. Let, at any time, the warmth of the inner body be Y, and that of the outer be Z. Then Y is the excess of warmth of the former. In the time element ddu, a quantity of heat dye passes from it into the outer body. Let the radiation coefficient be 7, then see 258. Daichiwell the 7 did du, and this is the first equation. 298. The heat dye which in the time do passes from the inner body into the outer changes its effect in the latter in a twofold way. First, the density. If the outer body is larger, it follows that it is of the same material. In this respect, dye must be diminished or increased in inverse proportion to the volume if the outer body is smaller. Second, the force. If the bodies are not of the same material, it follows that they are not of equal force. For I have previously shown from Boerhaave that, for example, quicksilver or spirit of wine does not take up more heat than water, 296. And so other materials may likewise show other differences. For both reasons, I shall therefore assume that the heat, which in the inner body was dye, amounts in the outer to mesd. The coefficient m must in each case be determined by the difference in size and in the material of the 2 bodies. From the outer body, a portion of its heat now also passes into the air. Let its cooling subtangent with respect to theta equal to theta. Then in the time element d tau, the portion that goes away is z t tau divided by the theta. Accordingly, the change that the outer body undergoes in the time element d tau with respect to its heat is in general dz chi d minus md 9 minus z tau divided by theta. And this is the second equation. From these 2 equations, it now follows that y and z are the sum or difference of the ordinates of 2 logarithmic curves, which we may represent by yg and are expressed by the 2 roots of the equation a87 theta theta at g z7 chi 0. Therefore, at g 7 theta 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 742 7 of theta 2 2. If furthermore y and z represent the heat of the bodies for tau g0, then one finds C change 7 ABID should be and B and 7B and B and 7B and B 7. I have, in the 4th volume of the Acta Helvetica, published in 1755, taken special note of that case and compared it with an experiment in which the outer body was twice as large as the inner one. I had placed a thermometer in a bowl of lukewarm water, but set the bowl itself on a wire stand. For if I had set it directly on the table would have been warmed, and the cooling of the water would have followed a quite different law than the one whose confirmation I intended by the experiment. The result was that only in the first minutes differences of a quarter or a third of a degree occurred. After that, however, the difference between observation and calculation was never a tenth of a degree, but for the most part was even smaller. Of the two logarithmic lines, whose ordinates when added together or subtracted from one another, give the degrees u and usually approaches its asymptote so quickly that after a few minutes have passed, the other remains almost alone. I have already made use of this advantage, which presents itself at first glance, in order to apply the formulas more easily to the experiment. It should further be noted that the initial degrees of warmth can stand in such a relation to one another that this relation remains the same throughout the cooling, and is therefore expressed by yz. The cooling, both of the inner and of the outer body, then proceeds quite uniformly, according to the ordinates of a single logarithmic line. In the other cases as well, the cooling continually approaches this condition more and more. On the 26th of June, 1772, I placed a mercury thermometer in a cylindrical vessel of thin brass, which stood on the outside upon a sheet of tin, and therefore did not touch the table directly. The thermometer showed the 23rd degree of warmth on the Réaumur scale, and filled about 1/3 of the space of the vessel. I then poured in boiling water until the little vessel was completely full, yet without lingering in the least. At once I also observed the time and the rise of the thermometer, and found the mercury finally fell here noticeably lower than the air in the room had been. This seems to arise from the same cause as in the experiment described above, p. 231, namely the wetting of the thermometer bulb with water. I have now carried out the present experiment in order to see more closely what this means for the coefficient P298. From the numbers in the table, it is clear that in the first half minute, the thermometer had reached the maximum of its warmth, and from then on began to cool again, at first very slowly. This maximum warmth of the thermometer was now equal to the warmth still remaining in the water, for otherwise the mercury would either have continued to rise or would already have begun to fall. Now, at the beginning, the water was boiling. Consequently, its warmth was 80 degrees. Subtract from this about 2 degrees, because during the first half minute, about that much passed from the water into the air. If the water had retained these 2 degrees, then the greatest warmth of the thermometer would also have been correspondingly greater. We can therefore set it at 54 degrees. The thermometer thus rose by 54, 23, 31 degrees. And the water still had just as many degrees remaining, since at the start it had 80, 23, 57 degrees. One sees that in the same space. To warm the water and the mercury by 1 degree requires EQQI fire particles. Since the space of the water relates to that of the mercury as 42 to 61, there were at the start in the water 42 DACTI 57 fire particles, and these were distributed at the time of the thermometer's greatest warming in such a way that all 42 DECTI 31 remained in the water, and U61 EGCI 31 odd ECI had passed into the thermometer. Accordingly, we have 42 UCO 57 ECO to WECO to 31 NCDO Q or 4W cheat 7 QW Q keat 74. That is to say, 4 particles of fire in mercury give off just as much heat as 7 particles of fire in water, provided that water and mercury have the same measure. In the month of June 1765, I placed a mercury thermometer which had 30 degrees of heat, into water that had 18 degrees of heat. It fell in it very quickly to 21 degrees, and from then on very slowly. The mercury had therefore communicated to the water 21 89 degrees of heat, and still retained only 18 degrees. And yet it now had only the same heat as the water, namely those same 3 degrees. Now, the volume of the mercury was to that of the water as 35 to 59. Here, accordingly, we had 30 DG 18, 35 Chi 3 35 Q. On the 31st of January, 1766, I placed a spirit thermometer, which had 30 degrees of heat, into mercury of 15 degrees of heat, which I had in a cylinder of thin cardboard that did not touch the table. The spirit fell very quickly to 23 degrees, but from then on very slowly. The volume of the spirit was to that of the mercury as 143, to 202. If, accordingly, V stands for the spirit, which, with respect to water, is W, then we have here 30D15, 143 GTI, 2315, 143 GT, 1660, or approximately 1313. On the 28th of August, 1767, I placed a spirit thermometer, which had 29.3 degrees of heat, into water of 17 degrees of heat. It fell in it very quickly, up to 20.5 degrees from that point on, very slowly. The volume of the spirit of wine was to that of the water as 285 to 581. Accordingly, we have 29, 30, 17, 286 VG, 20.17. Therefore, very nearly. From these experiments, it follows in general, and after allowing for the small errors that can hardly be avoided in such experiments, that 4 fire particles in mercury, 6 in spirit of wine, and 7 in water produce the same warmth. Because in reality, an equal measure is taken from these materials, the ratio 4. 7 is 2:3, which differs little from that of Boerhaave. See 296. Boerhaave, moreover, mentions the matter only in general, in order to show that one would not have expected this small difference. In fact, Desaguliers also says that, with equal warmth in mercury, there are as many fire particles as in 13 times more water. Mercury is 10 times heavier or denser than water. And from this, Desaguliers believes that the density of the fire particles increases with the density of the bodies. But that does not follow. One could, on the contrary, conclude that because a denser body, with its own peculiar matter, fills up more space, it leaves correspondingly less room for the fire particles. Yet even that does not follow, because it is by no means established that every space which a body's peculiar matter does not fill is filled with fire particles. Desaguliers, moreover, presents his procedure as an experiment that he demonstrated before the Royal Society in London. He poured 1 pint of mercury, which had the warmth of the boiling point, into 13 pints of cold water, and at the same time he poured 1 pint of boiling water. In both cases, he placed thermometers, and these showed, after half a minute, the same degree. Now 1 pint contains about 29 Paris cubic inches. Therefore, 13 pints contain 391 cubic inches. And the warmth of the mercury is said, in half a minute, to have spread completely through these 391 cubic inches of cold water, and the thermometer is said already to have taken on the full warmth. That is hardly believable. In my own experiments mentioned above, the vessel never held a full cubic inch, and yet it took half a minute before the warmth was evenly distributed. In the experiments described in the Acta Helvetica, where I placed a thermometer in a bowl full of warm water, a full 7 minutes passed before the thermometer reached its maximum. That is, before it had the same warmth as the surrounding water. Presumably, in Desaguliers' apparatus, the bulb of the thermometer was close to the mercury, for in that way it could be warmed before the heat had spread through the whole mass of water, and thus before it became weaker in every part. Dr. Segner found that in mercury and in bismuth, equal quantities of fire particles produced the same warmth, all 309. In the first of the 4 experiments cited here, John 3044, the very short time of 30 seconds in which the thermometer reached its maximum at the outset caused a small irregularity that indicates an oscillation in the motion of the heat from the water into the thermometer and then back again from it. One can see this clearly if one takes the times as abscissas and plots the degrees of the thermometer, even only above the 48th degree as ordinates. But this oscillation is already visible in the numbers themselves. The thermometer rose to the 52nd degree. From there, it should at first have fallen slowly, then somewhat faster, and then little by little, ever more slowly. Yet fell from 52 to 50i, that is, by 1 degree in the next 15 seconds. In the following interval, it fell only by half a degree, and then by 0.6, 0.82. This shows that the heat pressed into the bulb of the thermometer with such force that the fire particles attained a speed with which they struck through the entire diameter of the bulb, instead of piling up in the middle. In which case, the bulb would have cooled more slowly, though more uniformly. This circumstance causes the formulas given above, when applied to the experiment, not to agree exactly with it, because the formulas presuppose a uniform cooling. A similar deviation, But in a completely opposite sense, I found on 29 June 1772, I placed a mercury thermometer in a vessel of water. The former had 73 degrees of warmth. The thermometer then fell as follows. After the thermometer had at first fallen very quickly, it then fell much more slowly, and immediately afterward again somewhat faster, whereupon it continued to fall uniformly and without noticeable oscillations. Here, at the beginning, the particles of heat forced their way with power out of the thermometer into the water, passed through it with a perceptible speed, but were partly reflected back again by the vessel and by the surface of the water. Partly were reflected back again by the glass sphere, penetrated into it once more, and delayed the process, so that the sphere cooled more slowly. It is also probable that such oscillations already occurred in the first minute, but could not be noticed because of the rapid fall. Finally, however, they did have the effect that the further cooling became more uniform. If one plots the times as abscissas and the degrees of the thermometer above the 23rd as ordinates, this oscillation clearly strikes the eye. I have already indicated above 263 that with the mercury thermometer I found the cooling constant to be about twice as large as with the spirit thermometers, whose bulbs are of the same size. The experiments reported so far, 304, 308, may now serve to explain this. To this end, I note that when both thermometers cool in air, the particles of heat do not pass directly from the spirit and the mercury into the air. Rather, they must first take their way through the glass of the bulb. Now, the passage from the mercury and the spirit into the glass has 10 times less difficulty than the passage from the glass into the air, 263, 266. This causes the glass to take up the heat of the mercury and of the spirit, where, not perfectly, yet with only a very small difference. If, therefore, the mercury and the spirit of wine in both thermometers are equally warm, then the glass too has the same warmth. Now, since I see both bulbs to be of the same size, they also have the same surface area. Consequently, in the first small interval of time, equally much heat passes from them into the air. That is to say, from both glasses, equally many fire particles go into the air. And in order for it to remain so, equally many fire particles must also pass from the mercury and from the spirit of wine back into the glass. But when an equal number of fire particles is lost, the mercury loses more heat, because 4 fire particles in mercury give just as much heat as 6 fire particles in spirit of wine, 308. Let I be the heat of the mercury and U the heat of the spirit of wine. Further, let 7 and Thea be the cooling subtangents. Then for the first small interval of time, DDO, 258, DICGD 70. But the decrease of heat DIDO arises from the departure of an equal number of fire particles. Therefore, DID64, DH2D. This gives 327 cheat teta. The cooling subtangent of the mercury thermometer is therefore to that of an equally large spirit of wine thermometer as 2 to 3. That is, it is 1/3 smaller. This follows accordingly from ED 308, where the experiments are compared with one another. From GCA 306, however, it follows from the experiment itself that 7, Teta 13, 21, which comes closer to the ratio 3:5 derived above 263, although this too is only given in general, for spirit of wine and mercury are not always of equal quality. We therefore see from this that the difference of the subtangents arises simply because in the same space equal numbers of fire particles in different materials do not produce equal amounts of heat, and because these materials, when enclosed in glass or in vessels of any kind, must be regarded as enclosed. Martin, moreover, had the different rates of warming and cooling, meaning, to show the difference of the subtangents, pour the materials into open vessels, so that at least their surfaces were directly exposed to the air. Yet the greater part of the circumference was nevertheless enclosed by the vessels, and so warming of one body by another. Thus, from his experiments, it cannot be determined how the constants change when the material, over its entire extent, is in contact with the air. Section 312. The preceding considerations concern such bodies where one completely surrounds the other. If, however, they touch only on one side, then both bodies are necessarily exposed to the air. and thus there is a third cause of change, the loss of heat. Since in all these calculations only the loss of heat is taken into account, for the sake of brevity I shall set the heat of the air equal to 0 and call the bodies warm only insofar as they are warmer than the air. At an arbitrary time, let Y be the heat of the warmer of the two bodies, and Z the heat of the other. From the warmer body, in the time element DD, heat departs in two ways. First, into the air, the amount UR divided by 7, and into the other body, the amount YZ divided by theta. Here 7 and theta are the corresponding cooling constants. We therefore have the first equation, D, 7. The portion that is transferred to the other body changes its value by Y zeta for the reasons given above. Since this body is likewise exposed to the air, it also loses in the time element dE a portion of its heat Z2 divided by 9, where I take 9 to be the corresponding cooling constant. We therefore have the second equation, GZ9, section 313. From these two equations there likewise result, as above, two integral equations of the form so that the cooling or warming of each body takes place according to the sum or the difference of the ordinates of their logarithmic curves. The constants E, A, and O to the quadratic equation 0 G chi A fract M7 var theta T7. 7 theta var theta 9 theta 7 var theta. Dann 7 var theta 9. One then further has Jung fract 1 fract theta 7 fract. And if, and it does denote the initial heat or the value of Johann for T0, then one also has the two equations H and D and B. So that in this way, the initial ordinates A, B, J, these formulas include within themselves those given above P300, so that one can derive them from these if one regards 7 as infinite, and then calls 7 and var theta, what I have here called var theta, and 9, 3, and 14. The constants 7, and 9 used here are, in general, to be understood as being in direct proportion to the masses of the bodies to which their cooling refers, and in inverse proportion to those parts of their surfaces through which the particles of fire depart. These proportions, however, hold only insofar as the bodies are small and regular enough that the heat they receive is distributed uniformly through their thickness without any noticeable lapse of time, and insofar as the initially occurring oscillation, 309 to 310, is not taken into account as an inconsiderable non-uniformity, third section, warming and cooling of several bodies among one another, 315. Under the conditions just stated, 314, one may now also consider, in general, 14, an entire system of bodies that touch one another, wholly or in part, where heat passes from the warmer into the adjacent colder ones, and, insofar as they touch the air, is carried off into the air. Applying the calculation to this more general case presents no difficulty. For each body, insofar as it is warmer than its neighbors, as many cooling constants must be used, as there are adjacent colder bodies around it, counting the air as well, if it too is in contact. And since the heat that passes into the adjacent colder bodies changes its value, 298, these changes are to be treated by means of as many coefficients m, n, etc., as was indicated there. If, for any small interval of time, DDO one subtracts, for each body, the sum of the heat flowing out from the sum of the heat flowing in, one obtains the differential of its heat, and thus just as many differential equations as there are bodies. 316. These differential equations, taken in the most general way, have the following form: dx cat ax dby cz, etc., dx etc., where x, etc., etc., where x, etc., where x, etc., where represent the heat of each body at time, and a bc, etc., are coefficients determined by the cooling constants theta, etc., and by the coefficients mm and laws, etc. These differential equations are not always so complete. For if, for example, body x does not touch body z directly, then C2H0, Thus, one or more terms drop out. But if one wishes to learn to know the laws of warming and cooling of a system in their full generality, it is better to retain all the terms. The integral equations, therefore, have in general the following form: x dk, etc. Thus, at every time, the heat in each body is the sum or difference of as many exponential terms as there are bodies. And for all bodies, these terms have the same exponents, etc., and therefore differ only with respect to the initial coefficients, etc., b, etc., ci, etc., and so on. This is therefore the general law of the warming and cooling of a system of bodies in contact with one another, under the conditions mentioned above. The exponents alha, deity, etc., are here, of course, very unequal, and this has the effect that in the end of all the exponential terms only that one remains appreciable, which has the greatest exponent. Now, since heat in general passes 8, 10, now, since heat, and even more times more easily from one body